So in today's lecture, we're going to look at another high-level methodology called attack trees. We're going to do a pretty substantial or large example where we apply attack trees to studying a specific protocol called HTTPS. And so this is going to take multiple lectures to sort of go through. Okay, so high-level methodologies, you can remember, they're a methodology that's going to work kind of for everything. You could apply it to software, you could apply it to hardware, you could apply it to a policy, you could apply it in maybe a social engineering scenario. But generally speaking, with a high-level methodology, you're not going to be able to do a really deep dive. So what attack trees are, they're a nice way of sort of balancing the two. Where it is a high-level methodology, you can apply it to almost anything, but it also allows you to express low-level details. And so you're going to see this because we're going to literally take 3 lectures to go through just one attack tree for this protocol called HTTPS. Okay, so just to compare attack trees to the other methodologies that we've seen, an evaluation framework, we're talking about comparing different solutions. With Stride, you're looking at one solution, so it's a little more narrow. And then attack trees are even more narrow than either of the other two. What we're doing is we're not just considering one solution, we're considering one adversary's goal on that solution. So we have an entire tree just for one possible attack on one system. And then if we have a second attack on the same system, then that's a whole new attack tree. And if we have 5 different solutions, then we need 5 different attack trees. Okay, so it's much more narrow in its focus. So what we're going to do is we're basically going to say, okay, you have a solution. A solution is anything that requires security. So again, hardware, software, a policy. In this class, we'll look at HTTPS. And we're going to think about one goal. So what's one thing that an adversary should not be able to do? And what an attack tree will do is it will basically enumerate all the possible ways that you could break that property of that solution, or the adversary could achieve their goal. Okay. Now, the word attack sometimes is distinguished from the word threat. So sometimes we say, you know, an attack is something that actually happened. Someone did it at least once. And a threat is like it's a potential. There's a potential for an attack there. We're not sure whether anyone's actually done it or not. So for attack trees, what we're interested in is including both attacks and threats. So we could call it a threat tree instead of an attack tree. It would probably be more accurate. But for historical reasons, people call it attack trees. And so we'll stick with that terminology. But I just want to emphasize that if you can think of threats, so possible things that are plausible, you can put those in your attack tree as well as actual attacks itself. Then going back to Stride, Stride can help you with an attack tree. So they're not mutually exclusive. So you can kind of go through, you know, spoofing, tampering, repudiation, you know, all the different letters in Stride. And you can think about, okay, is there a spoofing attack? Is there a way that the adversary could achieve their goal using spoofing? What about tampering, right? And this can help you try to complete your tree and make sure that you are comprehensive and you see lots of different attacks. So the attack tree that we'll develop over the course of the next 3 lectures, you're going to see almost all the aspects of Stride will show up in at least, you know, different branches of this particular tree. Now, the last thing, this is why attack trees are great, is we mentioned that you sort of have this trade-off. So you can do a high-level methodology, but any methodology that's general enough that it could apply equally well to software and, say, policies or to hardware, it's not going to let you find attacks in a system if you don't understand how that system works. So with an attack tree, you need to understand the system first And then you can start thinking about how to break the security of the system. So one of the reasons why, again, we're going to spend 3 lectures just looking at basically one attack on one protocol is because a lot of those lectures I'll spend teaching you what the protocol is. I'm not expecting you to know what HTTP is off the bat. Okay, what does an attack tree look like? So we'll see an example. We'll do a quick example before going into the big example. But basically, it's a visualization of every way of attacking a system, or at least attacking one property of the system. Because attacks take multiple steps, what we do is we sort of link them together kind of like a branch in a tree. And because there's different ways of attacking the system, and some of the systems are related, or some of the attacks are related. So they have the first 3 steps are common. Then you're going to fork, and for one attack, you're going to go down one branch of the tree, and for another attack, you'll go down another branch of the tree. Okay, so the root of the tree is what the adversary's goal is. And then if you go all the way to a leaf, that's an actual attack or a threat. And then the branch, as you go along the branch, it will kind of tell you the story of the attack from the adversary's goal to actually achieving the attack itself. Okay, so when you're making one of these, what you'll do is you'll start with the goal. And one tip is usually the way I think about it is, why can't the adversary just do their goal right away? Like they have some goal, they want to break some property, like what stops them? So usually there's a defense mechanism or a set of defense mechanisms that prevent it. Then you can say, okay, well, can the adversary defeat that defense mechanism? Why can't the adversary just defeat it? And then you might think, well, they can't defeat it because of these reasons. And then you say, okay, well, is there any way to defeat those? And you sort of iterate down the tree, just sort of thinking about attacks, defenses, until you break through all the defenses and then you reach your end goal. Okay. Again, we'll see in a second an example of this that will make it a little more concrete. Okay. So the example we'll use at first is just a simple thing. So what's this? This is a parking lot. And let's say that the adversary's goal is to leave this parking lot without paying. Okay, so this is a parking lot. You pull in with your car. You get maybe a ticket on entry. And then you need to pay before you leave the parking lot. So you're not paying when you go in. You're paying when you go out. Okay, so is there any way that you can get out of this parking lot without paying? That's a goal an adversary might have. Okay, so we can develop an attack tree around this. So like I mentioned, what we should just think about, well, why can't they just leave, right? Like what's stopping them from leaving? Okay, and so the thing that's stopping them is the thing that's in the picture, right? You have this sort of robotic arm, it's lowered, it's a physical barrier. And so that's what's stopping you from just leaving. And then you also have the whole ticketing system, the whole payment system, right? And so if I'm able to pay and convince the computer that I paid, then the robotic arm will lift. Okay. So you can start thinking about, okay, what are the different ways I could get out of this situation? So this is not going to be a comprehensive thing at all. This is just a fun example to warm us up. But you might say, okay, there's kind of like 2 approaches. One approach is that I could do something about this arm. If I can evade the robotic arm, then I'm able to get out of the parking lot. And I could also do something about the payment, right? If I'm able to not pay, then I would be able to get out of the parking lot as well. Okay, so what are some ways that you could evade the robotic arm? So you can think about it for a second. Okay, so here's some ideas. One idea is you could just literally just drive through it. Okay, so that is a valid attack, right? And so that's something that you could put in your attack tree, and that satisfies the property. Is it the best attack in the world? Probably not, right? It's going to result in Probably a police investigation because you're destructing property. You can imagine there's probably security cameras that would have captured your license plate. And if you're prosecuted by the police successfully, it could result in, a serious fine. I don't know, maybe even jail time, maybe not. But anyways, it's not the best attack, but it is a valid attack. Okay. And you can think of other kind of physical things as well. So maybe you could just drive around the arm somehow, or there's another way out. Maybe you have to hop a curb. Maybe you have like a fancy SUV or something like that where you could drive over a curb and somehow get out of the parking lot without going through the arm. Okay, so those are examples, and they're things that you could put in an attack tree. Okay. Now, another thing you might do is you might say, well, when does the arm lift? So the arm lifts after someone has successfully paid, then it lowers, right? But sometimes people, like they have a car, they might have like a trailer on the end, and so they're pulling something. And so, it's kind of almost like two cars are going through, right? So the arm lifts, the main car goes through, and then the trailer goes through. And usually the arm isn't going to, come down in between, hopefully, if it's designed correctly. Okay, so what you could do is you could think, well, what if I tailgate someone? So if someone's leaving, I'll drive really, really close to them, and we'll kind of look like two cars. Or sorry, we'll look like one car, like maybe a car and a trailer, or a car that's pulling something behind it. And so the arm won't come down, and then I can get out without pain. Okay, so that's another approach that you might take. Another thing you might think about is failure scenarios. Okay, so in security, this is something that we are going to see over and over throughout this course, is generally when things fail, you need to decide between, do you maintain security under a failure, or do you let security go when things fail? Okay, so if you maintain security when things fail, we say it fails closed. And if you let security go, then we say it fails open. Okay, so let's think about the robotic arm. Let's say there's a power outage. Okay, so now the arm can't go up and down. We could fail closed, meaning that nobody can leave the parking lot. Okay, so that's the most secure. Power's out. We'll wait until the power comes back on. And then when the power comes back on, then we can start processing payments and letting people out of the parking lot. Okay. Unfortunately, people are going to be very angry if you do this, right? If they can't get out of a parking lot, the power failure is not their fault. They need to go somewhere. Maybe because of the power failure, they have to, leave very quickly, right? And so what you're going to see in a scenario like this is the system's going to fail open, meaning they'll probably manually open, they'll lift the bar up, and they'll just let people out. And since they can't collect payment, they have no choice, right? They'll just let people go. Okay, so that's one example of a system that fails open. And so anything that you do as an adversary to trigger that arm not working, whether it's a power outage, but it could be other different approaches, then you can expect the system to fail open, and then you could be let out of this parking lot without paying. Okay. Another thing is really the only way to open it? Is it really just by paying? Is there any other way that you could maybe override it? And so most of these arms are going to have an override, right? We just mentioned if there's a power outage, the attendee is going to have some way of lifting the arm up. Usually there might be like a key or something that's needed. So what you could do is you could try to get that key. Generally speaking, if you can get a photograph of a key, and then you can reconstruct, you can 3D print a replica of the key, and then you could use it. So if there's some way of getting the key, then maybe you could override the arm and make it lift. Because there's somebody with the key, that's a human being. And so you could also try to apply social engineering to that human, right? You could try and tell a fake story about why you need out of the parking lot, or why they need to open the arm, or whatever. There's different approaches. We'll do a whole entire lecture on social engineering. I won't go into those details now, but you could try to apply some of those techniques. The adversary could apply those techniques to the attendee and then get out of the parking garage. Okay, so in an attack tree, what we would do is we would sort of put all of these things together. So you would see that these things are kind of clustered together. So if you're going to like try to drive around or drive through, those are related to each other. They're both like sort of physically ways of evading it. So you might put them together in the tree, and then other types of attacks are they're all related to the idea of you're trying to get around this arm. Okay, but they might be, some of them are more related than others, and so that's how you sort of structure your tree. Here's just some pictures of things, so you can see a picture of someone driving through one of these arms. You can see what's probably the worst designed parking lot. And so what's happening in this picture? Well, you can see that there's an arm there, right? But there's no other physical barriers. And so if you want to get out without paying, you just simply drive around. And based on the sort of tire tracks that are going through the snow, in this case, it's pretty obvious that a number of people are trying to get out of the parking lot that way. And then this is just an example of a 3D printed key based on a photograph of a key. And you don't need a high resolution photograph like this, by the way. If you can, sometimes maybe it's a stereotype, but I picture sometimes people like an attendee walking around with like a big keychain with a bunch of keys hanging off their belt that are publicly visible. If you can get a picture of that, then that should be sufficient in order to reconstruct the key itself. Now, the other kind of approach that we could do is we could look at, okay, can we get away from not paying somehow? Okay, so maybe we counterfeit money, or we could just claim to have paid. Again, this is maybe more social engineering. We could go to the attendee and say, okay, we did pay, it didn't work for whatever reason, or it said it went through, but now I'm trying my ticket, it doesn't really work. The ticket itself is sort of the evidence that you paid. So different machines or different, parking lots work different ways. I'm envisioning one where you get a piece of paper when you enter, then you put that piece of paper into a payment system, you pay, and then what the payment system will do is it will write the fact that you paid back onto the ticket. So the ticket usually has like a magnetic barcode or something like that. Sometimes they have a QR code. That system's slightly different. So there's the difference between a system where the fact that you paid is actually written on the ticket itself. So the ticket itself has the evidence that you paid. In order to do that, you need to be able to write data to a ticket. And so like a barcode is typically how you would do that if it's just a cheap thing. The more common technology is a QR code. In this case, there's a back-end database. So when I pay, I scan the QR code and it finds a database entry for my ticket. It marks in the database the fact that it's paid. And then when I leave, it needs to check the back-end database so that the thing that's at the gate as I'm leaving, that also has to have an internet connection or an intranet connection into the database to see that I paid or not. But in any case, one thing that, for example, how I got out without paying, although it wasn't intentional, recently at the university at Concordia, is I just folded the ticket. It had one of those magnetic barcodes on it. I folded it, I put it in my phone case, and then when I went to scan it, it didn't work because I had folded it. And so then I just said, well, I folded it, and they're like, okay, who cares? You can just go. Okay. Now, another thing I'll mention. So this touches on repudiation in Stride. So repudiation is where you say something happened that's different than what actually happened. Okay, so you could purposely ruin your ticket, and then you could, claim some story about why you ruined it, and you could probably get out of the parking lot for free the first time. Okay, but generally with repudiation is you earn a reputation, right? The attendee remembers that, and so the second time it's not going to work, or the third time or the fourth time if you keep doing it, right? So there's a bunch of attacks that kind of work the first time. But then, if you keep repeating it, then people become skeptical of the stories that you're telling, and then they don't let you get out without paying. Anyways, you could also, if it does have like kind of a barcode or something where it's printed, the fact that you paid is printed on the ticket itself. You could get some sort of reader, writer, reverse engineer how it's written onto the ticket, and then you could probably just write that field or that flag it as having been paid. Okay, another idea for tickets is, so generally what happens if you go into a parking lot, you drive around, you realize, oh, there's no spaces, and then you leave. Do you have to pay? So generally parking lots are free for the first 5 minutes, maybe 30 minutes, it depends on the policy, but generally you're not going to have to pay. Okay, so what if you're just about to leave, and right before you leave, you just go up to the machine for coming into the parking lot, and you say, give me a new ticket. And then you take the new ticket, and then when you leave, you use the new ticket when you leave. And because it's fresh, it's only a minute or two old, it just kind of looks like to the system that you drove around the parking lot and you couldn't find a space, and so you're leaving right away, and then it won't ask for payment. Okay, so generally this doesn't work. So there's some techniques that parking lots use to try and make sure that the machine that gives you a fresh ticket when you enter will only give you that ticket if there's a car present. A simple way of doing it is just by weight, but there's more sophisticated ways. But just for the sake of this example, let's assume that you're using a weight sensor. Okay. So what could you do? Well, if you can make the sensor think that there's a car there, then you can get a fresh ticket. Then you can get out of the parking lot without paying. And so you could have all your friends, come and stand there with you, and maybe all your friends add up to the weight of a car, and then it will give you a ticket. Okay. Another thing is, if you know someone else that has a car, you could have them pull up to enter the parking lot, get a fresh ticket, but then instead of entering the parking lot, they just sort of reverse and leave. Okay. So again, you can always reverse and leave, but it might be a bit awkward depending on how the parking lot is set up. But that would be a way to get a fresh ticket. Okay. There's even more sophisticated attacks. So there's an attack, I'll call it chain attack. It's actually related to something that we see in voting systems, where it's called a chain attack. This is why I thought of this attack. But what you could do is you could go into the parking lot, park, and so you have this ticket, and you can't get out unless if you pay, whatever it is. Let's say it's $20 to get out of the parking lot with this ticket. What you do is you wait for someone else who's about to come in legitimately. They're coming in to park, and you just say, hey, I'll swap tickets with you. You give me your fresh ticket. I'll get out for free, and you're going to get burdened with this like $20 ticket. But don't worry about it, because when you're about to leave, you'll just do the same thing. You'll find someone else that's coming in at the same time. You'll swap the tickets with them. You'll get out for free, and they're going to be burdened with this ticket that you have to pay to get out. But don't worry, they can do it again. And so this chain can basically go, as long as people are going in and out of the parking lot, this chain can kind of go on forever. And the only person that has to pay is the very last person. Now, they might have to pay a lot because it looked like they came into the parking lot when the very first person who started the chain came into the parking lot. But generally, parking lots have a max, like a daily max or something like that. And so, or another thing you could do is you could just say that you lost it. And then if you lose a ticket, usually they charge you the max. Okay. So once the value of that ticket increases to the max, then that person pays the max, and the max that's being paid at the end is probably a lot less than the accumulation of all the tickets that people were supposed to pay going in and out. Okay, so that's an example, anyways, of a more sophisticated kind of attack. Now, back to attack trees. Here's the whole tree. The point is that you can have all these attacks. They can all sort of hang out together in the same tree, which is nice because we saw social engineering. We saw, failing open. We saw these sort of more detailed technical attacks like the chain attack. We saw really brain dead, simple attacks like, just drive through the robotic arm, right? And all of these attacks, they can all be part of the same presentation, okay? And so this is what a tree looks like when it's done. And so the goal is the root node. The leaf node is an actual successful attack once you sort of break through. And then if you follow a path, right, it sort of tells you the story of the attack. So my goal is to leave without paying. I'm going to try and get out without paying. But I can't do that because there's this tickets. And so I'm going to take my ticket and I'm going to tamper with it. And so now that I've tampered with my ticket, then I don't have to pay. So I've evaded payment. And because I don't have to pay, it will let me leave despite the fact that I haven't paid. Okay. So you sort of, if you go from root to leaf, it kind of tells a story, and then you can go from leaf back to root and see how you broke everything and then successfully attack the system. Okay, so that's just a toy kind of example of what an attack tree might look like. Hopefully a fun example. And hopefully it also shows you that you can put a lot of detail into one of these attack trees, depending on the level of detail depends on the level of detail in the attacks themselves. So if you have detailed attacks, then your attack tree can be very detailed as well. So what we're going to do next is we're going to look at a longer example. This is an example called HTTPS, and we're going to do a big attack tree, again, across like 3 lectures on how to attack HTTPS, or how to do one specific attack against this protocol. But before we're talking about the attack, let's just talk about what HTTPS is. Okay, so generally, if you're browsing the web, you have your laptop, you're connecting to a server. Let's say you want a website. You say, "Hi, can I have the website?" And then the website will send a copy of the website to your browser. Your browser will display it to you. The protocol, the network protocol that's being used to fetch that information is called HTTP. Okay, so HTTP, you know it because you've seen it. You might not have to type it in anymore, but you've definitely seen URLs like HTTP://. So that means that accessing that particular site happens over HTTP. It's not just limited to browsers. It's used in all sorts of networking applications, but we'll focus just on the browser case just to keep things simple. We don't really have to think about details beyond that. In most cases, there's maybe one attack where we do. Now, HTTP has no security. I don't know what security means yet. We'll get to defining what that is, but I'll just tell you that there's no security to it. And so what people wanted to do is they wanted to add security to it and create a secure version of HTTP. And so that secure version is called HTTPS, where you can think of the S as standing for security. Okay, so HTTP is the network protocol, and then the S comes from adding security to it, and specifically we're going to add some cryptography. And the library or the sort of approach that's used for cryptography is either called SSL or now is called TLS. It's the same protocol, they just changed names at a certain point in history. This is the kind of the history laid out for you. So the protocol started with the name SSL. It was developed by Netscape. It was developed in the early 90s. They had a couple they had some internal protocols, and then I guess they did a major revision of the internal protocols, and so they gave it the term or the name SSL 2.0. So there was no SSL 1.0 that was released publicly. It was something internal. But then SSL 2.0 came out. It was released. It was put into browsers like Netscape Navigator and then later Internet Explorer. And it kind of became the default way of doing cryptography for making what's called a secure tunnel. Again, we'll get to that in a second, what properties you actually get from it. Okay, SSL has undergone a bunch of revisions. At a certain point, at the point that it became known as TLS 1.0, What happened is the protocol, actually a lot of network stuff, all sorts of things about the web and your browser, and we'll see examples later, by the way, when we talk about cookies and same origin policy. A lot of this stuff was invented by Netscape, IBM, these early, maybe Microsoft, these early technology companies. But then when the web became more universal and lots of people were using it, people didn't like things that were tied to specific companies, or certain companies had kind of authority over them. And so what was created is something called the IETF, which is not a commercial entity. It's a sort of nonprofit organization. And what it does is it does all sorts of standardization of all the things that sort of go along with the web. Okay, so when it was handed over to the IETF, they decided to change the name, maybe to distinguish it from the commercial versions. So they changed the name to TLS. Okay, so it was called TLS 1.1, sorry, 1.0, 1.1, 1.2, and then today we have TLS 1.3. So that's the current version when I'm recording these videos, which is in 2026. We're still at TLS 1.3. And then every time a TLS is released, there's people that are hard at work on the next version, right? So TLS 1.4, there's some drafts. It's going to add a bunch of post-quantum things, and there's going to be some important developments in it. But right now, as of when I'm recording this, TLS 1.4 is not out. Okay. The other subtle change is SSL stands for Secure Session Layer, and TLS stands for Transport Layer Security. If you know your OSI model, I'm not expecting you to, but if you've done networking security or just networking in general, you might know that the word session means something specific in the OSI model, and transport also means something specific. They're different layers. And so the name shift also kind of implies that the layer in the OSI model at which this protocol is occurring changed, but it didn't actually change. It actually is in the same place. What they did is they just tried to sort of correct the language to make it reflect the right layer where it should be happening. Okay, what does HTTPS look like? Okay, so I'm on a website, and I might access that website over HTTPS, or I might access it over just HTTP. How do I know the difference? So today, again, as of when I'm recording this, this is basically what the UI says. So for a website that's not served over HTTPS, it's just served over HTTP, you will have the addition of the word not secure. This is Safari, by the way, so browsers might do it slightly different. So Safari will say not secure, and then when you're over HTTPS, the not secure disappears. So if your URL bar just looks normal, then you're over HTTPS, and if it says not secure, then that means that you're not over HTTPS. Another thing you might look at is if you click, for example, on it, you can see the full URL, https://. And so this also is an indication that you're at least trying to load this page over HTTPS. Now, there's a slight difference in the sense that this actually just means that you try to load it over it, okay? And this will get displayed even if you're not successful. Like, let's say that you try to load it, but there's some thing that goes wrong. It will still show HTTPS here, but it might show not secure here, okay? So the first two, this just means that the connection went through and the connection right now is secure or it's not secure. And this technically just means that you loaded it. But the chances of those like kind of weird corner cases where you tried to load it but it didn't work are very, very rare. They're so rare that you might as well just ignore this distinction and just think about these two being basically equivalent ways of telling whether something is loaded over HTTPS or not. Okay, now if you've been around the internet for just maybe 2 years, you might say, well, wasn't there like a lock? What happened to that? And so this was the old UI, so this has recently changed. But previously what would happen is when HTTPS was enabled, it would show a lock. And when HTTPS was not enabled, it would show not a lock. And the idea is that I think the idea behind the motivation for changing the UI is when you show a lock, it's kind of like this is special, right? The special case is when you're doing things securely. And when it's not there, it just looks normal. That's kind of like the normal case. So it's almost like sort of implying HTTP is normal. We don't show anything special. And when you enable HTTPS, that's special. So we're going to give you a special symbol, which is called a lock. But what browsers want is they want a world where HTTPS is used everywhere. Okay, they don't want it to be the special case. They want it to be the normal case. And so here, the normal case is you don't show anything. And then the special case now is when you're going over HTTP. That's like hopefully the rare case. And so what we're going to do is we're going to invent a special indicator, a visual cue for the special case. And so it's just a subtle way of trying to normalize this idea that HTTPS should be turned on everywhere. Okay. All right. Now, how do you end up on a page that's being served over HTTPS? Okay. So there's a couple different ways. The first way is that you can explicitly ask for it. So you can type HTTPS:// and then the actual domain that you want to go to. And what your browser will do is it will try to establish that HTTPS connection. And if there's any sort of problem doing that, then either the indicator will not be present or you'll get some sort of error message or something like that. We can look at examples of that later. Okay, another thing. Okay, so most people aren't going around typing URLs in, right? It was something that maybe, when I was growing up and using the internet for the first time, there weren't that many websites, and you might actually remember the websites that you want to go to. You would remember their URLs, and then you would just type it in. But now we don't tend to remember things. We just browse, right? We go to a search engine, or we don't even go to the search engine because it's built into our browser. We just type in what exactly we want, and then we get back some links. And if Google shows you a link, Google themselves are making the decision of whether to send you to HTTPS or HTTP. Okay, so it's embedded, the link to that page is embedded into the search results, which you're receiving from Google. And so Google made that choice themselves. You, as the user, aren't making that choice. Now, Google has security, in their sort of best interests. And so they're going to send you to the HTTPS version if there's an option to do that. Okay, it wasn't always the case. So I remember not too many years ago when Wikipedia, for example, had both an HTTP and an HTTPS version, and they were both live. And so Google would actually send you to the HTTP version. And once you were there, you could switch to HTTPS by adjusting, like typing HTTPS, adding the S in the : / before wikipedia.org, and then you could move over to HTTPS yourself. Now, in this case, how did they decide it? Well, Wikipedia is a big organization, and Google's a big organization. And so it wasn't a case of like, one website who's never met anybody from the other website, trying to make a judgment call on which version to send it to you. This is something where people from both organizations knew each other, and there was probably just a conversation about it. And Wikipedia were initially, I think, concerned about the performance. You might think that HTTPS hurts performance because you're going to do a bunch of cryptography that you wouldn't otherwise have to do. But today, with most like hardware that's available, typical servers and things like that, all the cryptography is handled basically in the hardware level. And so the speed of a website of serving, or sort of the performance load of serving a website over HTTPS is negligible compared to HTTP. So there's really no performance difference today. It wasn't always the case, but today it's the case. Okay. Now, another thing is your browser just might know, I know what that website is. For example, in Safari, let's say I open Safari and I just type in a search term into Safari. Then what will happen is Safari will send me to Google, and it will send me to the HTTPS version of Google. Okay, so it just knows about it. Another thing that you might do is have a browser that just knows what websites are available over HTTPS. So Chrome is this way. So Chrome is preloaded with a bunch of websites that will only take you to the HTTPS version. Preloads are based on, again, sort of you knowing someone at Google to get your preload into Chrome. But what you can do is you could announce the fact that you want to only be served over HTTPS just on your website itself. Okay, so every time someone visits your website, you send an extra little thing in the header of every response that you give that just says, by the way, I only do HTTPS. I want you to remember that fact later. And so two things will happen. One is your browser will remember it. It's called pinning. And so your browser will pin the fact that you only want to be accessed over HTTPS. And the second thing is for browsers like Chrome, because Google makes Chrome and they're also scouring the internet because they run a search engine, their crawlers will eventually find your website. They'll notice the flag. And then I believe Chrome will automatically put in the preload once their crawlers sort of see the fact that you want to have it pinned. I'm not 100% sure. I'm pretty sure that that's how it works now. Okay. Now another thing is you might go to the HTTP version, and then what the website will do is it will say, okay, I'm going to redirect you to HTTPS. Okay. So this is called a redirection. Redirections are not secure for reasons that we'll put into our attack tree at some point somewhere. But basically, if there's an adversary, the adversary can try and stop this redirection from happening. But we'll get there eventually. Okay. All right. So these are all the different ways that you would end up on an HTTPS website as opposed to an HTTP website. Now what we'll do is we'll think about what security properties does HTTPS give you. So the analogy I like to use is that of a secure tunnel. Okay, so what it does is it gives you a secure tunnel between you and the website that you're accessing, in this case, Concordia, for example. Okay, and what it secures you against is there's a bunch of parties that could be in the middle of your connection, and they could be eavesdropping, so reading what data you're sending back and forth between this website. Or they could be active in the sense that they're actually overwriting the data. So you send one piece of data and they change that data to something else and then send it on. So adversaries like this we call, classically in cryptography, they were called a man in the middle. So MITM. I'll use that terminology even though there's no reason why it needs to be a man as opposed to any other gender. It's just sort of old-fashioned language. But generally, we'll just talk about the adversary in the middle, but sometimes we'll use the acronym MITM. Okay, so what are the properties that you would expect from the secure tunnel? You're sending messages back and forth. What do you expect the tunnel is going to do for you? So what it does is three things. There's one thing that's pretty obvious. If you just look at this picture, it's probably the thing that you're thinking of. And then I find when I ask in class this, students struggle to name the other two properties. But the other two properties are really important as well. And arguably, you can't really have the first property without at least the third of the properties. But anyways, let's go through one by one. Okay, so the obvious property is that if you have a tunnel, the person in the middle, the adversary, the purple adversary here, can't be reading any of the information. Okay, so they don't see it, right? Because they're outside of the tunnel. So we call that confidentiality. So you can't read data, even if they're in the middle. So even if all this information is flowing through them, right? Then they can't read it. By the way, how do you get in the middle? So this is something I won't dwell on in this class. I cover it in other classes I teach, like 6120. But there's a bunch of different ways at a high level. So for example, they could be on the same network as you and somehow they poison the routing so that the routing goes through them first before it exits onto the internet. They could be colluding with any of the parties that are sort of on this back end, which tend to include things like your ISP, maybe government organizations, Concordia's ISP, different entities like that. They can also get in the middle when sort of packets cross from, say, your ISP. So let's say I'm on Videotron and Concordia, their ISP is called RISC. And so when packets kind of go from Videotron to RISC, it goes through this protocol called BGP, and there's some attacks that you can do at that stage as well. Okay. Another simple attack is I could just put up a Wi-Fi router. I could have the exact same, I could call it Concordia University. It matches the same SSID or the Wi-Fi name as the actual university. But because your computer is closer to mine and you're clicking on which Wi-Fi you want to connect to, you might connect to mine instead. So anyway, these are all like some examples of things that you can do. Little later in the lecture, we'll look at one thing called Firesheep that did one of these things. But in general, we're just going to assume that that the adversary, if they want to, they can get in the middle of your communication. Okay, so we want this thing to work even if they can get in the middle. We don't want to rest on the fact that, oh, it's hard to get in the middle, so we don't really have to do anything special because, you know, the adversary is never going to be able to get in the middle. No, we want to take this sort of paranoid view that says the adversary can always get themselves in the middle. We got to make sure that we're protecting against that even if they're in the middle. Okay, so if they're in the middle, message confidentiality says they can't read the data even if they're in the middle. Okay, what else do we want from a secure tunnel? I mean, isn't that it? Isn't that the only thing that we care about? So it turns out we're missing two properties. One property is integrity. What that says is that if I send data into the tunnel, the person receiving it is going to get, well, ideally we want them to get the data exactly as I sent it. Okay, so there's no way to change the data in the middle. It's a little too strong. The adversary in the middle can always change the data. Even if it's in a tunnel, they can sort of change so the tunnel's kind of representing encryption, so they can change the encrypted data around. Okay, but what we can do is we can make sure that we can always detect it. So I can look at it and say, no, someone tampered with that. The checks that I'm doing, they're not checking out. And so I want you to resend that data and try again. And maybe if I can't ever get the right data, I give up and we drop the connection. But anyways, and it's not only an adversary that might tamper with the data. It could be some sort of accidental thing where the data is getting corrupted, or there's network transmission problems, all sorts of things in the middle. And so what this message integrity gives you is it gives you basically a guarantee that if the check holds, that you know that the data that you received is exactly the same as the data that Alice put into it. Okay. So message integrity and confidentiality sort of go hand in hand. This is really important as well. Sometimes you don't care about confidentiality. Like, for example, let's say I'm downloading some software from a server. I want to make sure that someone in the middle doesn't put malware in it, and then when I get to my machine, like I'm getting it from the correct place. I'm downloading it, but it's just that there's someone in the middle and they're slipping malware into every time they see this file go by on the network. Now I'm getting a malware version of it. Right? So in that case, I care about integrity. Now, another question you might have is, if you have confidentiality anyways, if everything's encrypted, the adversary can't really see what they're doing, right? So they can go in and they can modify things, but because they can't see it because of the first property, they can't kind of meaningfully change things. And so don't you get integrity for free once you have confidentiality, right? And that's a great question. And it's something that makes a lot of sense that you would get integrity for free if you have confidentiality. But if you take a cryptography course like 6110 at Concordia, you'll learn that that's not strictly true. Okay, there are protocols where you have confidentiality, but the adversary, even though they're manipulating encrypted data, ciphertexts, they're still able to meaningfully encrypt it in such a way that they can sort of predict what the results will be. Okay, and there's actually a lot of history of people breaking the cryptography, not in the latest version of TLS, but in earlier versions of TLS, using these kinds of attacks, where people thought confidentiality was enough, but it turns out that you need integrity and confidentiality separately as two different layers. Okay, so in cryptography, you'll learn Confidentiality corresponds to encryption. Integrity corresponds to something we call MACs, message authentication codes. And TLS is going to do both. So all your data is going to be encrypted and it's going to be MAC'd. And there are new types of encryption that do both at the same time. So a common kind of encryption you might see is something called AES GCM. And so we call it authenticated encryption because it does basically both of these at encryption time. But anyway, these are details that you don't need to know for this course, but I'll just mention them for your interest. All right, are we done? So we have confidentiality, we have integrity, right? Looks like we're done. But there's one property that sometimes we forget about that is absolutely critical, okay? It's necessary. If we don't have this property, then we're not going to have the other two properties, okay? Again, let's go back to the analogy of a tunnel. So we have a secure tunnel, and we know that this tunnel is unbreakable in terms of its confidentiality. It's unbreakable in terms of its integrity, okay? But here's a simple question. Alice, she sees that she's putting her data into a tunnel, right? How does she know where the tunnel ends? If the tunnel ends somewhere completely different than Concordia, the tunnel can be as secure as you want. It can be a bulletproof tunnel. There's no way to break it, right? But let's say the tunnel goes to the adversary instead. So the adversary is the other endpoint of the tunnel. Well, all you're doing is very, very securely delivering your data straight to the adversary. And then the adversary can do what they want with the data, okay? So it's pointless to have a secure tunnel and have all these strong properties around the tunnel if you don't have a guarantee of where the tunnel ends. You don't know. I know one endpoint of the tunnel because I'm there. I'm putting my data in it, right? But what if the tunnel ends before it leaves my computer, right? What if it goes somewhere completely different, all right? So where the tunnel ends, we call server authentication, okay? Basically, we're authenticating the server and we're saying, okay, I have a tunnel and it goes all the way end to end, all the way to this particular entity. And it turns out that that's a really hard problem to sort of specify. How do I know that the tunnel is actually ending at concordia.ca? It sounds like a problem that should be easy to solve. But what we'll see is that like probably half of our attack tree that we'll develop will be attacking this property because this property is really, really messy in terms of how it's implemented. Okay, so just visualizing the fact that if the tunnel ends at the adversary, right, then it's useless. You know, it doesn't matter if this has perfect confidentiality and integrity. You know, you need it to go all the way to the end. Okay, so now let's talk about our attack tree. Okay, so what I want to do for the attack tree is I want to consider one attack on HTTPS. So we're going to try and break one of these properties, okay? We should have an attack tree for all of them, but the property I'm going to focus on is just the first one, okay? Confidentiality. So my goal, the root of my attack tree, the first node in my attack tree, is I want to observe the traffic or the data that's being sent over the secure tunnel, over HTTPS, even if, I want to observe this, assuming I'm already in the middle. So in my attack tree, I'm not going to consider how I get in the middle. I'm just going to assume I'm already there, okay? So I'm in the middle of this connection. I'm seeing quote unquote ciphertexts go back and forth, encrypted data go back and forth, but I want to see the raw data itself. I want to see the unencrypted traffic itself, all right? So what are all the different ways that I might be able to achieve this goal? So we can build an attack tree like that. So the root node will be to observe traffic sent over HTTPS from a man in the middle position. And then now we got to start filling out this tree. So what are all the different ways of sort of doing this? Okay. And what I'm going to do is I'm going to sort of cluster them into three general approaches. Okay. So the first approach, what I'm going to do is I'm going to say, assume I can't break the tunnel. Assume that the tunnel is secure. It's confidential. Okay. Does that really mean that I can't infer what's being sent back and forth? Or is there something even from outside the tunnel, even though I'm looking at the encrypted data, I could still try and figure out what's kind of going on? Okay, so we're going to have a bunch of attacks that are related to that. So I'm not actually going to break the cryptography or the tunnel. I'm just going to see what I can do, even though I can't break the tunnel itself. The second types of attacks we'll look at, this we'll look at in a lot less detail. I'm sort of going to enumerate them for you, but I'm not, because they appeal to a lot of cryptography, and I don't assume that you've necessarily taken a cryptography course. I'm not going to go into the details of them, but I'm going to show you some general approaches of how do you kind of break into the tunnel. Okay, so that would be the second line of attack. And then the third line of attack is, notice, if you can get the tunnel pointed at you, right, then you don't have to break it at all, right? Then the tunnel just ends at you, and everything is being put into your lap. All the traffic is just putting directly into your lap, and so you can look at it, you can change it, you can do whatever you want. Okay, so this will be the third kind of approach. Okay, so we'll look at attacks here, then we'll look at attacks here, and then we'll look at attacks in the third case. So let's start from the top. Okay, so the sub-goal, or this branch of the tree, what our idea is, okay, we're external to the tunnel, so we're not breaking the tunnel, we're not inside the tunnel, we don't have the tunnel ending at us, so we're external, so I'll call that external observation. So we're standing outside the tunnel, we're seeing stuff go back and forth in the tunnel. And what my goal is to ideally, I would like to recover the data. What we'll see is it's not realistic to actually recover the data itself, okay? But what we could do is we could potentially recover some of the data. We could know a little bit about what's going on, even if we don't know all the details of what's going on. And then at the end, we can ask ourselves, of all the, we were able to get some details and not others. Does it even matter that we weren't able to get some of the details, or the details that we were able to get, is that enough really to break it? And so I'll show you some scenarios where it probably is enough, and then there's other scenarios where it doesn't apply. Okay. So for this sub goal only, we're going to assume that the HTTPS protocol is perfect. There's no problem. There's nothing. It works flawlessly. Okay. But are we still able to learn stuff even though it's working exactly as it's supposed to? Okay, so before we start asking this question, let's just think a bit about the web and kind of how it works, and a little level of detail. We won't go through all the details, but we'll introduce a few things. Okay, so let's say we have Alice here and she wants to go to concordia.ca. Okay, she wants to load the website that's the index page of concordia.ca. What does she do? What's the first thing she does? So she types in, concordia.ca in her browser. She presses the enter key. What happens? Okay, so the first thing is that she's going to drop a packet that basically says a request for the website, concordia.ca. But the network has to figure out, how do I get that packet to concordia.ca? And so the way the internet works is that things aren't routed based on names like concordia.ca, which is called the domain name. So servers don't know where domain names are in the world, so they don't know how to route packets to them. Instead, what they do is they use kind of like a phone number called an IP address. So this is IPv4. So there's a newer version that is sort of bigger and better called IPv6, but for simplicity, I'll just stick with notation for IPv4. And so this is the kind of thing that a router needs to know. If you give a router a packet with this destination, it can figure out how to get it to this server, assuming that this is the correct IP address for this server. Okay, so everything's hierarchical, and there's a whole thing about how networking works that we're not going to cover in this class. Okay, so the question I have is, okay, I want to go to concordia.ca, but I don't know the IP address. I just know concordia.ca. So somehow I have to figure this translation out. And so there's a system called DNS that does exactly that. So DNS has every domain name, and it has the corresponding IP address for that domain name. How does this information get into DNS? That's a great question. Okay, put a pin in that. We'll think about that later, but that's a great question. Roughly speaking, Concordia is going to put that information. So Concordia knows their IP addresses or what IP addresses they want. So they need a way of getting that into DNS. Is DNS like a single server? There's one DNS server in the world and everyone goes to it every time they need to do one of these translations? The answer is no, they're sort of distributed. And so the DNS server that Alice is using is probably a server that her ISP gave her. So like say she gets internet from Videotron, then Videotron is going to give her a DNS that belongs to Videotron that Videotron runs. You're always free to override that. Right. So if you want to use, I don't know, say Google's public DNS server, which is at 8.8.8.8, you're free to do that yourself. That's fine. And by the way, that can sometimes be advantageous. Sometimes when you get behind like captive portals and things where they want you to pay for the internet, sometimes the simple trick is they just turn off DNS so that you can type a URL in, but you can never find the IP address, so the internet doesn't work. But the internet is actually working. If you knew the IP address, you could just type it in and it would take you. By the way, you can do that. If you don't want to go to concordia.ca, you can just type in the IP address into your browser and go there, and it's exactly the same thing. And this IP address, by the way, I don't know if it was right when I made this slide, but IP addresses change over time, so it might not be Concordia's IP address anymore. Well, it probably still belongs to them, but they might not be serving their website at that IP address. But anyways, in theory, if you put this in the URL, you can go to the website. Okay, I'm going on tangents, so let me get back to the story here. So we have the IP address, then we dump the packet on, and it's going to route to Concordia. Okay, now where could the adversary be? So let's consider first that the adversary, we said the adversary is in the middle. We want to break HTTPS. The adversary is in the middle. Let's assume that they're in the middle between Alice and Alice's DNS. Okay. Our DNS queries, is there a secure tunnel between Alice and DNS? Okay, is this question of give me the IP address of Concordia, and the answer, is that going over a secure tunnel or not? All right, so you might not know the answer to that, but just think of a guess. Would you guess yes or would you guess no? Right, so if you guess no, then you're right, mostly. So generally speaking, you're not going to use a secure tunnel between you and DNS. Now, there's lots of attempts to change that. Okay, we understand that this is a vulnerability, and there's new protocols like DNS over TLS. I forget what it's called. And then there's another thing that says, forget about confidentiality, but let's at least make sure that these things are signed so that you know that. Notice the adversary could just, if they're in the middle, they can change this IP address to a server that they control. Then you put into your browser concordia.ca, it takes you to some server, but it takes you directly to the adversary. Okay, now HTTPS, when we have that server authentication property, it should continue to work even if the adversary is able to do this. Okay, these are details that we'll go through later. But anyways, you could have these records digitally signed. That's called DNSSEC. So there's different ways of trying to secure this link. But generally, in terms of what's rolled out in practice today, like right now, I'm connected to DNS. Do I have a secure connection? And the answer is no, I don't. Okay, so the adversary can control this. They can read it. And so they immediately know what domain I'm going to. Even if I'm going to use HTTPS, if the adversary is here, they know I'm going to concordia.ca. Now, let's consider the adversary that's in the middle of the path here. Again, they're outside of the tunnel, so they can't break the tunnel. And let's just focus on this question of the domain name. Okay. Does the adversary know, they see this traffic going back and forth. Let's say they're close to Alice, so they know it's coming from Alice. Do they know it's going to concordia.ca as opposed to any other website? Okay. In other words, is the destination, Concordia, is that inside the tunnel or is it outside the tunnel? All right. And so, again, you can think about the answer. And the answer, it's probably obvious once you think about it, but not obvious if you just had to guess at first glance. You probably think, well, it should be inside the tunnel, right? You should put everything inside the tunnel. The problem is if it's in the tunnel, then the packet can't find its way to concordia.ca because nobody knows where it's going to go. Okay, it's in the tunnel. So you have to put the destination information outside of the tunnel. Okay, so if you have a packet that's encrypted, you have to leave the destination not encrypted. Otherwise, the packet's not going to find its way to the correct place. There's no way to route it. Okay. Now, what is going on the outside of it isn't the domain necessarily concordia.ca. It will be the IP address. However, you can also run DNS backwards. So the adversary will see this IP address, and then they can reverse DNS it and figure out that that's concordia.ca. Okay. So the adversary doesn't have to be between Alice and the DNS server to learn which domain name or the domain name of where she's going. The adversary can just be on the wire, and they'll see the domain anyways. Okay, so basically anyone anywhere is always going to learn at least the domain that you're going to. Okay, and this can be problematic in and of itself. Okay, so there are domains, there are situations where somebody might be wanting to surveil your network communication, and the fact that you're going to a particular website is incriminating. Okay, think of maybe a country where there's a lot of censorship of the internet, and you're going to a domain that's very, very clearly affiliated with some politics that are opposed to the government that's in power. Okay, so even though HTTPS is protecting you, it's working flawlessly. What it's not doing is it's not hiding the domain that you're visiting. It's just hiding the actual content of what's happening. Okay, a mental model for thinking of this, by the way, is you can think of kind of like an envelope. Like say I send you a letter, I put the letter in the envelope, I seal the envelope, so it's kind of like a secret, but I still have to write your address on, otherwise the letter's not going to find its way to you if I just drop it in a mailbox. Okay, so sometimes if I might say inside the tunnel or outside the tunnel or inside the envelope, outside the envelope, but what I mean is basically, is it part of the encrypted payload is the term that we use, or is it part of the sort of meta information that's not encrypted? Okay, so already HTTPS, even though it works perfectly, it's not doing everything that we would want it to necessarily, right? We might want to hide the domain names that we're visiting, and it's just not giving us that property. All right, now it gets slightly worse. So let's take an example again. So here's Alice, and Alice is reading Wikipedia, and she's looking at her favorite soccer football team, which is CF Montreal, of course. And so she's reading the Wikipedia article for CF Montreal. All right. Now, first off, ask the question, okay, if the adversary's in the middle of this communication, what do they know? Well, they know that Alice is going to nenglish.wikipedia.org. Okay, so they know that. But they don't know, for example, that she's looking at CF Montreal as opposed to looking at some other article. Okay, this is the one article that she's looking at. Now, the way modern websites work, like a website like that, is so you'll do your DNS lookup, you'll get the IP address for Wikipedia, you'll say, give me the Wikipedia article. It's located at wiki/CF_Montreal. This, by the way, is encrypted. So this is inside of the tunnel. It's what we call the path. So it's the path to the resource that you want. And the resource itself is an HTML web page. And this is the response that you get back. So you say, I want to get this. Wikipedia says, okay, I'll go to this location. The default file that sits there, if you don't specify it, is going to be index.html. And so I'm going to respond with that. So now I have index.html on my computer, or Alice does. So she's happy. The lock here just indicates that this is all happening over HTTPS. Okay. Now, if I look at this website just visually, I see a bunch of stuff. Like I see a bunch of pictures, right? There's logos, there's pictures. There's going to be some like scripts that are running on this website. There's the different fonts that are used. There's a bunch of stuff inside of this website. So does that all come down in index.html? Does HTML just like, it's one file and it's a complete archive of everything that you see on the website? And so the answer is no, that's not how the web works. What happens is it will give you a link in the HTML to all the other resources but you need to go out and load those as well. Okay, so if there's a logo that's an image, a PNG image file, then you're going to have to go, and it might be at a different domain. It might not be at Wikipedia. It could be at upload.wikipedia.org, and you'll go to that domain, and you'll get the logo back from that domain. Again, hopefully also over a secure channel. A question you can store in the back of your mind is, well, what happens if I load this first page over a secure channel, but then I start loading resources that are not over secure channels? That's a great question that we'll tackle a little bit later. But for now, we'll just assume that everything's secure. Okay. And what I'm going to do is I'm going to assume that the adversary is in the middle for all of these. Okay. So they can not just see you load the original page, they see you load all the different resources as well. Okay, so if we want to enumerate what all the different resources look like, first off, I'll just note that you can do that in your browser. So basically any browser such as Safari is going to have that functionality that lets you look at it. So let's just see this. So I'll go to the Wikipedia page for... Now, you might have to enable, like, for example, I'm using Safari, so you might have to enable what's called developer tools. It's a setting. But then there's a web inspector. And so you can see here under network, I have all selected here. You can see that all the resources that were loaded, okay? And basically, it shows them to you sort of in order that you get them. Let me do this instead. You can sort of see a timeline here of kind of like when you got resources. And, you know, sometimes it takes a while because you have to load a resource that references another resource and then references another resource. But anyways, the whole website came down in about 400 milliseconds. It wasn't that case. When I was growing up and using the internet, you would go to a website and the text would load first and then images would sort of slowly come in. You know, and so it sort of reinforced the idea that you're just not downloading. This whole website isn't being loaded all at once. It's coming down piece by piece. Okay, now I'll go back to basically just in the slide. It's essentially what we were looking at before. And let's think about all the different stuff that's coming down. So we have a bunch of files. For example, here's a PNG. It's an image file. There's the name of the file itself. Okay, so there's a file name. There's the place that I'm getting it from. So the domain I'm getting it from might not be the domain that I'm on, right? So all the images could be hosted on a completely different domain. Here, Wikipedia is very clean. Everything is clearly from Wikipedia itself. But most websites, they're going to weave together content from like completely independent domains, right? So you'll be on Wikipedia, but you'll be getting a script from Google, and you're going to get another script from DoubleClick and something from Facebook, and you're getting a bunch of stuff from all over the place. Okay, but anyways, there's where we're loading it from. There's the fact of whether it comes over a secure channel or not, which is indicated by the lock. There's the kind of file it is, which is called PNG. We'll skip this column for now, and then there's the size of it. How many seconds into your connection before you received it, or maybe started receiving it. I'm not sure exactly what this measures. But yeah, these are all different things. Okay. Now let's think about the adversary. Okay. So the adversary's in the middle, and they're seeing you load all of these resources, but because there's a lock on all of them, they're being loaded over a secure tunnel, right? Okay. So what does the adversary know and what does the adversary not know? Let's start with the file name of the image. If I go to this domain and ask for this image, does the adversary get to see the image itself? Do they see what that picture looks like? So the answer is no. So the secure tunnel is going to protect that. So they're not going to see the picture itself. Are they going to see the name of the picture? Even if they don't see the picture itself, do they see the file name itself? Again, the answer is no. Okay, so they don't see that either. So they don't, that's all in the tunnel, or it's in the envelope. Okay, but the fact that I'm loading it from, say, upload.wikipedia.org, they do get to see that. Okay, because I have to send that request to this server, and I can only do that by writing the IP address of this server on my packet. on the outside of my packet. Okay, otherwise my request isn't going to find its way to this server. All right, so then there's the file type itself. So is it a PNG? Is it JavaScript? What kind of thing am I downloading? Does the person in the middle, the adversary in the middle, do they see this? And the answer is no. It's kind of goes along hand in hand with this, which is they don't see the image, they don't see the file name of the image, they don't even know the extension of the file, so they have no idea what it is. So they know some data is coming down, a blob of data, but they don't know whether it's HTML or an image or JavaScript or PHP or whatever. Okay, so yeah, so this is also protected. Now the last thing is, what about the size of the file? Is the size of the file going to be protected or not? So I want to pause here and I want you to think about it. What do you think? Okay, so the answer is, well, the reason we have the secure tunnel is we're sort of encrypting data. So a different way of asking the same question is, let's say I have some data and I encrypt it. Is the encrypted form of that data bigger or smaller or the same size as the data itself? So when I encrypt it, does it change the size of the data or does it not change the size? So the answer is it doesn't change the size. Okay, there's some slight variant. It might change it slightly, like to the nearest byte if you're using something called stream cipher, or it might change it to the nearest couple bytes if you're using something called a block cipher. But as far as you know, files that are in like kind of the kilobyte range are, it doesn't change the size. Okay, so encrypted data is the same size as plain text data. Okay, it can't be smaller. If it were smaller, then you would have trouble decrypting. I won't go through the argument as to why that is the case. It could be bigger. They could arbitrarily, you could pad out your file so that all encrypted data is exactly the same file, but then that's going to be really inefficient, right? Then you'll be always downloading things that are bigger than you need to download. So the web wants to be very efficient, so they're going to send the minimum number of ciphertext bits as possible, or encrypted data as possible, and the minimum that you can send is something that's the same size as the original data itself. Okay, so if the adversary is on the outside of the tunnel looking at this, they are going to be able to see or approximate the size of every resource that's being loaded. Okay, so in summary, they don't know the file name. They do know the server that you're getting it from. They don't know the extension or what kind of data it is. They don't see the data, the file itself, but they do see the size of the file. Okay, now let's assume that we're going to the CF Montreal Wikipedia page. And let's assume that when I look at this website, there's 87 resources. Okay, so there's, if I count up how many of these things we call them resources, there's exactly 87 of them. Okay, and I have to load them all, at least the first time I visit the website. Okay, the first time I visit the website, I have to load each of those once. So I have to create 87 outbound requests and ask for each resource one by one. And the adversary sees that. Okay, they don't know what I'm requesting, but they see that I request, say, exactly 87 of them. And they see the size of each resource. Okay, so they see, oh, you know, now Alice is requesting something that's about 20 kilobytes from Wikipedia, n.wikipedia.org. Oh, now they're requesting something that's 1.27 kilobytes from upload.wikipedia.org. Then they're going to request something that's 2.91. You know, and so they're seeing all of this data go back and forth, and roughly they see it in the same order, because this website's going to kind of load, you know, from top to bottom according to which resources, the order in which they're specified in the original HTML document. They're going to try and load in the same order. All of this stuff, there's a lot of fuzz, right? So if I've been on the website before, I'm maybe not loading all of the resources because I already have the logo for Wikipedia itself. I just need like all the flags of all the players on the team or whatever. Encryption maybe very, very slightly changes the size, but basically it's the same size. And if I ask for 10 things at once, or my browser prepares to ask for 10 things at once, they might come out in a slightly different order than my browser was preparing them. But in general, there's going to be, despite a bit of noise, there's a lot of signal in that as well compared to the noise. Okay, so if I took this information and asked myself, man, how many pages on Wikipedia are there that have exactly 87 resources, and the size of these 87 resources are exactly this kilobyte, this kilobyte, this kilobyte, this kilobyte. And generally when people download this page, you sort of see the big thing first, then a smaller thing, then a bigger thing, and it has this sort of pattern. Okay. How many pages on Wikipedia have that sort of exact pattern? And the answer is probably none, right? Probably one, right? The CF Montreal website is probably the only page on Wikipedia that has exactly the same number of resources that it has that are roughly the size of the resources that they are, that you would generally, sort of download in a particular order. Okay, so that pattern that's created of basically I ask for this resource and I ask for this resource, and here's the sizes of all the resources, that creates a kind of fingerprint. Okay, and because we can do things like fingerprint matching, we can use machine learning and things like that, we can tolerate all this noise. Okay, so just the fact that maybe it's cached, maybe it's not, there's enough like uniqueness that when I look at a specific traffic pattern going to Wikipedia, even though there's a bit of noise in these conditions, I can more or less guess very accurately which website, which Wikipedia article the user is looking at just by looking at the fingerprints of this data itself. Okay, so researchers did this. So this is one of I think the first paper that sort of did this in detail. And so they went to a bunch of different websites. You can see lots of different services, and the bottom line is it's about 90% accurate. Okay, now maybe you can make it a little more accurate using more modern techniques or things like that, but essentially just by looking at sort of the traffic patterns that go back and forth, you can figure out not just that someone's going to Wikipedia, but exactly which Wikipedia page they're looking at. And you can do this despite the fact that it's HTTPS protected. Okay, there's nothing broken about HTTPS. It's doing exactly what it promised to do. Now, you might think that's really scary. I hope you do, actually. Okay, so I hope that scares you because HTTPS is doing a lot less than maybe what you think it's doing. Okay, but there is some good news. The good news is that this fingerprinting only works if I can go to the website first. Like I go to the CF Montreal, I see what the pattern is, and then now that I have the pattern, then I try and match it to traffic. Okay, that works because I can visit CF Montreal, and when I look at the CF Montreal page, and when you ask for it and end up looking at it, they're exactly the same. Okay, therefore they will have the same fingerprint. All right, so this works for any website that's public. So I go to a website, it's public. You can go to the website, I can go to the website, we both see the same thing. But where the fingerprinting attack breaks down is, let's say you go to some website where only you can see stuff. So for example, let's say I log into Gmail and I look at my inbox. That's my inbox. You can log into Gmail and look at your inbox, but your inbox is going to look different than mine. So you could fingerprint your inbox, but when I go to Gmail, right, and I look at my inbox, it's not going to match your fingerprint because my inbox is completely different. Okay, so sometimes we call that sometimes it's sort of confusingly called the dark web because you can't see it, but the dark web usually means something different related to some anonymity, anti-surveillance technology called Tor, which we're going to visit. Actually, I guess we have already, you've already seen that. But anyways, so fingerprinting, it only works on public websites. So you can't use it to, for example, if you log into Gmail and you start looking at your email, I have no idea what your emails say. Okay, I can't use this attack. But if you go to a public website like Wikipedia, I can figure out which Wikipedia article you're looking at. All right, so this is a kind of partial victory for the adversary. All right, now let's go back to something that I hinted at, but we didn't fully discuss, which said, okay, let's assume that some of these resources, when we go and load a website, Some of them are coming over HTTP, not over HTTPS. So I go to an HTTPS website. Let me just back up a slide and just show you this again. So assume that the first thing I ask for is indeed over HTTPS, but then it says, oh, go load this PNG from this server. But when I go and load that file, it's not over HTTPS. It's just over HTTP. Okay. What should the browser do? Should it consider that this website is secure? Should it give me the indicator that says that it's a secure website, even though some of the resources were loaded, or should it not? Okay, so before we answer that question, now I say, should the lock be displayed? I should update this slide. This was the old visual where when you were on HTTPS, you would see a lock. But the point is, like, should you display the website as if it were HTTPS or not? Okay. All right, so we have two kinds of content. We have content that we consider passive. So these are resources that you might load, and they basically they don't compute code. They're not scripts. They're not capable of doing computation. Okay, so that's what we call it. What we call passive. Okay, so things like images, audio files, videos, these types of things. Okay, then we have active content. Okay, the biggest one is the script attribute, which basically can be JavaScript. Okay, so it's script, it's running, and that script can do more or less anything. Okay, and generally we're more concerned with, for example, let's say that you're either going to get a bad image on the page because the adversary changed it, or you're going to get a bad script running on your page because the adversary changed it. Which of the two do you care more about? Well, if you get a bad script running on your page, it can basically rewrite the entire page. Okay, so it could, including all the images, right? If the adversary is able to tweak an image, well, they can change that exact image so it will show up differently on the page, but the rest of the website would be intact. Okay, so we care a lot more about making sure, for example, bad scripts don't get loaded on pages than bad images. If you want to understand what does it mean to have a bad script running on a page, wait a couple lectures and we're going to eventually talk about something called policies, and we'll look at something called the same origin policy that has to do with this. Okay, so should we display the lock or not? So this is what Firefox used to do. Again, this slide isn't completely up to date because we're going back to this lock terminology, but I can show you actually what Safari does now because there's a great website that lets you try out different combinations of things. But essentially what all browsers will do is they will try to distinguish between active and passive content. Okay. And what they'll also do is they'll update the lock basically to say, yes, there's some passive stuff that's coming over HTTPS, or there's active stuff coming over HTTPS. Okay. And the other thing that browsers will do is sometimes they'll just step in and just block it. So you'll try to load a resource, and because let's say you try and load JavaScript, and the JavaScript is coming over HTTP instead of HTTPS, then what the browser will do is it'll just drop that JavaScript. It'll just say, no, I'm not accepting that. I'm not going to run that. I'm not going to display it to the user, right? I'm just going to drop it. Okay, so it just ignores it. And does that break the website? It very well could. Okay, so maybe the website doesn't work because there's this JavaScript that's missing because your browser decided not to load it. Okay, now this is newer behavior, so browsers didn't always work this way. But now we realize that getting bad JavaScript is so dangerous that it's best to just drop it completely. And if that breaks the website, then that breaks the website. So be it. Okay, where the browser is going to protect the user. Okay, now if it drops it, then there's no longer mixed content. Mixed content, by the way, that's the terminology for when you're mixing HTTP and HTTPS. Okay, so browsers will basically look at the content. They'll make some decisions about, do we just drop it, or do we allow it to be displayed to the user, but we want to indicate to the user that it was mixed right? And so we're going to, instead of showing, say, a lock, we're going to show like a lock with a warning sign or a lock with a slash through it or something like that, okay? So there's different indicators depending on the different combinations, and different browsers are going to do it different ways. Okay, so let's take a look at it. So there's a great website called badssl.com, and it has lots and lots of different examples of kind of misconfigured websites that give you all sorts of different indications, and you can see different things that happen. Okay, so I'm just going to fire it up. We'll take a look at it, and we'll do a couple of these. Oops. And I'll keep this open in the bottom because sometimes we'll see stuff. Okay, so yeah, so this website's great. It has a bunch of different things that we haven't really talked about related to like the underlying cryptography and things like that. But in terms of mixed content, we'll look at this here. Okay, so first off, they have an example like this. Okay, so this is called mixscript.badssl.com. And what it tried to do is it tried to load a JavaScript that did not come over HTTP. Okay, now if we go here, we don't see it. Okay, so I'm not seeing a JavaScript that came down. I would expect to see the JavaScript without the lock. And the answer is, the reason it's not showing up here is because this is an example where Safari stepped in and said, what you're doing is so bad that I'm just going to block it. And so what it did is it actually triggered a warning, which you can see at the bottom of my screen. And it says, when I downloaded this website, it requested that I grab this .javascript file over HTTP. Okay, the content was blocked. It must be served over HTTPS. Okay, so what I'm doing is I'm just running this website without it. Now, because that got dropped and everything else was loaded over HTTPS, the browser is displaying this as if it's an HTTPS site. Okay, so now in the new terminology, it doesn't say not secure here, right? It is secure. It's secure because that was dropped. Okay, if it was an image or something like that, okay, then we would see something different. So let me see if I can show you what this type of thing would look like. Let me just go back. They say demos never work because weird things happen. Like, for example, my internet's not working for whatever reason. Okay, here we go. Okay, so I'm going to go back to mixed content. And I'm going to try a few of these other ones. So this one, I can't remember what all of them do. I think this one maybe just has an image or something that comes down that's mixed. Okay, so finally it came down. Okay, so in this case, again, my browser intervened. So what it said is I tried to fetch image.jpg, okay, and it came over HTTP. But what it noticed is that actually this website does have that image, and that image can be served over HTTPS, okay? So my browser, again, it kind of outsmarted the website and said, oh, before I block it or try and show some other indicator to the user, what I'm going to do is I'm just going to check and see maybe I can get it over HTTPS. Maybe the person who coded up the website, they just forgot to put the S in, or it was like a silly mistake like that. And so they automatically went and tried to grab the file over HTTPS. They noticed that, hey, it is there. It's served over HTTPS. And so they were able to get it. Okay. And because they were able to get it, then they were able to say every resource is loaded securely. Therefore, I'm going to consider this a secure load. Okay. All right, so now Safari is so smart that it might, we might have trouble trying to get it to do something. So here you can see that this has to do with favicons, are kind of like the little logos that appear beside URLs. I guess the reason the website is separating them out is because maybe they're handled slightly different. So here it is complaining about it, and in this case what it did is, again, it just blocked it. So there's no mixed content here because everything's just getting blocked. And this is an example where this is slightly different, but you might be on a website and you submit something, and the submit button, is this going to go over HTTPS? So this website's on HTTPS. If I hit the submit button, what happens? And the answer is that, well, it depends on whoever coded the website. Did they code the submit button to post this data over HTTPS, or did they code it up to submit over HTTP? In this case, because this is a bad website, they did it over HTTP. So let's see what happens. So here I get a browser warning. You might have seen this before, and now you know the answer to why you're seeing it. It basically just says that the submit button is going to send this data over HTTP. The kinds of things that you might type into something like this and press submit would be something like a password. And so it's really dangerous if you're going to put your password over HTTP. And so that's why your browser steps in and it warns you. So I can send it or not send it. And if I send it, then it got sent, and there were some other errors that were happening on this website. Okay, so I was hoping to be able to show you an example of mixed content, like something that's in between. This is fully HTTPS or this is completely not HTTPS. But it seems that maybe Safari, even in the recent months, have made changes to this. And so now it just seems like they're blocking everything, or they're so smart that they're auto-upgrading things. So I don't have an example to show you, unfortunately, of what mixed content looks like. But you can see that browsers are very, they're proactive in going in and trying to stop resources, any resource, even if it's just an image, from loading on a page, if it's not served over HTTPS. Okay, now another thing that we'll add to our attack tree that's unrelated, but it's related to this idea of I can't break into the tunnel, okay, is, well, what if I just store this information? I can't break into the tunnel today, but maybe I can eventually, right? In a couple of years, I'll be able to break into the tunnel. I'll have a quantum computer, whatever the answer is. By the way, I say that sort of offhanded. Let me back up and actually say a little bit about that. So you probably have heard that there's new types of computing, sort of a new paradigm for computing called quantum computing. You maybe have heard that it breaks a lot of cryptography. What does that mean for HTTPS? So quantum computing breaks some of the cryptography that's used in HTTPS, but not other parts that are used. So it breaks some of it, but not all of it. And there's also different ways of doing HTTPS. There's sort of like two modes that you can use. One mode has a sort of enhanced security property called forward secrecy. TLS 1.3, which is the current version of TLS, everything in it is forward secret. Okay, but if you go back a couple generations, then you'll find some algorithms that are not forward secret. Okay, and so the rough story is that if you're using something that's forward secret, and the attacker isn't in the middle with a quantum computer. So maybe we'll start there. Let's say the attacker has a quantum computer and they're in the middle of your communication. You have no security. HTTPS does not work. Okay, if the attacker is there today with a classic computer, and all they're doing is they're writing down everything that they see. And then 5 years from now, they're going to take a quantum computer. They're going to take their log of everything they saw from today, and they're going to run that through the quantum computer. If they have forward secrecy, you're not going to be able to break it. Okay, if you use this older key transport type of mechanism, then they would be able to break it. But that's been sort of taken out of TLS now. And so you need the browser to be up to date and the web server also to be up to date. But if both of those things are true, then quantum computing is not a threat in the sense of I just record everything. Okay. Now there might be other ways of breaking cryptography, right? So it might turn out that, I don't know, the block ciphers that we use have some underlying weakness that we don't know about. And in 10 years, we're going to realize that, AES is broken, right? And I can look at ciphertext and I can figure out what the plain text is. I can unencrypt it, even though I don't have the key. Or I can look at a bunch of encrypted data and I could figure out what the key is, whatever the type of break is, okay? And so some people are kind of banking on that. So it's alleged, for example, the US government, they built this big, what appears to be a big data center in Utah. Again, we don't know, it's top secret, it's classified, but there's satellite imagery and things like that. And people sort of, who know about like building these types of things, they sort of looked at it and speculated what it's for. And it seems to be like a storage facility for like storing as much data as possible. And then the speculation is, well, this is probably an NSA facility. NSA are interested in trying to break secure communication for foreigners, so non-Americans. And so what they could do is they could be collecting all sorts of information that they can't break today, but they're hoping that maybe in the future there'll be techniques that they can use to break it. And because they have records of it and they've recorded it all today, then they'll have a shot at breaking it. And even if it takes 30 years to break it, there is some data that's still relevant 30 years down the line. Okay, like especially at like government, nation states, strategies, diplomacy, that type of stuff. There could be data in there that's still useful. Okay, so another attack against HTTPS is to just sort of capture it today and try and break it in the future. Okay, and then just mentioning this property forward secrecy or perfect forward secrecy. So this is at a high level, without going into the whole crypto lesson, this is something you want. Okay, it enhances the security. It protects against certain kinds of attacks. In particular, communications are protected by cryptographic keys. And so if that key ever leaks, if it leaks after the communication was done, then the attacker, even with that key, can't decrypt past communications. So that's why it's called forward secrecy. They can decrypt future communications that are still using that key, but it protects past communications. All right, so let's throw this into an attack tree. So we have our root node again, recover partial data from external observation. So we can do a bunch of things. So first off, there is a bunch of stuff that doesn't go over HTTPS. For example, I know the domain that's being visited because it's not encrypted. It's in the header of the packet and it's unencrypted. If I'm between the user and their DNS, and DNS is not secure, or it's not private, then I also know the domain being visited just by seeing what domain they're asking for. Right, so they have to ask for the IP address of Wikipedia before they go and visit Wikipedia, okay? Unless if it's cached. So in any case, I get the domain that's being visited. And if there's any HTTP content that's getting mixed in, right, I can see that content as well. And this is something I didn't say at the time, but I'll just mention it now, is even if your browser blocks it, it still downloaded it. So the content still came over HTTP. The adversary in the middle was able to look at it. Your browser decided at the last minute to block it and not to display it in the context of the website that it's displaying to you. But that content still went by and the adversary was able to look at it. And if whatever this content is tells the adversary or gives the adversary hints about what the other content that is encrypted is, then that can leak information as well. Okay. Another thing is if you do see JavaScript that doesn't go over HTTP, this is a threat, not an attack anymore because it's fixed. But what you could have done is you could have just replaced that JavaScript and you could get your own script running. And then once you get a JavaScript running on a website, you can just basically walk around everything else that's being displayed on the website and phone it home to a server. Okay, so this branch no longer works, but this branch did work at some point in the past until browsers started blocking active content. Okay, so there was a period of time where they would allow active content, but they would just give a funny lock logo. But now they just completely block it. The next thing I could do is I could fingerprint public websites. So I could look at how many resources are loaded, what are their sizes, the sort of relative order. Now I have a rough fingerprint of what it looks like to visit that particular website. And now when I see you and your encrypted data, I compare that to all the public websites I fingerprinted, and I pick the one that's closest to it, and I guess that that's what you're looking at, and I'll probably be right 90% of the time. Okay, and then I can always store it and try and break it later. This is more of a nation state attack, not really something that an individual would do. Okay, so this is one sort of aspect, or one sort of sub tree within our overall attack tree. And with that said, what we'll do is we're going to move on to the second part of the attack tree, which is we're going to try and break into the tunnel. Instead of just standing outside of the tunnel, we're actually going to try and break the protocol or break the cryptography somehow and try and get ourselves into the tunnel. Okay, what do we mean by break into the tunnel? So what we mean is we're going to break or somehow subvert the cryptography that's being used. Okay, so cryptography is the thing that makes the tunnel a tunnel. It's not literally a tunnel. It's not a physical thing, right? It's cryptography itself. And because this isn't a crypto course, I don't want to go into a lot of detail here. But if you know the basics of cryptography, you know that cryptography establishes security properties based on someone having a key, a secret key. And you can set up, for example, a secure tunnel. It says that there's some keys that are being used. The sender knows the key. The recipient knows the key. And if the adversary is able to get that key, right, then they get into the tunnel. So the tunnel is basically as strong as the key. Okay, if you break the key, then you get to break into the tunnel. There might be other ways of breaking the tunnel besides getting the key. But let's split those two out. Okay. So strategy one is somehow we just get these keys that are being used. Then we're able to break into the tunnel. The second is we find some weakness or some problem with the protocol, that we don't require the key itself. So both of these are possible attacks that we can include in our tree, and we can consider different flavors of these two basic attacks. Okay, so let's say, so we can either steal the key or we can break the protocol or the implementation. That's another important point. So sometimes, a protocol is sort of the math that's worked out by the cryptographers. They write it down, but then when you go to implement it, then it turns out that there's something wrong with the implementation. Maybe there's something in the protocol that's not fully specified. So when you implement it, things get changed a little bit. Sometimes there's just mistakes that are made, simple CME mistakes, so they don't follow the protocol precisely. Sometimes the protocol is underspecified. There's different reasons why the implementation might be the problem. Okay, so one line of attack is called side channel analysis. This only applies to very old versions of HTTPS, old versions of TLS, I should say. And the crypto details I won't go through. Okay, so they have to do with an encryption algorithm that's used that's called RSA. It's one of the very first encryption algorithms. You might recognize the name. And RSA encryption is not even in TLS 1.3 anymore. You might see signatures, but not encryption. And there was, there's this part of RSA where you need to pad out messages. And there was a problem with how exactly you did this padding. And basically what it would do is it would leak a little tiny bit of information about the plain text. if you could tell basically whether, how much padding was introduced, and the way you would measure this is with time. Okay, so you would need to have like a very sensitive clock. You would have to be close to the server. Say you're trying to break the server's key or the client's key. But in this case, I believe it only applied to the server. And you would be very close to the server, and you would basically, send it data, and then you would sit back, wait for it to decrypt and respond accordingly. And it could respond in different ways. It might say, oh, there was an error in what you sent, right? Like there's this padding bit that wasn't, or sorry, it wouldn't say that. It would just say, oh, there's an error, right? And so, send it again. And then based on different types of errors that could occur for different reasons, and the fact that you would realize certain errors quicker, then you might get really far down decrypting it and realize there's an error right at the end, or there might be an error in one of the very first steps that you do. Then you return the error message a lot quicker. Based on those timing differences, you could start pulling out bits of what was encrypted, and eventually you could decrypt the whole thing. Okay, so you can take a crypto course. You can learn about these kinds of attacks. They're really cool, learning how they work. But the main idea here is that you're using time. Okay, so the fact that when an algorithm fails, if it fails early or fails late, is a measurable difference in time. This is something that a protocol is not going to tell you, a specification of a protocol. It's just going to tell you that if you see this, you should fail, but it's not going to be like, oh, you should always fail at the same time so that, somebody who's watching you fail can't figure out why you're failing, right? So today, in TLS, depending on the implementation, but if you use an implementation like OpenSSL, so that's the most common implementation. We'll talk about it in a second. If you use OpenSSL, every single crypto sort of thing that you do, operation, takes the exact same amount of time. So if it's going to throw an error, it will wait, and it will throw the error at the very end. And so basically everything, and there's a bunch of other differences as well too, where you can measure different things, and depending on the time, you can try and leak some of the information. Okay, so every crypto operation takes the exact same amount of time, and people have gone through every single algorithm in OpenSSL and really made sure that this is the case for every algorithm. Okay, now this idea, the higher level concept, is we call it side channel analysis. Side channel meaning that you're not attacking the protocol the way that the person who wrote the protocol down was expecting you to, right? They wrote the protocol down. They sort of knew ways that you might attack it, but now you're kind of going around the side, and you're using things like time that aren't specified in the protocol itself. And so it turns out that side channel analysis is a pretty powerful category of attack. And it shows up across a whole bunch of different domains. So it's showing up here for HTTPS in terms of time, but there's other sort of variants of it. So I thought just for interest, I would tell you some of the other variants. So a lot of these are sort of older examples that have now been fixed, but they give you the idea of how these sort of attacks, where they came from. So other things that you could measure beyond time, you could pay very close attention to how much power something is consuming. So imagine that, for example, there's an ATM, and for whatever reason, you're able to unplug the ATM, plug it into a very sensitive meter, voltmeter, watt power, consumption meter, and then plug that into the wall. So the ATM continues to work, but you're able to measure the consumption. Then what might happen is someone might type in their PIN. Now, every time you, say, press a button, like you press the 1 or the 2 or the 3, right, it might draw a little bit of power, but the exact shape or the fingerprint of what that power draw looks like might vary ever so slightly between pressing the button 1 versus pressing the button 2. Okay, and if you're sensitive enough, you might be able to actually distinguish those two just by looking at the power, right? So what you could do is you could sort of sit back, and when someone's typing their PIN in, what you could do is you could look at the power waves, and then you could read their PIN out, and then that would you still have to steal the card to complete an attack, but you would have the pin, which is usually the harder part, and then you could try and get the card as well. Okay. Very similar electromagnetic interference. So it's sort of like the noise that things give off on like a radio spectrum. There was another example, sort of like an ATM, but it was for voting. So there were these voting machines, same thing. They have buttons and you press the button. And every time you would press a button, it would give off a bit of electromagnetic interference. And so what would happen is someone could stand outside of the polling place. So they're not even in the same room. They have a very sensitive radio. It's tuned to a bunch of different frequencies according to each button on this voting machine. And then every time someone presses one of these buttons, you could basically read out their vote standing outside of the polling place. So this was an actual attack that happened on one particular voting machine. Another story I remember is when I was a PhD student, a cryptographer came. His name's Adi Shamir. He's actually the S in RSA. So you see RSA on the slide. So the S in RSA. He came to my university and gave a talk. And he said, I was sitting in my office and I was working, and I had one of these like older desktop computers. And if you've used them, you know that they're like really noisy. And they're always making these like weird clicking sounds. And that does correspond to something that's going on in the computer, right? It's not just random noise, right? And usually if you work the computer a little harder, like you ask it to do something that's intensive, then it gets noisier and noisier, right? And so he thought, man, I wonder if I could break encryption just by listening to the computer. So for example, I'll ask it to do an RSA encryption, and it has to pull the key bits in. And depending on what the value of the key is, it's going to do this operation as opposed to this operation. And the difference between those two, you might actually be able to hear, not as a human, but as a very sensitive microphone that's fed into some sort of machine learning algorithm or something complicated to analyze it. Okay, and so he tried it, and indeed it worked. So he was able to read keys out just based on the weird, like, kind of clicking sound that was the computer was making. Another type of side channel analysis. Most phones have a very sensitive gyroscope. What's a gyroscope? So gyroscope tells you sort of if you're leaning to the left or leaning to the right. Basically, what's your orientation relative to Earth. And so phones have very sensitive ones. The reason that they have them is so that if you turn your phone to the side, right, then the whole phone goes from portrait mode into landscape mode, right? You're taking a picture, it rotates around it. And then there's other applications too, like you might have seen some augmented reality where you sort of hold your phone up, or maybe on Google Maps or something like that, you can sort of point your phone in a direction and it will show you on the map which direction that you're pointing. So all of this is possible because of a gyroscope. Now, the gyroscope doesn't need to be super accurate, but it turns out it's just easier to put a very accurate gyroscope in. And if your software is able to read the value that the gyroscope is producing at all times, it can do things like, for example, when you type in a password or a PIN, because you're slightly vibrating the phone as you type it in, it's going to jitter or shake the gyroscope. And you're going to be able to measure that by looking at what the gyroscope is producing. And if you press a button, let's say you're typing in a PIN and the number 5 is very close to the center of the phone, and because you're kind of gripping it with both hands, it might not produce a lot of jitter when you press the number 5. But the number 9, that's way down at the bottom. It's in the corner of the phone, and so when you tap the number 9, it's going to jitter a lot. And so again, you can sit back and you can watch all this jittering, and you can try and figure out what people's pins are. Usually, it requires a lot of training, so you need to see a bunch of examples where you know what the pin is first, and then you can start guessing in the future. Reflections are another thing. So there's all sorts of technology for, trying to have cameras that say I'm looking at my computer. I wear eyeglasses, And so if you see the reflection of my computer monitor in my glasses because you're on the other side of me, you can't see the monitor itself. It's facing me. You're past the monitor, but you can see my glasses and my glasses can see the monitor. Then can you pull out an image of what the monitor looks like from, say, a video recording just of my glasses? Okay, and so it turns out that that's not particularly difficult to do. And in fact, you can do it from very far distances. Like, for example, like if you're, say, in a building beside the building of someone who's in an office, you might be able to pull an image off of the reflection of something. It could be the window, it could be a picture that's hanging on the wall or something like that. And using, advanced algorithms and high definition video, you would be able to reconstruct what someone's looking at. Sometimes these are called tempest attacks, so it's the name sometimes that it's used. Okay, so this is all side channel analysis. Anyways, it's one way that you might go about trying to get the key for a secure tunnel. And once you get the key for the secure tunnel, then you're able to break in to the tunnel itself. And these padding oracle attacks were designed specifically with TLS in mind. All right, another way to get a key. So this is just sort of more of a story, but what you could do is you could try and get the key off of either the client or the server. And so in this case, we're going to target the server. And you could do that basically using any mechanism that you want. So any malware that you can get on the server, you'd be able to get the key out. Or if there's a vulnerability and you could exploit the vulnerability on the server, then you could get the key out. So the story I'll tell is called Heartbleed, and it's just about one vulnerability that existed on servers. But it happened to exist on a lot of servers, about 40 to 60% of servers that were on the internet at the time. And this was big news when it happened. You could just pick up normal newspapers, not technical magazines or something like that, but like just, in Canada, it might be the Toronto Star, the Globe and Mail, or National Post or something like that. And there would be an article, maybe even on the front page, about Heartbleed. That's how big of a deal it was at the time. So Heartbleed was, first off, this is an implementation flaw. Okay, so there's no flaw in TLS or SSL itself. And in fact, this flaw isn't with TLS directly. Okay, it's a flaw that you could use to get a TLS key off of a server, but it was just a generic flaw with servers. So that's the first overlap it has with TLS. So it's not a problem with TLS itself or HTTPS itself. It's just a general problem, but TLS keys is one thing that you might target to steal. The second thing is that the vulnerability existed in a library called OpenSSL. And so OpenSSL is the library that you use for HTTPS. So that's just sort of a coincidence. It could have been a vulnerability in some other library, and we could still be talking about it in this lecture. But the vulnerability happened to be in OpenSSL. So what would happen is that OpenSSL is, first off, it's an open source implementation. And it's the default SSL or TLS library that's used in Linux. It's also used in other platforms. For example, I have a Mac. It has OpenSSL just built in, but most people don't run servers on Macs. However, there's a lot of people in the world that run servers on Linux, and in particular, they run it on Apache. So that's one flavor of Linux server. Okay, so everyone who's running Apache who at some point turned on HTTPS would by default have OpenSSL. You could certainly configure other SSL libraries, but if you're just going with the default settings, you're going to have OpenSSL. And at the time, the default setting with OpenSSL had a like sort of protocol inside of OpenSSL called a heartbeat protocol that we'll talk about. Okay, and so this stack was vulnerable to this attack, Heartbleed. Heartbleed is a play on the words heartbeat. And about 40 or 60% of servers on the web at the time had this particular stack. Okay, so almost about half of the internet had this vulnerability. Okay, what's the heartbeat protocol. So the heartbeat protocol actually has nothing to do with the fact that it's an OpenSSL library. It just has to do with the fact that it's an internet library. It's something that's online. It's running on a server. And the idea of it, first off, it's a very old thing that was put into the first versions of OpenSSL. No one really used it, and I think most people forgot it was there. But it was there indeed, and some security researchers noticed it and thought maybe there's a way of exploiting it. The other thing about OpenSSL, just for interest, is if I recall correctly, I think the person that made it, he said that, I wanted to learn, I forget if it's in C or C++. I think it was in C++. He was sort of like, I wanted to learn C++, so I just implemented a bunch of crypto, and that became OpenSSL. Of course, it was super polished, even by the time Heartbeat came out. Lots and lots of people had, even companies like IBM had put a lot of effort into making this a very robust library. But anyways, there was this older Heartbeat protocol. Like I say, most people forgot it was there. And this is a simplification, but this is roughly the idea. What would happen is you would send some bytes to the server, and you would say, basically what you're trying to do is know whether the server's on and whether OpenSSL is running. Okay, so that was the idea. It was sort of a debugging kind of protocol. And so you would just send it a bunch of bytes, and if the library caught it, then it would echo those bytes back to you. Okay? And if it echoes them back, then you're like, okay, this thing is responding correctly, and so I know it's running OpenSSL, And so I'm happy for whatever reason. Now I'll talk SSL with it or whatever the case is. Okay. Now there was a feature of it where you could have it echo back a subset of what you sent. So you might send a long string and say, I don't need the whole string back. Just send me the first 5 bytes. And then it would send back the first 5 bytes. Okay. And so now this is sort of confusing already because if you want to echo back less, why don't you just send less to begin with? I mean, if you only wanted to send the first 5 bytes back, why don't you just send 5 bytes? But for whatever reason, you could send a much longer string and it would just echo part of it back. Okay. All right. Now, look at this protocol and think about where you might think there could be a vulnerability. If you've seen this kind of thing before, you might immediately recognize it. So what happens if I echo back, say, 3 characters in this case? Then I would echo back 3 characters. I could echo back 6, which would echo back the full string. What if I echo back, instead of 6, 7? Right? What if I echo back 7 bytes or 100 bytes or 1,000 bytes? What would happen? Okay. So what should happen is the OpenSSL library that's catching at the Heartbeat protocol, it should say, okay, that's invalid. You only sent me 6 bytes. I can't echo back 1,000 of them. Maybe it repeats it, just cycles. I don't know. There's different error cases that it could do to handle this. But what it absolutely should not do is it should not say, okay, I'll echo back 1,000 bytes. Here's how I'm going to do it. I'm going to load into memory at the location of where I stored this string. So I stored this string in RAM somewhere. And so I'm going to, load in where I know the character A is. And then I'm just going to echo back everything in RAM, and I'm going to keep doing it until this counter, counts all the way down to 0 from 1,000. So I'll send you 1,000 things that are in RAM at that time. Okay. So we call this a buffer overread. So the buffer is the string, and we're reading past the end of the string. We don't know that the string ends. Again, I mentioned this is programmed in either C or C++. The way it handles strings is it's easy to do things like this. So what's the bottom line? The bottom line is, because of this vulnerability, what you could do is you could ask for it to echo back up to 64 kilobytes of whatever you sent. So you send a really short string. You'd say, give me 64 kilobytes back. And then what it's going to do is it's just going to go into RAM, and whatever happens to be beside it in a stack infrastructure. So then it's just going to echo it back to you. Okay, so what are the kinds of things that might be on a web server that would be sitting in RAM that could potentially get echoed back? Okay, so what it's going to do, what's going to be there is like recent data that it needed for whatever purpose that it was done, that it was using. Okay, so things like a username of someone else that was logged into the server right before you did this attack, their password, it would have to pull into RAM to check it. It would hash it, insult it, and check it to the password database. Other kinds of secrets like cookies, it would pull it in to check it and make sure it's the right cookie that's assigned, or if it receives some data with a cookie, it has to look up which user that corresponds to. Any actual data that the user was submitting, say it's an email client, other emails or whatever they were looking at, that's the kind of thing that could be sitting there. And then for the purposes of this class, we might worry that one of these TLS keys would be sitting there. Okay. Now, without going through the crypto details of TLS, I'll say that there's kind of like two levels of keys that are involved. There's keys that protect the session that's going on right now. So let's say you connect to Google, you have keys, Google has keys, and you're sending information back and forth. You go away. Tomorrow you come back to Google, you're going to have completely different keys. So those keys live as long as your session itself. Okay, you could steal those with Heartbleed. Okay, so there would definitely be the kind of thing that would be sitting in RAM. Okay, but unless if you found yourself in the middle of that connection in addition to executing Heartbleed, it's not going to be that useful, because by the time you find yourself in the middle, those keys the session's over and there's going to be new keys anyway. Okay, but in order to get those session keys, there's a longer term key that's used. It's a key that belongs to the server, and it basically only changes once every 2 years. Okay, so Google, Concordia, whoever, they have these keys. They generate it. They get what's called a certificate for it. We'll talk about that in a couple, a little bit down the line of this lecture. And there's a key that's used, the public key that corresponds to the signing key. And anyways, this key is used for a couple of years. And so if you're able to steal that key, then what you're able to do from a middle position is you're able to impersonate that server or break the tunnel of any tunnel going to that server, basically for as long as that key is still valid until it expires. The certificate that contains that key expires. Or you get caught and then you face the idea of the key getting revoked, which is another whole thing that we'll spend a lot of time on. Okay? But anyways, now here's what happened. People said, I can't remember, it was like a major internet company. I can't remember which one, but they basically said, when you boot up your computer, you boot up a server, this key, and you start OpenSSL, this key gets loaded in right away because you need it all the time. Okay, it's one of the very, very first things that get loaded into the computer. And then a bunch of stuff happens and other stuff is coming and going, and the stack is filling up with memory. And that key is always going to be way more than 64 kilobytes away from whatever you're doing right now. So whatever you're doing right at the moment, this key is it's buried under a whole bunch of other stuff because it was literally the very first thing that you loaded into memory. And so people said, this is really dangerous, this Heartbleed vulnerability, the fact that you can read stuff out of RAM. But the one thing that's probably safe, not like theoretically safe, but in practice, is probably this TLS key. You probably can't get it out. Okay. Now, once the company said that, people, black hat, white hat hackers said they took it as a challenge. And they said, okay, let's figure out a way that we can get this key out. It is correct what they're saying. So this key is like so deeply buried that we probably can't reach it. And so they came up with this idea. They said, well, what if we find another vulnerability where we can trigger a reboot? So we knock the server off. It needs to reboot. And then once it reboots, then we hit it with Heartbleed right away. right? The very first thing. Now the key is fresh in memory. There's not much else that has been going on since it reboot, because it clears the contents of memory, of RAM. And so lo and behold, they were able to pull these out as well. Okay. And so once they demonstrated that they could pull out these TLS signing keys, now this problem becomes really, really bad, because unless if you have logs of like when servers went online and offline, you might have to renew all your keys. And we're talking about like 50% of the web having to update all their keys at once. Okay, so this now becomes like a like front page news worthy like kind of event. So in Canada, the government of Canada servers, they were one of the things that were hit. So CRA, which is our tax agency, they had computers that were vulnerable. They also had logs. And so one story that came out of this was there was a student, 19-year-old, and he was just, he was fooling around. He wasn't trying to break anything, but he saw Heartbleed. He had the technical skills to actually, use it. He probably didn't write the library from scratch, but he was able to get it from Metasploit or wherever. And he thought, oh, maybe I'll just see if CRA is vulnerable. And so he checked, and they were. He didn't do anything with the information, but he did see it. It did traverse into his computer. And, it's a tax agency, so it's like people's social insurance numbers and their tax info and a bunch of like highly private information. Anyways, he thought it was interesting, and then that's it. Nothing happened. But then I don't know how much longer after, it might have been weeks or months, CRA went back through their logs and they said, okay, we know that we were vulnerable to this Heartbleed bug. Let's just make sure that no one exploited it. And then when they went through the logs, they saw that, oh, actually there was at least this one person who did. They got the IP address. The police went to the door or whatever, and it turned out to be a 19-year-old kid. And so he was, if I recall correctly, I think he was found guilty, but they sort of waived. There wasn't like a strong sentence or something like that. It was just sort of, it was probably a suspended sentence or something like that. Like as long as you don't do something else again, you're not going to get in trouble. But anyway, so the reason I bring this story up is just as a reminder, we're learning a lot of content in security courses like this. You have to be really careful what you do. Okay. And even if you're doing things just for education or just to try things out and you're curious, right? Your curiosity can get yourself into trouble. Okay. So you need to think through the legality and the ethics of things that you do, even if you're just curious to try and test things out and see whether they work in real life. All right. Moving on from Heartbleed, we'll talk about downgrade attacks. So this is another sort of category of attacks. So in HTTPS, in TLS or SSL, the crypto that's used in HTTPS, this protocol has been around since 94, I think it was. So it's been around a long time. And the web is also full of lots of people. You wouldn't think about it because it's probably not you, but there are people who bought a computer in the 90s or in the 2000s, running, say, Windows 2000, and Windows doesn't even support updates, but they may not be updating it anyways. Okay, so they have some old-fashioned computer. They're still using it on the internet. And every now and then they're going to come to your website and you're going to say, hey, can you talk TLS 1.3 with me? And they're going to say, sorry, I only support SSL 3.0 or TLS 1.0. Okay. And then you have some decisions to make. You can decide, okay, I'm going to cut you off. I'm going to say, oh, sorry, you're not compatible with my website. Or what you might do is you might say, oh, no worries. I still have those old versions of SSL. I have those old encryption algorithms that were like popular at that time. And because I have them and you have them, let's talk encrypted, right? Let's make a secure tunnel. It might not be the most secure tunnel because the cryptography is a little old, but it's probably better than no tunnel at all, right? And if it's better than no tunnel at all, then let's just go ahead and use it, Okay, so, and the same thing could happen with servers, probably less common, but you could have a server that just no one's updated, since the 90s or the 2000s, and you're connecting with your modern, up-to-date, newest iPhone or MacBook or whatever, and it's saying, oh, I don't speak the latest language. Okay, and so SSL TLS has a lot of flexibility in terms of being able to negotiate what version of the protocol you're using, and then once you decide on a version, you can negotiate the cryptographic algorithms that are used as well. And it has tons and tons of options. Okay, there's like 50 different options that you can choose from. All right. So for backwards compatibility, we allow this negotiation to happen. Now, this is maybe, again, something that's sort of obvious once I say it, but you might not think of it. Is this negotiation happening over a secure tunnel or not? Okay. By definition, it can't be happening over a secure tunnel because the reason you're having this negotiation is to set up a secure tunnel. Okay. So this negotiation has to happen before the secure tunnel is in place. So in SSL or TLS, typically we split what's happening sort of behind the scenes into two stages. There's the first stage we call the handshake, and the handshake is happening before the tunnel's established. Okay, it's basically trying to negotiate and establish the tunnel. And then once the tunnel's established, then you can switch over and now you have the tunnel in place. And that's sort of the second phase of the protocol, which is all the stuff that's going back and forth between the tunnel and encrypting it and decrypting it and checking MACs and signatures and things like that. Okay. So the adversary that's in the middle, they can do whatever they want during that negotiation phase. Okay, there's nothing to stop them. There's no tunnel in place to try and stop them from doing something. Okay, and so what they could do is you could connect to a website and say, I support TLS 1.3, and the adversary could replace that with, oh, I only support SSL 3.0. Okay, and the server, it receives that message and it says, okay, that's kind of weird that you only support SSL 3.0. That's pretty old, but that's fine. I still have, for backwards compatibility reasons, I still have those old libraries. And so let me dust them off and I'll make you a connection with SSL 3.0, right? So it goes back to your computer. And now your computer's thinking, oh, maybe there's a problem with the server. Maybe the server doesn't know TLS 1.3. That's why it's sending me to SSL 3.0. I also have these old libraries just in case I encounter servers like this. Let me dust them off. And then now all of a sudden you're talking SSL 3.0. Your browser's happy. It's not saying it's not secure because there is an SSL connection in place. But there's some vulnerabilities in SSL 3.0 that don't exist in TLS 1.3. And now the adversary is going to try and exploit one of them, right? Or they're going to downgrade your encryption so bad that they can break it. So there's a bunch of different variants. Now, as I say this, you might be thinking, okay, so this is an attack that happens. This is more in the threat category. And so TLS does protect against it. Okay, so it has some mitigations against it. What happens in TLS is one thing that cannot be negotiated is something that protects the message integrity. So you can do a lot of negotiation around the confidentiality of messages, but the integrity, until the most recent version, I think, of TLS, it was always just fixed. It was locked. And it was always a good algorithm. And there was never problems with the algorithm. And that actually saved TLS a bunch of times. Because what would happen is at the end of the handshake, I forget who goes first. Let's say the client goes first. They basically say, okay, by the way, now we have a secure tunnel. I'm going to repeat back to you everything I heard you tell me about what you want this connection to look like. So it would repeat back, oh, I asked for TLS 1.3 and you said you only support TLS, SSL 3.0. Is that actually true? Right? And now that the secure tunnel's in place, because we have message integrity, and there was no way to downgrade away from message integrity, the adversary can't change that message. They could drop it, but if they change it, it's going to get flagged. And so if that message goes through, then the server says, oh, wait a minute, I never said that, right? And then now they have a chance to tear down the whole handshake and start again. So downgrading is possible. It's really complicated. So some versions allow some kinds of downgrades, but not others. And then there's the whole world of actually implementing the protocol. So the protocol itself at various points in time was vulnerable to some types of downgrading. And then there was a period of time where the protocol was okay, but the implementations weren't. And anyways, you can read a whole history of a bunch of different things that fall under this like sort of downgrading kind of attack. Okay, so this is it's interesting to know this because it is a kind of general kind of attack that if you want backwards compatibility and you want flexibility, you are going to have to support different kinds of algorithms and change those algorithms over time, right? And so you need to be able to negotiate things. And if you have the ability to negotiate things, you always could have an adversary in the middle trying to downgrade you to the older versions. So this is something that just doesn't just show up in TLS. It shows up in basically all sorts of network protocols, not even network, but just general cryptographic protocols where you have different versioning and different options that are available. Okay, last thing I want to show you is I want to dig into one of the attacks on TLS. So there actually was a whole kind of family of attacks that were quite related. So the names of them are here. They don't mean anything to you, which is fine. There's one called Beast. There's one called Lucky 13. There's one called Poodle. There's one that concerns RC4. It's that this is an algorithm that was used in TLS. Okay. And all of these attacks have the same kind of threat model or the same setup. And the one I'm going to talk about is crime, and I'm going to talk at a very high level. But I think you can sort of wrap your minds around kind of conceptually what's going on here. And it also is a nice demonstration of like the complexity that people consider things. When they consider these attacks, they consider very complicated kinds of attacks. Okay, so here's the threat model that's common to all of these attacks. I'm going to assume, like we are in the attack tree, that the adversary is in the middle. So they're seeing all the information go back and forth between Alice and the server. It's going over TLS or HTTPS, so they can't read it directly, but they're looking at the outside of the tunnel and they can see the information that goes back and forth. Additionally, I'm going to give the adversary one extra power. I'm going to say they have some JavaScript that's running on the client's machine, and it's running inside of a website that they want to attack. Specifically, what they want to do is they want to get Alice's login credentials for that website. Later, we'll talk about passwords and cookies and the differences between them. But in order to to hijack Alice's session if she's logged into a website, it's sufficient to get a small value called a cookie. So if I can get this cookie value, then basically I can hijack her session and I can be logged into the website instead of her. Okay. So what I have is I have some JavaScript. Now the JavaScript can't ask for the cookie directly, even though it's running on the same website that is putting the cookie in. There's reasons for that. Again, it's going to be reasons that we're going to see later. And actually, now that I say it out loud, I realize that I misspoke. This attack's a little more general. Apologies. This attack is the JavaScript actually can be running on any site. It doesn't have to be on the site that Alice is or that the adversary is targeting. So let me say it again with a specific example to make it clearer. Let's say I want to hijack Alice's Gmail connection to Gmail. Alice and Google have a cookie. Okay. What I need to do is I just have to get JavaScript running in her browser on any website. It doesn't have to be on Google's website. It could be on some website that I send her, maybe through phishing. It could be that I have an ad library that I've exploited. She's on a website that's looking at that ad library. As long as I have some JavaScript running on her machine, then I'm able to target her cookie for, say, Google. Okay. All right. Now, the next thing I'm going to assume, and this makes this attack not very general. Okay, so this attack doesn't work. It only works in very narrow circumstances, but it's the easiest of the set of attacks to understand because you don't have to know any crypto details to understand it. I'm going to assume that whatever the secure tunnel is doing, it's also using compression. So what's compression? Compression is when you have data and it's big and you try and squeeze it so it's smaller, then you send it across and then the person who receives it unsqueezes it. Okay, makes it bigger, recovers the full data itself. We use compression all the time for images, for videos. You can use it generally on data. Okay, is compression actually part of HTTPS? Okay, so it's kind of there. There is support for it, but it's not really used that often. However, for a brief time, there was a competitor to HTTPS that people like Google and Twitter were experimenting with called Speedy. And Speedy does use compression. It's one of the main features of it. And it also uses very TLS-like things. So this attack worked on Speedy, but it could also work on other forms of TLS or of HTTP itself, assuming that you were in the right mode or whatever where this compression was used. Okay. Now, in general, I should say at a high level, we shouldn't care about whether compression's used or not, right? It shouldn't be, we shouldn't live in a world where you turn compression on and all of a sudden your secure tunnels are broken, right? Your secure tunnel should have no concerns at all. Like if the data going into a secure tunnel is compressed or uncompressed, should have no impact whatsoever on the security properties of the tunnel itself. Okay, so we should be happy to have compression if people want to use compression. Okay, but in this case, the combination of a couple things, including the compression, is going to be problematic. Okay, now because the adversary, I'm calling the adversary Mallory, because Mallory is able to have JavaScript running. What can Mallory do with JavaScript? Well, she can open an internet connection to any website that she wants. So if she wants to open 1,000 connections to Google, to Gmail, she can do that with JavaScript. And what will happen is Alice's browser, right before it opens the connection, it's going to say, hey, am I logged into Gmail? Do I have a cookie that corresponds to Gmail? And if she does have a cookie, like a login cookie, her browser will insert it into the request. So the adversary here is able to request from any website they want. They can request anything. So they can name the resource that they're requesting anything they want. Okay, so just think of this purple string as the request that's going to Gmail. And this is under the adversary's control. That's why it's purple. Okay, so it's more or less completely controllable by the adversary. They can put whatever value they want. They don't see the cookie because Alice's browser puts it in after the fact. So they create the request, then Alice's browser will put the cookie value in the header. So they'll put it at the start of it. And then this whole thing will get encrypted and sent across the secure tunnel to the server. Okay, so the adversary can see the result. They can see the encryption of all of this. And they can choose the second half of this message, but they can't choose the first half of the message. But what they really want to know is what's being said in the first half of the message. This is the value that they're interested in. So everything seems okay right now, right? Even though the adversary is able to choose some stuff, the secret is staying secret, and it's all getting sent across a secure tunnel. And the adversary, even though they're in the middle, they can't see the secret. And even though they control the second part of the message, they can't see the secret. Okay, so everything is sort of as it should be. Except for there's one problem. The problem actually goes back to something that we just talked about recently, which is when you encrypt data and you look at the result, the encrypted data or the ciphertext, what's the length of the ciphertext relative to the length of the plain text? And the answer is it's the same thing, right? So if I send a small piece of data that's encrypted, and I send a large piece of data that's encrypted, if I look at the encryptions of it going across the wire, I can tell the difference between the two, right? Because the encrypted version will be the same size as the original data. Okay, so what the adversary is going to do is they're going to exploit that and this idea of compression. Okay, now let's think about compression. How does compression work? Okay, let's think of a picture. Okay, you have a picture and the first thing you should know is that compression works differently. It depends on the picture itself. Some pictures will compress a lot better than other pictures. Okay, so let's say I have a picture and it's of, I don't know, a landscape, and the sky is blue, and 2/3 of the image is just a blue sky, right? And the shade of blue is very, very close. A lot of those pixels are the exact same shade of blue. What I can do is, instead of saying this pixel's blue, this pixel's blue, this pixel's blue, this pixel's blue, I can say the next million pixels are blue, right? And that's a lot shorter to say than to say this pixel's blue a million times, okay? That's the basic idea of compression, or that's all you need to know about compression to understand this attack. Compression obviously can be a lot more sophisticated, okay? So, for example, if I look at this cookie value, right? And let's say I have this, I control this request value. What I'm going to do is I'm going to put into the request guesses at what this cookie value might be. So maybe I write into the request the string E33A. And then what I'll do is I'll have Alice's browser compress the whole thing. Okay. And because this character is repeating, okay, so the character that I have here is a repeat of the character that's here, it's going to compress well. Okay. If I have a guess here that's completely wrong, like 093A, it doesn't show up anywhere in the cookie. Cookie is random information. My guesses are random. Randomness doesn't compress. I didn't go back and say, what's a picture look like that doesn't compress very well? Think of a random picture like static. Okay, that's an image that basically you cannot compress. Okay, so if your data is random enough, you can try and compress it and you're not going to get anything out of it. Okay, so what the adversary will do is they'll just start guessing, a couple bytes or whatever here, and then they're going to sit back and they're going to say, what does that do to the overall result of the length of this thing? If it's getting smaller, then I know those bytes must show up somewhere. And if it's not getting smaller, I know those bytes don't get shown up. Okay, so they start guessing a couple bytes, and then they start combining their guesses, so they have like longer bits of this message, and they know it's right because every time they do it, it compresses even further. And eventually, what you can do is you can essentially read out, you sort of go byte by byte by byte, and you can read out the entire cookie value. Okay, that's what this paper shows. All right, now this is kind of a theoretical attack. Okay, there's a bunch of like practical reasons why this isn't the greatest attack in the world. First off, it's pretty strong assumptions on the adversary. They have to be in the middle, and they have to have some script running, cross-site scripting we call it. They have to have some script running on JavaScript probably running on Alice's computer. Okay, you can't use it to break HTTPS in general. Okay, so I couldn't read your Gmail contents using this attack. All I can do is I can read out things that are in the header that I don't have access to. Okay, so it's good for stealing cookies, but stealing cookies is a big deal. If you can steal cookies, that's a pretty good attack. Okay, cookies are also very small compared to a cryptographic key. A cryptographic key is much larger, and so this is going to work on small data. And then the other thing is you have to do a lot of trial and error. So you're trying lots and lots of guesses, and you're doing these subtle like measurements, and then you're trying other types of guesses. And every time you guess, what you're doing is you're opening up a connection to Google. So you're creating traffic to Google. So if you have to do 1 million guesses, you have to open 1 million connections to Google. That's problematic. Okay, it's problematic. It could be problematic for Google. They might shut you off, but that actually doesn't matter. As long as you're in the middle before Google shuts you off, it doesn't matter if they're going to eventually shut you off. But it matters a lot for Alice. So Alice's computer will generate all of these things. Her computer might get slow. As soon as she closes the tab that has this website open, or Safari crashes or whatever, then the attack is over, kind of thing. Okay. If she's on a corporate network, she might have some sort of intrusion detection. Again, it depends when the adversary's in the middle. Are they past the IDS or before it? If they're past it, then it could disconnect her or cut her off that system as well. Okay, so this attack, anyways, it's not the most practical attack, but it is one example of this style of attack that you can do, even though there's a secure tunnel in place. And there's lots and lots of variants of this attack that exploit things other than compression in TLS. Okay, so let's throw this into a tree. So we can sort of, I split it up maybe a little different than I articulated it, but I'm going to either attack the protocol or implementation of the protocol, or I'm going to attack the underlying cryptography itself. So if I'm attacking the protocol, I could do some downgrade attacks. There's some attacks that we didn't talk about that also sort of correspond to the implementation. There's one called Freak. We could try and leak the key off of the server. So Heartbleed would be an example of that. We could try and leak the key using side channel analysis. So we could do a timing attack on RSA. I put SSL 3.0 because that's the version that has the padding that's vulnerable to this. So it's just a pretty old version. And then there's attacks on cryptography. So Crime I put here. It uses compression or compression oracles. There's other ones that are based on padding. They're a little different. The reason RSA is also based on padding oracles. This one's leaking the key, so I kind of put it up here. These ones are leaking cookies and things like that. It's basically the same setup. The original one that used that setup is called Beast. It uses the fact that the encryption that's used doesn't have the strongest property. So we want encryption that has a certain security level called CCA secure, and it's not the way it's implemented in TLS 1.0. And then there was another string cipher that had biases in certain bytes. Okay, so a lot of this tree isn't going to make sense to you because we didn't go through all the crypto details. Again, this isn't a crypto course, so that's why I'm not covering it. You go and take 6110, 6120 at Concordia or another crypto or network protocol kind of course, you might see some of these attacks. And if you're interested in them and want to do a project or something on it, that these are very interesting attacks to look at. But we're just not going to cover the details, okay? But you get the flavor. The main thing I want to do is I want to leave you with the impression of, first off, the cryptography isn't bulletproof necessarily. So there have been lots of problems historically with these protocols. You have to worry about the implementation on top of the protocol itself, all right? And secondly, it's not like there was one attack once on SSL on TLS. It's more like there were 20 attacks or 30 attacks. Okay, so there's a lot of variation. Some of them have things in common, and some of them are quite different from each other. Okay, so this is a protocol that because it's high value, people target it. They're going to target the highest value protocols, and so people are going to keep digging and digging and digging until they find vulnerabilities. Okay, so that's all I wanted to say about that sort of side of the attack tree, the break into the tunnel attack tree. So again, just to summarize, we talked about what you could see just by looking at the tunnel from the outside. We talked about how to get into the tunnel. Now, the final category we're going to talk about is, can I get the tunnel pointed at me? All right, and this is probably the biggest category of attacks. So the user, they're putting tunnels or messages into a tunnel, right? But they don't see the other end of the tunnel. The other tunnel is somewhere else. So how do they know that it's going to the right place? Okay. All right. So again, there's some cryptographic details, but they don't really matter that much. The main thing is that the way that we tell what the end of a tunnel is, again, goes back to this idea of keys. So there's a kind of key called a public key. So people publish it. And you can have a public key. I can have a public key. Google has a public key. Concordia has a public key. Okay. And if I can get Concordia's public key, and it's actually their public key, I can make a secure tunnel that ends at Concordia. So basically, the only people that could break to end the tunnel would be people who know, well, the private key that corresponds to this public key. Okay, so that's the guarantee. So you can think of it more abstractly as you're tunneling to a key value, right? So if you're able to get the right key, then you're able to tunnel to that key, and there's no way to break it in the middle. And the adversary can't get you to tunnel to them unless if they know that particular key, or if they trick you and pretend that their key is Concordia's key, okay, which is what mainly we're going to be considering here. Okay, so the question I have for you is, how do I know I want to go to concordia.ca? It has a key. If I can get their key, then I can have a secure tunnel to concordia.ca. It doesn't matter if the adversary is in the middle. Okay, so that's pretty powerful. All right, but the simple question is, how do I get Concordia's key? All right, if you can solve that problem, if you can say this is everybody's key, then you've completely solved a huge area of the web. We call it PKI, public key infrastructure. So basically the mapping between keys and identities. And solving public key infrastructure, PKI, would be a huge benefit, not just for cleaning up HTTPS, but there's tons and tons of protocols that rely on PKIs. Basically, any protocol that uses crypto relies on some sort of PKI. Okay. Now, so now the next question is, how do you solve it? Okay. So you're probably thinking one of two things, if anything at all. Maybe you have no idea, which is fine. We'll go through it. But if you are thinking of a solution, you're probably thinking of one of two things. Okay. If you're sort of not deep into technical stuff, right, you might be just thinking of, okay, well, what's the closest thing to sort of solving this problem? Well, what about something like DNS, right? There it was like you had a bunch of names and you had IP addresses. Here we have names and keys. So like, why couldn't it work the same way? Or you might be thinking of like maybe a telephone book, like you have a book and it has everyone's name, it has their phone numbers. So you could have kind of like a telephone book of people's names and of their keys. Okay. So that is not the model that is used on the web. First off, the phone book doesn't work because there isn't one trusted entity that could produce that phone book. Okay. If you have a small PKI, let's say that you have a bunch of keys, say you're within an organization, and you're giving out keys by hand to people, you might in fact use, we call it a directory, so a key directory. It's like a telephone book for keys. You might have a directory, and everyone that works at that company, they trust that company to produce that directory. Okay, but there's no directory for the internet because there's no one company or one organization that controls everything on the internet. All right, so we don't have a directory. DNS style system could actually work. Okay, in fact, there are proposals to basically actually make DNS itself handle keys. So the idea is just that everyone would put their key into DNS. Okay. The short answer of why that doesn't work today is because you'll recall that DNS is not encrypted and there's no message integrity. So if there's an adversary in the middle and you go to DNS and say, give me Concordia's public key, all the adversary is going to do is they're going to swap out the key that DNS is responding back for their own key. Now you're going to get the adversary's key instead. Now you'll have a tunnel that goes to the adversary. Okay. If we could solve the problem of having a secure tunnel for DNS, then we can start to have a serious discussion about whether we could just put keys in DNS. Okay. But anyways, it's something that we actually will circle back to in a little bit, but let's set that solution aside. Okay. Now that was my guess. If you're sort of non-technical, those are the kinds of things that you might be thinking of. If you're a technical person, you're probably thinking that there's a solution and the solution is called certificates. Okay. And so you're partially right. So certificates are involved, but I'm not sure that you've thought through exactly everything there is to know about certificates. Okay, so let's go there next. So certificate is basically just a digital document, and it has the name of someone, say concordia.ca, and it has the public key. Okay, so that's it. It's just it's a document that binds those two pieces of things together. Now, if you say, you ask Concordia or someone else and say, give me Concordia's public key, right? If this is all there is to a certificate, it's just someone wrote down Concordia and they wrote down the public key, the adversary could change that value of the public key to their own. So when you get one of these documents, it doesn't really prove anything, right? It just proves that somebody wrote down that Concordia's public key is this particular value, but that might not be Concordia's public key, right? It could be the adversary's key that they just replaced in this document, okay? So it's going to matter who you get this document from, essentially. Now, we don't like to live in the world where you get documents, you have to care about where you get them from. And so what we're going to do is we're going to do something similar where we're going to solve it with signatures. So we're going to have a document and someone's going to sign it. And now it doesn't actually matter where it came from, even if the adversary gave it to you, because they can't forge the signature, we'll assume. This is a digital signature. We'll assume the adversary can't forge it. Then they can't replace this value. If they replace this value with something else, then the signature is going to break. Okay? And for the purposes of the rest of this lecture, we're going to assume that digital signatures work. They're fine. There's no problem with digital signatures. Okay? So what happens is you have Concordia and you have this public key. Now it's signed by someone. We call them a certificate authority. In this case, say Global Sign. And they sign this document. And so now you can't lie about the key up here. Okay? If you lie about the key here, it's going to break the signature. All right? So that seems to solve the problem. All right? But there's still another problem with this. How do you know that the signature is from a certificate authority? Okay, so this signature is supposedly by this certificate authority called Global Sign. We'll assume that that's fine. Everyone knows that Global Sign should be going around signing these things. But how do you validate the signature? Well, to validate the signature, I need Global Sign's public key. If I have Global Sign's public key, then I can validate this signature. Okay? And I can then have Concordia's public key. But how do I know Global Sign's public key? Right? It's actually just the same question, just at a deeper level. I didn't know Concordia's public key, so I got this certificate thing. The certificate thing is signed by Global Sign, but I can't verify the certificate if I don't know Global Sign's public key. How do I get Global Sign's public key? Right? We just went in a big circle. Right? I was trying to solve how I get Concordia's public key, and now I need Global Sign's public key. All right? So we didn't actually solve anything. All we did is we just kind of pushed the problem around. I'm still sitting exactly where I started, where there's someone out there. I need to know what their public key is, and I have no idea what their public key is. I don't know how to get their public key. Okay? So what do we need a certificate for Global Sign? Well, if we have a certificate for Global Sign, then that certificate needs to be signed by some CA. How do we get that CA's public key, right? So we just go in a big circle, right? Like we don't make any progress on it. Okay, so certificates are not the complete answer. They're part of the answer to the problem. Okay, so the issue that we're facing is, how does Alice know the public key of the certificate authority? Okay, now a side issue that's interesting to ask is, let's say we solve this. I have a way that you can know what Global Sign's public key is. Great. Whatever method that Alice uses to figure out the certificate authority's public key, they could also use that exact same method to find Concordia's public key, right? If I can figure out this key is right, then whatever method I use, call it method X, I could use method X to figure out that Concordia's key is right. Then I don't need certificates at all. Right? Then I can just directly use that method to try and figure out what Concordia's public key is. Okay? Now, there's a second issue, which is Global Sign signed this document saying that this is Concordia's public key. Okay? Global Sign thus had to figure out what Concordia's public key is. They wouldn't sign off on it if they didn't know that this was actually Concordia's public key. Again, they have to have some method for doing that. I don't know what that method is. Let's call it method X again. Okay. So if Global Sign can use method X to figure out Concordia's public key, why can't Alice? Right? Why can't I just use method X to figure out what Concordia's public key is? Then again, I don't need Global Sign. The certificate isn't adding anything. I'll just do whatever the certificate authority did. Right? So how does the certificate authority know what key the website is before they sign it? And then why can't why can't Alice, just do this same method themselves? Okay. All right. So good. I'm happy if you, at this point, realize that, the certificate thing, it sounded really easy. It sounded like a solution. And what we did is we really just kind of pushed the problem around without solving it. Okay. Now, there are answers to these questions. You might not like them. They might not be the most convincing answers, but they're the answers that we got. And it's the answers, of how the web works today. Okay. But we're going to take these sort of like one by one. Okay, so let's start with the first question. How does Alice know the public key of the certificate authority? All right, so this is the idea. The idea is I go to the Apple store, I buy a brand new MacBook, never turned it on ever before, it's never connected to the internet. I turn it on for the very first time, and even before I connect to the internet, the keys of certificate authorities are on that computer already. Okay, so it comes hard-coded with the certificate authority keys. Okay, so they're already there. All right, if you want to see them, you can see them. Okay, so you can go to a place called Keychain Access, or called Keychain on your computer. I think it maybe in the latest version it's changed slightly, but you can see all of the different certificate authorities, and you can see a video here of me scrolling through all the ones that are on my computer. Okay. All right, so that's how we solve that problem. But there's still a kind of issue with this that maybe you're noticing as you look at the scrolling that's happening. Okay, the first thing is, how many of these companies have you actually heard of? So some of them you definitely have. Like I can see Amazon is there, right? That's a company I've heard of. But what about other ones? Like Global Sign itself was the example that we're using. Have you ever heard of Global Sign before? Right? If you're not into like networking and certificate authorities and things like that, you probably haven't. You probably never heard of DigiTrust or DigiCert or DTrust or Entrust. Lots of trusts, right? They sound good. They sound like secure companies, but you really have no idea who these companies are. Okay. The other thing that I might hope makes an impression is that maybe before you saw me scroll through this list, you were thinking that, we probably live in a world where there's maybe 10 certificate authorities, right? Why do we need any more than 10? But you can look and you can see there's a lot, right? There's maybe 50 different unique companies. Some of them, the same company has multiple certificates. And sometimes when you dig into it, you realize that, Symantec owns like 3 of these other CAs or whatever. But there's probably about 50 unique companies, and most of them you haven't heard of. Okay, so the next question is, who cares? Why does it matter? Why does it matter that there's 50 CAs? There could be 500 for all I care. Who cares? Okay, so this is the most important thing in this whole entire lecture. Okay, you're going to watch a 4 or 5 hour lecture on HTTPS, and you only remember one thing. This is what I want you to remember. Any CA can sign a certificate for any website. Okay, so you might think, only certain, like Google, like it's a big website, there's only certain CAs that could issue a certificate for Google. That is not the case. Any random CA could issue a Google certificate, okay? And there's nothing in the TLS implementation of the protocol that says that you should reject that because it wasn't the right CA to sign that certificate for Google, okay? Now, if you're using Chrome, which is a browser from Google, Chrome will step in, okay? They know what CAs Google uses, and they're not going to let you get away with it, okay? But any other browser, and that applies to Google because they're a big enough company and everyone knows them, and they have a browser and they have the most popular website on the internet, okay? But if you're Concordia or someone that's a little smaller, right, you have to worry about the fact that any certificate authority, is able to issue it for any website. And now there's 50 companies. And so what are you going to do? Well, if you're an attacker and you want a certificate, first off, why do you want the certificate? Because if you're in the middle, you can now intercept traffic. You can have the tunnel end at you, right? So if I can mint a certificate for Google or Facebook and I'm in the middle, I see someone trying to connect to Google, I'll drop my certificate in and now they'll connect to me instead. They'll have a secure tunnel to me, so the tunnel will end at me. So that's my goal, is to get certificates for websites that I want to intercept traffic for. And now that there's 50 CAs to choose from, I can choose the weakest link. I just have to get one of them, find one that's vulnerable, and then now I can attack that one. Okay, but it gets worse. There's actually, in practice, sort of more than 50 CAs in the world. And that's because when you go to a website, this is usually what you see. You see that the website, say Concordia, it has its key, and this is being signed by some CA. We'll call it R3. Okay. And R3 itself, it has a signature and a corresponding public key that you can use to check that signature. And that public key is going to be contained into another certificate. Okay. This certificate is going to be signed by someone else, say ISRG, and then ISRG, their certificate will be signed by themselves. So the key here and the signature, the key that's used to verify the signature, will be the same thing. Okay, so it's sort of, we call it a self-signed certificate. And this is what's sitting in your computer that Apple puts into your computer when you buy it for the first time. Okay, so I go looking through that list. This is what I see. I see this certificate. When I go to concordia.ca, I see the site certificate. But what I don't see is I don't see the middle certificate. Okay, and the middle certificate could be a completely different company. All right, so what can happen is the company that controls a root certificate is they can say, I'm going to let some other company issue certificates. And the way I do it is I just sign off on their certificate. And there's way more fields in a certificate, by the way. This is an oversimplification. But there's going to be a field in here that says that this certificate, you're allowed to issue certificates yourself. We'll talk about that, by the way, later. Why can't, if I have this certificate, and we have these chains of certificates, why can't I just start issuing certificates for websites? We'll talk about why that's not possible a little later. But there's basically, it comes down to there's a flag that either says you're a CA or not. And so the root certificate's going to sign off on this intermediary being a CA by basically signing their certificate with a flag set to this is allowed to be a certificate authority. And because that chains back to a root certificate that's coming with your computer, then you trust this intermediary certificate as well. Okay, so why do we have intermediaries? So there's two reasons. So one is what I said, which is that it's a different company. Also, you can have chains that are longer than two, right? You can have 3, 4. You can have, usually the certificates will put a restriction on how long the chain is, but in theory, there's no reason why you couldn't have a longer chain. So that's the first reason. So the first reason is that this is some organization that doesn't have a root certificate, but one of the root certificate companies allowed them, it gave them the power to issue certificates for websites. The second reason is that it's actually the same company. And because these root certificates are really hard to change, like if you get one of these root certificates, if you are a CA with a root certificate and your key gets compromised, basically every computer in the world has to upgrade because it's hard coded in. Okay, so there's no way to like easily fix that issue. So what happens is there's an article, if you're taking this course at Concordia, you'll have access to Moodle, and I'll have it linked to, or you can just Google it, about VeriSign, which is one of the biggest CAs, and sort of where they keep their root certificate. Like it's in a safe, and I think there's like it's sort of split up into like a bunch of different devices, and there are a bunch of different safes, and you need like 10 people like to go in, and they all have to put their fingerprint in order to get in the room. And there's this whole elaborate like security ceremony that's around this root certificate. The problem is that every time someone issues a certificate for Concordia, they have to sign it. So they have to have that key sitting on a computer somewhere in order to sign it. So what they'll do is they'll create a super secret root key. They'll use it once every couple years to create a second key that's not quite so secret. And this key only lasts maybe a year or two. This root certificate is probably valid for like 40 years. If you look in the key store, you can see the validity period of it. And so what they're going to do is they're going to have this super long-term key. They're going to use it every couple years to issue a key that's only good for a couple years. And then this key is going to do all the work of issuing site certificates. And then if this key gets compromised, you have some options for trying to get it revoked that we'll talk about toward the end of this lecture. But anyway, so it's very common that you'll see that even if the root and the intermediary are the exact same company, you still see chains of at least 3 because they're not going around signing things with the root certificates. They're going to create these more temporary, ephemeral certificates to sign things with. Okay, how do you see an intermediary certificate? So where's the list of intermediary certificates? So it's not on your computer, right? You don't see them. You can see the root certificates, but you don't see the intermediary certificates. The only time you see them is when you go to a website and you see that it chains back through it. Okay, so I go to Concordia for the first time. Now I see this R3 company for the first time. Never seen it before. I know about ISRG because it's in my computer. It's hard-coded, but I don't know about this R3. Okay, so if I look through my root store and I see that there's 50 CA companies, that doesn't mean there's 50 CAs in the world. That's a lower bound, right? There could be a lot more because there's all these hidden intermediaries that I'm never seeing unless if I chain back through. Okay, so how can I find how many intermediaries there are in the world? The answer is I can't directly. It's not written down anywhere. Okay, now there are a couple approaches that you could use. Okay, 2 in particular that work. The first is that you could just go to every single website on the web. That sounds a little crazy, but remember that as far as the internet's concerned, we don't think in terms of domain names. We think in terms of IP addresses. And at least on the older version of IP, called IPv4, the number of addresses is searchable. Okay, it's not something you do in a second or an hour or a day. Okay, it's something that takes weeks or months. But you can go to 0.0.0.0, then go to 0.0.0.0.1, etc., and go all the way through to 255.255.255.255. Okay, it will take you a while. And then for every single IP address, you can say, do you speak HTTPS? And if the answer is yes, they'll send their certificate. You can write that certificate down. You can write down the intermediary. Okay, so that's one way that people have done it. They've literally scanned the entire internet, at least on IPv4. When you go to IPv6, there's too many addresses. You can't do this anymore. But you can write down every certificate that you see. Okay, and so people have done these kinds of studies, and there's some really cool tools that let you do this really fast, like with a lot of efficiency. There's another project called Certificate Transparency, and what it does is it tries to log every site certificate that exists, and it doesn't log intermediaries. That's not its goal. Its goal is only to log site certificates. But when you submit a site certificate, you often, or I think you have to submit the full path. So you submit the intermediary as well as the root. Okay. Now, not every site certificate has to be in certificate transparency yet. There's some complicated rules about that that are changing over time. But I think eventually we'll hit a place where maybe by the time you watch this video where every site certificate, basically, if it's not in certificate transparency, your browser doesn't trust it. Okay. But it doesn't quite solve the problem because both of these, for the same reason, don't quite solve the problem because there might be more than one path backwards. So you might have a path that goes through this intermediary, but you might have another path that goes through a different intermediary, and no one's seen that intermediary before. Okay, so anyway, so it's hard to get a gauge on the number of intermediaries, but based on these scans and based on CT and things like that, we think there's probably about 200 other organizations in addition to the 50 organizations that create root certificates. So there's probably about 250 different certificate authorities in the world. Some people say it's up to like 600 or 700. Sometimes it gets complicated. Like there's some large university networks, and it's not clear whether you should count each university as its own CA or if you should sort of count the parent as a single organization that controls all of these universities because they're all sort of in the same country. So there's different ways of counting, but anyway, so this is, I think, a pretty conservative number. Okay, so we care about this because we have what we call weakest link, right? You have to break, any CA can sign a certificate for any site, so you just got to break one of them. You don't have to break all of them, okay? And so if you have 250 targets to pick from, that's a lot better for an adversary than just having 2 targets to pick from, okay? So an adversary that breaches one of these CAs, once they breach that CA, right, then they can issue a certificate for any site on the web. Okay, so they can intercept traffic now for Google, for Facebook, TikTok, whatever, wherever you want. Okay, at least in theory. Okay, so I mentioned that some major websites, if everyone knows your website and your very famous website, then browsers themselves might know the keys that you use and the certificate authorities that you use, and they might lock down the browser so that if they ever see something that's different, then they'll just reject the connection based on that information. Okay, so it's not coming from the protocol itself; it's just sort of insider information. Okay, and browsers do this for sure. Okay, but not every website can enjoy this enhanced security because it relies a lot on having relationships with these companies in order to get that into the browsers. One other thing I'll mention, I think it's a good time to mention it, is, well, first off, have there actually been attacks on these CAs? And the answer is yes. So there are CAs who have been breached. It's not always like you break in and steal the root key. It could be you subvert the process that's issuing the certificates. Somehow you get malware running on it, or there's different ways of breaching it. So you don't have to necessarily steal the secret. You can sort of breach the process that issues certificates and hijack it. But anyway, there's lots of attacks of people being able to do it. There were a lot that happened around the same time. And there were 2 major ones that happened roughly at the same time. One was called DigiNotar and one was called Komodo. And in both cases, somebody was able to break these CAs, and they were able to get Google certificates amongst other things. And the reason that these were discovered, probably, the story I've been told, is that Chrome, the Google's browser, they actually turned on a feature at that time which said, it basically told the browser, these are Google's keys and Google's certificate authorities. And you should start rejecting anything that doesn't look like this. By the way, if you ever are out in the wild and you see a proper, well-formed Google certificate, so like nothing in the protocol is wrong, it's correct, it chains back to a root certificate, it's a valid certificate as far as the protocol is concerned. But as far as Google, the company, is concerned, it wasn't a certificate that was requested by Google themselves, right? If you're ever out on the web browsing with Chrome and you see one of these things, make a copy of it and send it back to Google. So Chrome would just do this automatically. It wouldn't tell you that it was doing it. And so as soon as this feature got turned on, then you start noticing things like DigiNotar and Komodo, and that's how these CAs got caught. Because Chrome was picking up the fact that the people, the actual users of Chrome, were seeing these fake Google certificates in the wild. Okay. Again, the emphasis on fake is just that it wasn't a certificate that Google requested, an adversary requested it, but it was valid for all purposes of HTTPS. Okay, it was a valid certificate. It was actually signed by CA, and these CAs had the right to sign certificates. Okay, it just wasn't a certificate, it wasn't a CA that Google was using themselves. Another thing I'll mention is that CAs are not necessarily politically neutral companies. Okay, so some of them are governments themselves. So I know, for example, in the US, the Department of Homeland Security had a certificate, an intermediary certificate. You won't find them in the root store, but they had one at one point in time. I'm not sure if it's still true today. Okay, some of them are aligned with governments, okay? Or they're just in countries where the government might compel them. Okay, so the government, in theory, could go to that company and say, give me your keys, or, mint certificates for this because we want to surveil our citizens or whatever traffic that we can get our hands on that are flowing through our country. All right, so there are examples of sort of historical cases that were controversial. Okay, so for example, I think it was the UAE, there was a telecom, might have been Saudi Arabia, I forget, and it had been caught putting malware on phones. So you would buy a phone, it would say be an Android phone, but then it would have some customization. And the customization was sort of put there by this company at the request of the government. Okay. And so people were upset about that when it happened in terms of the phone. And then it took maybe a year or two, but someone noticed that, oh, this same company has a root certificate. And so, if the government can get them to put malware on phones, then maybe they can get them to, break HTTPS connections if they wanted to. Okay, so these are the types of things that people worry about. There is a kind of consortium, I would describe it as, where a bunch of browsers and CAs and other stakeholders kind of get together, and nothing's binding. There's no, government. It's not an official thing. They can't boss anyone around and make browsers change or make CAs change. But it's used sort of as a consortium where they just get together and they talk, and then they try to self-govern. So they try to come up with policy changes, and then everyone sort of adopts them. And so this is the kind of thing that would be discussed in those kinds of forums. So it's called the CA/browser forum, that particular one. Okay, so we answered the first question, although I will note that we actually only answered the first half of the first question, so I'll say something about the second half. So the first half was, how does Alice know the public key of the certificate authority? The answer is it comes hard-coded in her computer, or it chains back to something that's hard-coded in her computer. Okay. Now, the next question is, why can't Alice use the same method to determine the key of the website? So Alice knows VeriSign's public key. Why can't she know Concordia's public key the same way? In other words, why doesn't Concordia have their key in this key store, right? I buy a computer, it comes with a whole bunch of keys. Why can't it have the keys of all the websites? The answer here is that the websites are changing all the time. So these certificate authorities, they've been sort of stable for some amount of time, but there's new websites that are created, and there's going to be, when I buy my computer, there's going to be websites that are created after I bought the computer. And so there's no chance of that getting put on my computer, unless if Apple's like pushing software updates or something like that. So that's why we call it an anchor. So we anchor trust in a set of 50 root certificates, but then because we can create new site certificates and just chain back to those root certificates, it allows greater flexibility. So I just need to know the public keys of like 50 companies. And from those 50 companies, I can get evidence of what other people's public keys are, even if I don't know what their public keys are. I don't have a copy of their public keys on my computer. Okay, so that's why we use CAs and things like that. Okay, then the next question is, how does the certificate authority figure out what Concordia's website is? So they signed off on what Concordia's public key was. They had to figure that out somehow, right? And why can't I do what they did? Okay, they did something, so why can't I just do that? Then I don't even need a certificate authority. Okay, so what's in a certificate itself? Okay, so first off, there's a lot of stuff in a certificate. It's maybe worth just looking at a certificate for 1 second. So I kind of simplified it before when I showed you just that it was a name and a public key. There's a bit more to it than that. If you want to see a certificate, different browsers do it differently, and it also changes over time. But right now in Safari, what I do is I click on this, and then I click on Show Certificate. And so first off, up here, you can see that chain that I've been showing you. So Concordia has a certificate, Global Signs signed it, and then this one, because it has that sort of bronze or copper looking thing, that means it's a root certificate. So this is the thing that's hard-coded on my computer. This is the intermediary that I've never seen before until I connected to Concordia for the first time. And then this is Concordia's certificate. The certificate details are here. So you can see you have Concordia University, you have the name of the website. Then you can see a bunch of sort of cryptographic things, and you can see information about who's signing this. So Global Sign is signing it. Then you can see the public key itself. So the public key is this value. And then there's a bit of other stuff you need for the public key as well. So you need to know what kind of key it is. And it's a little more than a single value. There's some other values that you need as well, but that's all there. And then this is the signature of the CA on everything. Okay, it doesn't expand for whatever reason. Then you have a whole mess of other stuff, okay? This is a bunch of policy stuff, parameters, things about revocation, and we're going to see some of this stuff. So I'm definitely not going to like walk you through what every field means in a certificate, but we'll see 3 or 4 of what these things mean, and we'll kind of dig into what they mean before we're done this lecture. Okay, but anyways, that's sort of what a certificate looks like. And in general, there's also different kinds of certificates. So the certificate that we were just looking at is something we call an OV certificate. And what it will do is it will bind together the domain. So concordia.ca, that's the website I'm going to. I'm trying to get the public key because I want my tunnel to end at concordia.ca. And so I'll get the public key. So that's both of those things have to be in the certificate. But then what is Concordia? You know, is it Concordia University in Montreal, or is it the other Concordia University, or is it some other entity called Concordia, right? Is it somebody whose name is Concordia? Like what's the real world identity? Okay. And so what an OV certificate does is it tries to say something about this in addition to these two things. Then there's a stricter version called an EV certificate. So an EV certificate, it goes into more detail about who the person is, okay? So the difference between these two, I'll talk about in a slide, but let's just set that aside, okay? Then there's a lighter weight kind of certificate. It's called domain validated certificate. And all it does is it tries to figure out who controls concordia.ca and what the public key is of the person that controls concordia.ca. But what it doesn't attempt to do is try to figure out what is Concordia. Is it a university? Who is it? So there's no information about that. It just says, here's a domain, and here's the key that's associated with that domain itself. Okay? All right, so these are different kinds of certificates. Okay, so an EV certificate is going to try to bind together not just the domain, but the actual organization that holds the certificate. EV certificates are sort of the original vision of what a certificate would be. Okay, so we always thought certificates would look like this, but for whatever reason, we moved away from it. So DV certificates are sort of a newer concept. I'll talk about why we moved away from them in a second. But basically, there's going to be some like person-to-person verification. Okay, so it could be things that are sent over the phone or documents that are sent back and forth. And the organization, let's say Concordia, is trying to get one of these. They're going to try and convince the CA that they actually are Concordia. They're someone that works at the IT network admin at Concordia, that type of thing. And so this is a pretty secure process because it goes back and forth. There is some vulnerability to social engineering. There's actually a story about someone who was able to get a certificate from Microsoft because they previously worked at Microsoft. So they had a valid Microsoft identifier card, and they went to the CA and asked for a certificate for their own key, and they were able to obtain it with a fake, not a fake ID. It was a valid ID. It was just expired. Okay, so the CA didn't know that this person no longer worked there. In this case, it wasn't a certificate for HTTPS. It was for something slightly different, which is code signing, but it works more or less the same way. Okay, now the problem with this stuff is that it's pretty expensive to do, and it's slow. It takes a couple days or maybe a week. You know, there's a lot of back and forth in order to get a certificate. Okay, and so that's something that we're going to want to fix later. Now, another thing is, let's say you're looking at a website and it has an EV certificate. How do you even know it, right? I told you Concordia's was an OV certificate. How do I know it was an OV and not an EV? So for a period of time, it's no longer the case now. But for a period of time, what would happen is back when we had locks to indicate that you were on HTTPS, they would also use the color green. So you'd have a green lock, and that means it's one of these extended verified certificates. And one of the things they verify is the registered business name. So if you're a registered business, say Concordia is registered in Canada, then you would see, it wouldn't say just concordia.ca, it would say Concordia, the name of the university, and then it would say CA or something for Canada to indicate that this is a registered business in Canada. Okay, so it would try to tell you beyond just that you're on a particular website, that you're on a website with this particular name. Okay, this is important sometimes because maybe you go to like, I don't know, sometimes people like register domain names because anyone can register any domain name. So maybe someone got concordia.ca before Concordia University did, and they refused to sell it. Okay, and then maybe they themselves, because they're malicious, or maybe an adversary targets that particular domain because they know there's a lot of people going there that are going to get confused, and they put a phishing page there that looks like Concordia's website, but it actually isn't. Okay, so what EV is meant to do is it's meant to stop those kinds of attacks, because not only do you have a certificate, you know the name of the company that you're connecting to, and even if an attacker could take a domain that kind of looks like it's right, they wouldn't be able to get a certificate with the actual company name here. Okay, now this was a failed experiment. So people over time realized that basically no one pays attention to this. People could be on a website that was green or not green and had the name or doesn't have the name. And so browsers eventually said, we're going to, it's not removed completely. I'll show you what it looks like today, but they're going to de-emphasize this. And so basically it's hidden, so you can't really see it anymore, unless if you go digging for that information. Okay, so it was sort of an experiment that failed. So now it doesn't matter what kind of certificate you have. It basically always looks the same, at least from the main browser window. Now, an OV certificate is just a little less rigorous than an EV certificate. So it will include the name of the organization. So, for example, Concordia, but it won't necessarily go checking whether that's a registered business name with the government and things like that. Okay, so you get some level of validation, but not the full-fledged validation of an EV certificate. Okay, now the problem with, say, an EV certificate is, let's say you wake up one day and let's say you open a business and you're doing really well. You're making, I don't know, $1 million a day. And all of a sudden you wake up and you check your email and you have hundreds of messages from very frustrated customers that say, we're trying to buy stuff from your website, but we keep getting these errors that say certificate expired. What is that? And you realize that, these certificates that I have, they don't last forever. They last, maybe a year or 2 years. And I forgot to renew my certificate. I forgot to get a new one to replace the old one. Now my certificate's expired. And because it's an EV certificate, I have to go back to my certificate authority and I have to, send them all these business documents and things like that. It's going to take me 3 days before I get a certificate. And now I'm losing $1 million a day for 3 days, right? Like, that's not an acceptable solution. I mean, I made a mistake. That's fine. That's on me. But I shouldn't have to wait 3 days to fix that mistake. I should be able to fix that mistake right away. So what people said is, we want certificates. We want this to be an automated process. We don't want to go back and forth with certificate authorities. And the CA said, okay, here's what we can do. We can automate it. That's fine. We can absolutely automate it, but we can't automate the process of whether you are an employee of Concordia University, the registered business in Canada, right? Like that, we just can't automate that. A computer can't decide whether that's true or not. But the one thing a computer could try to decide is whether you control the domain concordia.ca. Okay, and I'll talk about how they do that in a few slides. And so if we can automate this process, what we could do is we could give you a certificate. The certificate isn't going to say who you are, what your organization is. It's just going to say your key and the domain. and we're going to sign off on that. And we can do that automatically. It just, takes a couple clicks on our website. You have to pay for it. But if we do that, then that's fine. Okay, so that's how we ended up with domain validated certificates. And then once we had domain validated certificates, they were cheaper, they were automatic. And so lots of people just switched to them. Like, why even bother with an EV certificate, especially now because it looks exactly the same anyways. Why even bother with it if you can just get a domain validated certificate? Okay. Now, domain validated certificates, they're not going to solve that problem I mentioned of, let's say I'm able to register, say, Google with 3 O's, right? I can get a DV certificate even though I'm not Google because the certificate isn't saying I'm Google. It's just saying I'm the owner of this domain. And if I actually own that domain, then I own it, right? So I'm entitled to a certificate for that domain. By the way, if you see a website that has a certificate, that doesn't mean the website is good or trusted or anything like that. It just literally means you have a secure tunnel to the website. It doesn't say anything about how trustworthy that website is. Websites with malware, phishing websites, they can get certificates too. Okay, certificates just basically say this is the information you need to form a secure tunnel to and from this particular website, but it doesn't say anything about the quality of the website itself. Okay, right. Whereas if it was an EV certificate, you could also get a certificate, but you couldn't say that you're Google, the company in Mountain View, California. Right? You would have to have another registered business name, and if you're an attacker, you're not going to put some government registered business name on it. Otherwise, the government will be able to track you. Okay, so how do they look? How different do they look? So let me, I'll actually show it to you here. So this is Concordia, okay? I mentioned it's an OV certificate. So the way I do it is I go to Safari menu and I click on Connection Security Details, and then it says blah, blah, blah. And when I look at the certificate, I do see, I see that it does say Concordia University. It's in Quebec, Montreal, Canada, okay? I also see the word OV here, okay? But the real way I know this is an OV certificate is buried. So it's buried in one of these fields here. It's called policies. Let me see if I can find it. And so it's actually just this number. There's this weird number that's sitting in this field. And I have a slide about it, so I'll show you what these numbers mean. But anyways, that's how just this weird number that's sitting here tells me it's an OV as opposed to a DV, as opposed to an EV certificate. Okay. Okay. So what do other websites look like? So here's 3 examples. Google, they just use a DV certificate. Okay. They don't bother with anything else. And so it just basically binds together the circle's kind of in the wrong spot. I meant to circle the thing above it, which is the name is google.com, and then there's a value for their key. So they bind that information together. What I accidentally circled was the issuer name. So this is the person that's issuing the certificate called We2, but notice that that's Google themselves. Okay, so why do Google just issue themselves domain validated certificates? Well, it's because they actually control the root certificate themselves. Okay, they're not a company that's going to another company getting a certificate from them. They're just a company that owns the whole chain, and so they don't really have to bother with anything more than a DV certificate. Okay, if you're Concordia, you don't have that benefit. You're not a certificate authority. You don't have a root certificate. So you might be looking at something like an OV certificate. So in this case is exactly what we saw. And then an EV certificate, PayPal is an example of one that has the EV certificate. First off, you can see a lot more information, okay, including a business name and a registration number. So this is the registration number of this business in the United States. And what browsers do, the one little thing, well, Safari does anyways, to distinguish is before you clicked on this menu to expand everything, you'll notice that the information here is slightly different. It adds something. So both of these just say that you have encrypted communication between your computer and google.com and concordia.ca, sorry. Notice they don't say Concordia University here. They just say you have secure communication with concordia.ca. But when you have an EV certificate, they say, oh, actually, your secure communication is to the company DigiCert Incorporated, which is, the DigiCert's the CA. They've issued a certificate for PayPal.com, but PayPal.com is a company named PayPal Inc. It's registered in San Francisco, California, and U.S. Okay, so it says something about the actual company itself, in addition to just saying, oh, you have secure connections between you and a particular domain name. Okay, so that's the extra little bit that gets added. But again, if you don't go opening menus and looking at this stuff, you would never know that you're on a website that uses an EV certificate as opposed to a DV certificate. How do you specifically know, other than relying on the slight differences in the certificate itself? Well, it will be encoded in the certificate itself. So DV certificates are assigned this number in a field that's called certificate policies. So there's a field called certificate policies. You can see this number shows up. That means it's a DV certificate. If it's OV, the number is this one. So you can see it there. And if it's an EV certificate, it looks like this. Sorry, it looks like here under policy ID 2. Okay, so it's not even human readable. You would never notice the difference there, but anyways, it is there. It's in the certificate itself. Okay, now the next question is, let's say we go this DV route. For EV certificates, I send business documents back and forth. Let's say I want to do a DV certificate, and the promise to me was that this was automated, that if I forget to renew my certificate and I wake up and I realize it's expired, I can spend 5 minutes getting a new certificate. I don't have to spend weeks or days getting a new certificate. Okay, so CAs have different processes for doing this. There's 3 that I'll talk about. There's one called email. We'll spend the most time here. Then these are just slight variants on it. So there's a variant using HTTP, or you can use API requests, and essentially the threat model is the same. And then there's an option through DNS as well. Okay, and basically all the attacks that are possible on the first one, generally the same variants of the attacks are possible on 2 or 3. Okay, and this one actually I think has the most attack surface for you to try and look at. Okay, the process goes like this. So I'll just walk you through it, and then we'll think about whether this actually works very well or not. Okay, so I'll go to a CA and I'll say I own domain.ca. And maybe I do, or maybe I don't. Maybe I'm an attacker that wants a certificate for domain.ca, or maybe I'm the actual true owner of domain.ca. The job of the certificate authority is to tell the difference between the two and only issue the certificate if I'm actually the owner, and not issue the certificate if I'm someone pretending to be the owner. Okay, so what I do is I request a certificate for the website. This is called the CSR. That doesn't really matter that much. It's basically all the unsigned certificate. So all the information in the certificate not signed by the CA yet, I'm asking them to sign it. And what the CA will do is they'll say, okay, we want you to prove that you own this domain. So here's what we're going to do. We're going to generate a random code, and we're going to either email the code to admin@domain.ca, or we'll send a link in that email, and the code will be embedded in the link. So you just have to click on it. And when we get back the fact that you either clicked that link or that you typed in the code on our website, right? Then we'll believe that you at least control that email address, admin@domain.ca, because that's the only way that you could have gotten that code. And because you control that email, therefore you control the domain.ca. And so we're now satisfied. Okay. If you were someone that was impersonating domain.ca, we would send that email, but you wouldn't get that email because you're just impersonating them. You're not actually domain.ca. And whoever is running that thing, they would see this email, but it's completely unsolicited. And you know, they didn't try and get a certificate from us. And so they're going to ignore it, or they might report it as a problem or something like that. Okay. And so if you can basically relay that code back to us, then we'll sign the certificate. So how long does this process take? Well, it takes as long as basically getting an email. So you do a bunch of stuff on their website. You know, it generates an email, it sends it to you, you click a link, and then you're done. Now you have a certificate. Okay. So it's not quite 100% automated because you have to go into your inbox and click on a link, but it's pretty close to being fully automated. Okay. Good. Now, are there any vulnerabilities in this? Let me put the protocol back up. So take a second, look through this, and try and think about, you're an attacker. You want to get a certificate for domain.ca. You want to convince the CA that you actually own domain.ca, even though you don't. How are you going to do it? Okay, so there's a couple of different things that we could do. The first is, if we get access to the mail server, then we have access to the email. Okay, the mail server is going to be somewhere physically. It's going to be in a server room somewhere. And so if we can get access to that server room, then we could get access to it. It also is, because it's sending and receiving emails, it's online. Otherwise, the emails aren't going to reach it. And so we could also try remotely to try and access and breach the server, depending on how it's configured and the network's configured and things like that. Okay, so that's one approach. If we can control the server, then we can answer that email. We can get a certificate for that website. Email accounts, how are they protected? Generally, still today, you know, maybe two-factor starting to come in, but generally it's just a username and password. Okay, so if I'm able to guess the password, keystroke logger, just a random guess, getting malware on the machine of the person that can access this, whatever the case is, if I'm able to get that password, then I'm able to read that email, and then I can get a certificate for it. Okay, so that's things targeting the recipient of the email itself. Okay, now what if remember, we're considering this whole attack tree under the assumption that I'm already in the middle of communications. Okay, what if I'm in the middle of that email? So the email is sent from the CA to domain.ca, and I'm somehow get myself on the path that email goes across. Okay, is there a secure tunnel between the sender's email and the recipient's email? Is it encrypted? Does it use HTTPS, or does it use anything else? Okay, so what do you think? This worth thinking about, right? When you send an email, is that encrypted or is it not encrypted? So you might think it's got to be encrypted because everything is encrypted, right? Like it seems crazy to send around emails that aren't encrypted. If they weren't encrypted, we probably know about it, right? But the answer is that they actually aren't encrypted, at least not securely encrypted. Okay, so what email uses is uses something called optimistic encryption, and so basically what that means is it says if I'm sending an email to you, and I've never sent an email to you before, so I don't know anything about you, I'll go to your mail server over plain text, no encryption, and I'll just say, give me your key. And your server will give me its key. And if there's no adversary on the line, then I get your key. And once I have it, I'll remember it. Okay, so if an adversary comes along later, it's not going to work because I remember your key. Okay, but if the adversary is there the first time, then when you send your key to me, the adversary will replace it with the adversary's key. All right, and now I have a secure tunnel to the adversary instead of a secure tunnel to your mail server. Okay, so we call this trust on first use, this idea of you just, you know, cross your fingers and hope you get the right information the first time. And if you do, then you remember it, right? And you can remember it for the future. There's other things that work this way, like SSH. If you've ever logged into a computer, it's sort of like, okay, here's the key. Do you want to trust it or not? But anyway, so that's basically how email works. So we call it opportunistic encryption or trust on first use. The email also doesn't cover the full path. So you don't have a secure tunnel. Like say I'm composing the email on my computer and I hit send. It's not the case. And then you're reading the email on your computer. It's not a tunnel from my computer to your computer or my email client to your email client. It's more like I have a tunnel to my outbox. And then when my email sends it, it sends it to another mail server, and there's a secure tunnel between the mail servers. But then sometimes email gets forwarded, but each time it sort of breaks down the decryption and forms a new encrypted tunnel to the next party. So we call this link by link encryption. So it's getting encrypted, decrypted, encrypted, decrypted. Okay, so if the adversaries, even if they can't break the encryption, if they're at any one of those links, then they're able to also see the decrypted email as well. Okay, so short end, email is not secure the way that you think it is. It's not encrypted. There are things that you can do. If you want encrypted email, you can add PGP or GPG is the free version of it. It's something that a lot of people use for email encryption. In corporate environments, you might see something called SMIME, and that gives you true inbox to inbox encryption. But generally, email is not encrypted. Okay, so if you're in the middle, you could potentially intercept that email. You could thwart the encryption. You could get the code. And then once you have the code, you could get the certificate for the website that you're trying to impersonate. There's a paper, by the way, that we wrote that looks at all the different aspects of email, its security. And this is something that I cover at least when I teach the course at Concordia called INSE 6120, Crypto Protocols and Network Security. You could try and just guess the challenge value. So CAs will choose something that's random and long, so this probably isn't going to work, but it's worth noting it in an attack tree that this assumption must hold. It must not be a guessable value. You could try a whole bunch of values until you get the right one. If the person's using webmail, so sorry, let me say this slightly differently. Let's say I'm trying to get, I'm an attacker, I'm trying to get a certificate, and the person that I'm targeting runs a webmail service. So for example, I want gmail.com. I want a certificate for gmail.com. Okay. What I could do is I could just go to Gmail and I could say, okay, I want to sign up for Gmail. And they're like, well, what email address do you want? And I say, well, I want the email address admin. Okay. If I have the email address admin, then all the CA stuff is getting sent to that email address. Okay. So admin is a kind of special address. And there's this assumption that wasn't really written down. It was just sort of assumed that you would never hand out the email admin at, domain.ca to just any normal user. That's like a special email. It should be reserved. Only the IT staff should have access to that email, right? But that wasn't like really written down anywhere. Okay. Now here's another question. Why admin? Right? What does admin mean? So admin is short for administrator, okay? Because we call people system administrators that manage this networking stuff, okay? And really stupid question, but what language is the word administrator in? Right? That's English, okay? Now, does the entire internet run, in English? So actually a lot of it does because a lot of it was developed in the United States. So there's a lot of names of protocols and things like that have English in them. Okay. But there are CAs all over the world, right? And so is a CA somewhere else that doesn't use English, are they going to send an email to admin, or maybe they use the local language version of admin? Okay. Also, is admin itself like what about administrator at domain.ca, right? Like why how did we decide to abbreviate to admin, right? Are there other kinds of names that we should reserve? Okay. And so it turns out that there's other names too, like host name at domain.ca, and there's a bunch of other things that people just sort of assume are technical email addresses that you can use to reach the system administrators that wouldn't be handed out to normal users. Okay, and Who's deciding this? Well, the CA is deciding it. The CA was the one that said, I'm sending the email to this email address. And some CAs let you choose as well. So they'll give you a menu and you can say, okay, do you want to receive this email at admin or at host name or whatever? And remember, again, there's 250 CAs. They're all over the world. They're all in different languages. All it takes is you finding one CA that will send it to a weird address that someone like Gmail or live.com, Hotmail, Microsoft's email service, or whoever's webmail, that they don't know is on a CA's list, right? If there's some CA out there that will send this kind of email, right, to some email address, and Gmail is not aware of it, Google's not aware of it, they will not have blocked you from registering that address. You could register that address and you could receive a certificate. So this is precisely what happens. There's a CA, and the CA had the option of sending this kind of email, this sort of challenge, to SSL certificates at whatever domain. Okay. Now, nobody, including at Microsoft, knew that SSL certificates was something that a CA would send emails to, assuming that this would never be a user, this would be an administrator. So Microsoft had not set aside this email and said, oh, no, you can't go, if a user comes up, like this guy named Mike comes and says, I want SSL certificates at live.com, they haven't set that aside and said, oh, no, you can't have that email because some certificate authorities use that email. Okay, so this is a real story. He was a security researcher, so he was able to find a CA that would send it to a weird address. He went over to Microsoft's, which was called Live at that time, to their webmail, and he was able to register this address. Then he was able to complete the certificate verification process. He was a white hat hacker, so he purposely got an expired certificate, but he was just trying to prove the concept. And once he got the certificate, it was for all of live.com. Which is kind of like all of Microsoft's resources. It's not just their webmail. There's a lot of stuff that they do under that domain. And he could intercept all traffic to and from that, assuming he was positioned in the middle. He could, in theory, with that certificate, intercept all of that traffic. Okay. Now, he disclosed it instead. And, of course, everyone scolded this certificate authority for having a weird name. But it also kind of begs the question of how many domains are there, right? If you're a sysadmin, right? How many of these things are you supposed to register? Like admin, administrator, hostmaster, is there a list anywhere of all the ones that you're supposed to register? And so if you go looking, you can go look different, specs and things like that. They all have kind of different ideas of names. And I found one repository, and it basically said, okay, we have 1,250 email addresses that you should only allow admins to use. Okay, because there's lots of weird stuff out there where different people are using all sorts of different kinds of names. Okay, so 1,000, that's crazy. And this is what happens when there's no central control over things, right? Things just evolve organically. You have CAs and they start doing stuff, and then the system administrators try to keep up, and there's no rules in place or anything like that. And so you end up with 1,000 different email addresses that you shouldn't have. Now, that's not to say that we need a central authority. I'm not arguing that at all. If you know me, I do a lot of research on decentralization and things like that. But at least something like the CA browser forum, where even though it's not binding, it's not legal or anything like that, it's at least somewhere where people can come together and talk about this stuff. That's the type of organization that could work out an agreed upon list that they could try and get all CAs and all browsers to follow and say that we're only going to use these email addresses for this purpose. Okay, now setting aside that, let's say that you're going to send an email to me. How does that email get to me? It has to come to my server, right? My server for receiving emails. How do you know where that server is, right? You can't literally just drop, jclark@concordia.ca. You can't drop an email to that address on the wire and computers know where to send that email. They can't get it to me, okay? So again, we need a kind of DNS thing where we have a domain. So you're sending it to j.clark@concordia.ca. So I'm going to try and figure out what concordia.ca's IP address is. But in this case, I'm not interested in their IP address for their website. I'm interested in the IP address for their mail server, which handles all of their email. So DNS does this as well. So it doesn't just keep track of IP addresses for websites. It also keeps track of IP addresses for mail servers. It's called an MX record. It's one of the things in the DNS. Okay, so it's the same thing. You'll go and you'll look it up. Now, can I attack that? Sure. There's different ways of attacking. So, for example, how does that information even get into DNS? Right? How does it get into there in the first place? Okay. So later we'll do a lecture on social engineering. I'll show you an attack where someone was able to change the DNS record for a domain that they did not control, which is called domain hijacking. Okay, so if I can hijack your domain, then I can change your MX record to my mail server, and now that email's coming to me, and because that email's coming to me, now I can get a certificate for your domain. Now, the attacks that apply to email also more or less apply to the other two types of things, but we'll just go over them anyways. So let's say another thing we could do is we could use HTTP. And it's the same sort of idea. What I do is I put something on my domain, for example, a copy of the certificate that I'm requesting, and I just put it at a location that the CA expects it at. So I just say I stored it at csr.txt. And what the CA will do then is they'll go and they'll fetch that information. So they'll open a connection to domain.ca. They'll request this resource and they'll get back this resource. And if this matches what I'm saying, then they'll assume that I must control domain.ca because I'm the only one that could put that file on that domain at that location. Okay. Now with APIs, it's more or less the same idea. It's sort of like I have a domain that's sort of well published. And what the CA can do is it can basically it can hit my domain at that location, and I'll have a server there, and it will talk to the CA, and they'll basically just go back and forth. And what I can do is I can have it like fully automated so that it, maybe it renews a certificate automatically every month or whatever. So like Let's Encrypt is an example of a CA that does this type of thing. Okay, but it's the same idea. It's I'm trying to reach a particular URL. I, in this case, is the CA. If I can reach it and get the file back, then I believe it. Okay. Now there's maybe a couple issues with this. So the first is I did say we do it over HTTP. I did not say over HTTPS. So why is that the case? Okay. Why can't I fetch this over HTTPS? Isn't it a problem? I mean, it is a big problem, right? So let's say that the CA requests it from domain.ca, and domain.ca says, I have no idea what you're talking about. There's no file sitting there. But the adversary's in the middle, then the adversary will just change that response to say, oh yeah, here's the file. It was found, and here it is, and send its own file down to the CA. Okay, if it was over HTTPS, if they had a secure tunnel, then that attack wouldn't happen. But because there's no secure tunnel, that attack could happen. Okay, so why can't we have a secure tunnel? Well, the answer is because the reason we're doing this protocol in the first place is because we need a certificate, and we can't have a secure tunnel without a certificate, right? So we have a sort of chicken and egg problem where I can't run this over HTTPS unless if my domain already supports SSL, TLS. But in order to support it, I need a certificate. And if I need a certificate, then why am I asking the CA for a certificate, right? I already have a certificate. Okay, so it could technically run over HTTPS if you're doing things like renewing a certificate before your old one expires. But if you're ever in the situation where you're registering for the very first time, or you're renewing after one has expired, then you're going to have the option of running it over HTTP. Okay, so in addition to that, basically, if I can attack DNS, I can redirect this request to my server. If I can attack the password that controls this domain or controls the DNS register for this domain, any one of those passwords I can get, I can break this. If I have physical access to the server that's serving up this domain, I can get access. If I'm in the middle and it's going over HTTP, I can get access to this. A lot of the same similar attacks, a lot of the same attacks as on email, and some of them are similar rather than the exact same, but it gives you the same idea. Okay, and then finally, DNS. So the idea here is that you, instead of putting your request information on your domain at a location, you just put it in a record in your DNS. There is a record called TXT. Now the CA is going to check DNS for that record. Okay. Now this works pretty well. The problems are you still have attacks if someone's in the middle, but in this case they have to be in the middle between the CA and the CA's own DNS. Okay. So the CA is not going all the way across the internet. Okay, they're just going to their local DNS. They probably run their own DNS resolver. Okay, so having a man in the middle in that position is a lot less plausible. Okay, and they can also turn on something called DNSSEC, and if that's turned on, then it doesn't matter. There could be a man in the middle. They can't really do much about it. Okay, you could try and attack the DNS record. I mean, it has to start somewhere close to domain.ca, like they go to their domain registrar. By the way, if you break into that with their password or anything like that, you get access. And then once their domain registrar knows what the TXT record is, the DNS system has this whole protocol for kind of spreading that information, because the CA's local DNS resolver is not necessarily going to know about any changes that are made until it spreads from the registrar for domain.ca all the way to the DNS resolver for the CA. Okay. Now, there's opportunity for attack there. Okay. So there's a bunch of DNS style attacks that we're not covering in this course where you try to corrupt or pollute records as they propagate. And the other thing, though, I'll note is that it takes some time. Okay. So if I put this TX record in today, by the time the CA's DNS resolver knows about it, it might be a matter of days. It might be 2 or 3 days later. Okay, so this approach isn't preferable to the email or HTTP approach. It's because it's a lot slower than these two approaches. Okay, so let's go back to many slides ago. We sort of said, okay, we're gonna introduce certificates to solve this high-level problem of I don't know what Concordia's public key is. Okay, and we said, well, if I don't know Concordia's public key and I just have a certificate that's signed by someone else saying what its public key is, well, how do I know the public key of the person that signed it? And so we trace that back to this idea of CAs and your computer coming hard-coded with them. Okay, then the second question is, how did the certificate authority know the key before they signed it? So how did they figure out what Concordia's key is? And so the answer to that was they did either an EV type of process where they, had documents sent back and forth, and they were able to figure it out that way, or they did one of these automated processes where they only issued a DV certificate. But it was automated, and they figured it out because the person was able to respond to an email that was sent at admin@domain.ca. Okay. Now, why can't Alice use the same thing? So if the CA can figure it out, why can't Alice just do the same thing itself? Okay. So the first thing I want to point out here is, at least as far as DV certificates are concerned, even though we call a certificate an authority usually means you're authoritative over some information. Like I know, like the government knows things about me, right? They're like an authority for that information. But certificates aren't really an authority. They don't actually know anything that no one else knows. They don't know what Concordia's public key is, right? All they did was they bounced an email back and forth between Concordia, and now they believe they know what Concordia's public key is. But there wasn't anything special, right? Certificate authorities, so they're not actually authoritative over anything. They don't have any special insider information. If you want to become a certificate authority, you can do the same processes and procedures that certificate authorities do, and you're just as authorized to bind public keys to identities as they are. Okay, so that's the first thing. So certificate authorities don't really know much. I mean, it's not to say that they're not useful businesses. I mean, they know a lot about processes and procedures and keeping servers hardened and keeping keys secret and things like that. So they do have special industry knowledge, right? But it's not actually about the primary thing, which is which keys belong to which people. They don't have any special information about it. They don't have any insight that no one else knows. So in theory, whatever the CAs are doing, you could do yourself. Okay. The only reason we don't do it that way is it doesn't scale. Okay. You can't be like, oh, I'm going to Google. Let me send them a quick email to make sure that they can answer a challenge so that I believe I have their proper public key. And then turn around and do that for every single website that you visit. It just doesn't scale. Okay. Now, of all the three methods that we just looked at, email, HTTP, and DNS, there is one that actually does scale, which is the third one. Okay, so if this, by the way, is just saying that it's more efficient for a CA to do it, so that's why we can't use the same method. But if everyone's going to put their keys into DNS, right? You put a TXT record and you drop your key into it, right? Then users are already checking DNS. Okay, so I already have to go there and get the IP address for a domain that I'm visiting. If the key's sitting there anyways, right, then why don't I just take the key out of DNS and then I don't have to bother with certificate authorities or certificates or anything like that. Okay, so we can completely eliminate certificate authorities. So there is a proposal called DANE, which is essentially this. There's a prerequisite to using DANE, which is this totally does not work if you don't have at least message integrity between the user that's requesting the DNS record and the DNS server. Okay. Otherwise, if there's an adversary in the middle, when the DNS record comes down and it says what my key is, the adversary can replace it with their own key. Okay, so we need like signatures or something like that. We don't need full-fledged encryption secure tunnels, but we at least need some signatures on these records. So there's another proposal called DNSSEC that for a variety of reasons it's out there, it's deployed, some people use it, but it's not like every DNS uses DNSSEC, for complicated reasons that I won't go into. But if DNSSEC were ever, or maybe a lighter weight version of it or some alternative to it, were rolled out, then you could start looking at this idea of just everyone just drops their keys into their DNS record and then we're done. We don't need certificates at all. We don't need certificate authorities. We don't need our computers to come with trusted certificate authorities or anything. We just rely on DNS itself. Now, the other thing I'll mention is that DNSSEC does have CAs. So it doesn't quite eliminate CAs. It eliminates all the HTTPS CAs, but DNSSEC works with signatures, and so there's also certificate authorities for the DNSSEC system. Okay, so we, in a sense, we're replacing the hundreds of CAs that we have in the SSL case to the CAs for DNSSEC, but DNSSEC is a lot cleaner. I believe, if I'm not mistaken, there's only two CAs, but they sort of both have to sign. So one is a public organization, which standardizes a bunch of internet stuff, and the other one is, it's not the IETF, which does the standardization. It's related to them, and they do they control keys and things like that. And then VeriSign, I think, is the other one, which is just a private company, but they've been in the CA business since almost the very beginning. They were one of the very first CAs, and they're one of the highest profile CAs. And so I think that you only have those two CAs in this system. Okay, so that's just for your interest. It's something that might change over time, but for now, we don't have DNSSEC, so this isn't really an option, or we don't have wide adoption of it, and so we're not doing this at this time. Okay. Something I just said is that certificate authorities are not really authoritative, or they don't have special insider knowledge about whose keys own what. They rely on DNS working right and emails working right and things like that in order to figure this stuff out. Okay. The other thing is that sometimes we think of SSL, secure tunnels, TLS, HTTPS. We think of those as like kind of pure cryptography. Okay. A lot of the internet works on passwords. Right, you're sending passwords for this and you're sending passwords for that, okay? But when you go to HTTPS, you're using encryption and signatures and you're using keys, okay? But if you really study the model and you consider all the ways that you could break HTTPS, you have to include how you get these keys, signed off by CAs. You have to consider the PKI problem, right? And when you consider the PKI problem, you realize that under the hood, these CAs are they're just using other protocols. They're relying on DNS and HTTP and email and things like that to work correctly. And a lot of this stuff is protected by passwords, right? If I can get into your inbox, right, because I have your email password, then I can get a certificate for you and I can impersonate you. And it doesn't matter that you're using pure cryptography, right? I've completely broken HTTPS just by getting one password to your email inbox for admin at your domain. Right? Or if I can get the email for your DNS registrar, then I can point your domain at me. I can point your MX record at me. I can answer those challenges when the CA sends them. I get a certificate for your domain. And now all the guarantees of HTTPS don't mean anything because I can end the tunnel at me instead. Okay? So even though there's a lot of cryptography involved, when you look at the full scope of everything that needs to be protected, if you look at the full scope of every attack that's possible, which is what we're doing in an attack tree, you'll see some of these attacks, the leaf of the node is just, guess or steal a password, right? If I steal this password, then I can do email validation. Then I can get a DV cert. I've subverted the issuance process. I have a valid cert for your website. And now that I have a valid cert, I can get the tunnel to end at me. And then I can ultimately achieve the goal of intercepting all the traffic that's sent over HTTPS between any user and your website, assuming I'm in the middle. Okay. So if we put all this into an attack tree, you'll see, so we have, let's start here. So these are all the ways of obtaining a valid certificate. So I could break a CA, so like the DigiNotar Komodo examples. I could break the issuance process, so I'm not necessarily stealing the key, I'm just breaking the issuance process. If it's EV, then I'm doing some sort of social engineering attack. I'm trying to convince them that I'm a network administrator for Concordia, even though I'm not. And if it's a DV certificate, then what I'm doing is I'm breaking, for example, the email-based validation using any of these attacks that we just talked about. I won't go over them again right now. Other things I could do is instead of breaking a CA, I could just go over and say, I'm the government, give me a certificate. You're operating in my country. Or there's another branch of things that I didn't have slides about, but there are a bunch of, I'll say a few words about them now. This idea of getting the tunnel to end, somewhere in the middle between the user and the website they're trying to visit, right? We think of that as an attack, but there are some scenarios where people do that and they don't do it for attack reasons, they do it for legitimate reasons, okay? So there's two good examples of it, maybe three. The first is that an organization might do it because they want to monitor traffic, perhaps for benign reasons, like they're just watching for malware going in and out of an organization, that type of thing. Okay, so what they can do is they can get a box that sits in the middle, like a server, middle box we call it, and all the traffic is, they'll network, they control their own network, so they'll make sure all the network traffic routes through that box. Okay. And in order to break the connection in the middle at that box, they have two options. Okay, option one is they can, if they're an organization that's issuing computers to their employees anyways, what they can do is they can put a custom root certificate for their own CA a CA that exists on this box, on this middle box. So the key for this CA is on this middle box. They put a root certificate into all their employees' computers, and then they give you the computer. They tell you don't to change it, and and they don't give you admin rights on the computer and things like that. And now all your traffic, let's say you go to a website that no one in your company has ever visited before. You go to Google for the first time. You're the first employee ever to go to Google, right? What the middle box will do is it will say, oh, this person's trying to go to Google. I'm going to mint a fresh certificate for Google out of thin air, and I'm going to send it back, but it's going to have my key in it. And so I'm going to control that. Okay. And then what it will do is it will, on the back end, it will open a connection between it and the real Google, and that will be negotiated using Google's real key itself. Okay. So it breaks it in the middle. All right. Now, other types of things that do this are antivirus software. So if you have, this wouldn't happen across a network. It might happen just within your local computer. So I have a computer, and the tunnel is actually getting broken before it even leaves my computer. So all my traffic goes from my browser to the antivirus software. I have a secure tunnel between, for what it's worth, I have a secure tunnel between my browser and my antivirus, which is running on the exact same computer, right? And then the antivirus will create a tunnel from it all the way to the server, all right? And it's decrypting everything in the middle. Okay, and then parental control software can work the same way. So if I'm a parent and I install it on my kid's computer, or maybe I install it on my network and then install a root certificate on their computer, then I can intercept this traffic that's going over HTTPS, and the software can look at it and make sure that it's not, it complies with whatever the family rules are about things that you can do on the internet. Okay, so these are all problems. Now, there are security concerns with this, besides the obvious one, which is that you now have someone that's intercepting your traffic. If someone breaches that particular server or that software, right, now they have access to everything. And the other thing is you don't know anything about how basically about the second connection. So I know, because my browser is negotiating the connection from me to the middle box, I know what that connection looks like. I know all the crypto that's used. I know it's using TLS 1.3, the newest version. I'm very happy about that connection, but I have no idea what that thing is doing when it's sending my traffic to Google. It might be negotiating a terrible connection, right? It might be using old versions of the protocol, or old versions of cryptography. It might not even use encryption at all. Like I just have no way of seeing it. I don't know what it's doing. Okay. And so a colleague at Concordia, Manon, has a bunch of papers on getting a bunch of these things and studying them and trying to see, all the things that can go wrong when you use it. So I'll refer you to that. The other thing that happens, this is another story. This is a story, but there was a security researcher, and he went to one of these big security conferences where there were lots of vendors and they had set up booths. And he went to one of the booths and he got talking to the people that were running the booth. And they said, oh, we do this. We build these middle boxes for corporations. And, you can intercept traffic that's in the middle. And then the researcher said, okay, that's good. But he was sort of pretending to be like someone that might be interested in buying it, and said, I don't really like this software because you have to go change everyone's computers, right? We have all these employees. They already have their computers. I can't have them bring all their computers in and put this like root certificate on all their computers. And the person selling the system said, oh, no. You don't have to do that. It just works, you don't have to do it. And the security researcher, tried to press on details, but the person, they didn't even really understand the details themselves. And so the security researcher said, okay, I got to get one of these things and figure out what it's doing. So he went and obtained one. And when they reverse engineered it and looked at it, they realized that actually what happened is that one of the CAs gave this company an intermediary CA. So they gave them a certificate so that this company could be their own CA. And they put that certificate into this piece of hardware that you could buy. So you're basically buying hardware that has a CA certificate, not just the certificate, but like the the private key for issuing certificates is hard-coded into this machine, right? And what it would do is it would actually create certificates that already chain back to a certificate. You didn't have to put a custom root in anyone's computer. It chained back to an existing root certificate that was already there. Okay. Now CAs are not supposed to do this. They're not supposed to give out certificates for this purpose. And it's very dangerous to put this in a piece of hardware and sell it, because if anyone can get that key out of that hardware, then they can be their own CA and impersonate any website. So there were actually, I guess, a bunch of middle boxes that had this. They got caught. The browsers, cracked down on the CAs that had issued these in the first place. I think in most cases they removed those CAs, so they're no longer CAs today. Maybe sometimes CAs are kind of deemed too big to fail, and so they get scolded, but they don't actually get removed. But anyways, that was kind of like a big deal when it happened. Okay, now let's say that I get a certificate and I'm looking at it. I want to make sure that it's valid. And there's a bunch of checks that I'm going to do. I'm not going to give you a complete list of all the checks, but I'll give you some of the major ones. And the reason I'm giving you these ones in particular is because I have a story for more or less each of them. Okay, so the first thing that we all know is when you get a certificate, now we all know it, we look at it and we see that it traces back to a root certificate. So the certificate was signed by CA, and that CA was signed by another CA, and eventually we find a CA that signed everything that is in our computer already. It's already hard-coded in our computer. Another simple thing is if Concordia.ca is saying, "Hi, I'm Concordia.ca, here's my certificate," that certificate better be for Concordia.ca, right? If you go to Google, like say I have a certificate for my domain, which is pulpspy.com, and I'm in the middle of your connection between you and Google, and you say, "Hi, Google, I want to talk HTTPS," and Google says, "Great, here's my certificate." I just replace that with my certificate for pulpspy.com. Right? Will you then start sending traffic to Google that's encrypted for the key in my domain? The answer is no, because my domain is different than the domain that you're trying to connect to. You're trying to connect to google.com. You're getting a certificate for a completely different domain. That certificate doesn't mean anything as far as that connection is concerned. Okay? So it's a simple thing, but you got to check it. We mentioned that what happens if... again, let's say I actually have a domain, say I pulpspy.com. What happens if I go start issuing certificates for, say, google.com and facebook.com that chain back to this certificate, right? So I have this certificate. It does chain back to a root certificate. So why can't I issue certificates? And now I'm just part of the chain, okay? And so the answer is that whenever a CA gives you a certificate, there's a flag that says you're not a CA. It says CA equals false. And when the CAs have their own certificates, they have this flag set to true. Okay. And so you can see this. It's called basic constraints. It's one of the things that's in all those details about certificates. So you can see Concordia certificate. It's not a certificate authority, which means it can't issue further certificates down the chain. It can try. It can do it, but your browser should reject it, because when it starts chaining back, it will eventually hit this certificate. It will say, hey, this certificate's in the middle of the chain. Therefore, it's a CA. It's acting like a CA. But when I go look at the certificate, I realize that the flag for it to be a CA is set to no. Okay? And again, Concordia can't flip that flag. What if I just write yes in there? Well, it breaks the signature. So Global Sign signed off on this certificate. And so when Global Sign signed off on this certificate, they made sure, or they were the ones that wrote in no for certificate authority. So Global Sign's only going to sign off on non-CA certificates and give them out as site certificates. Okay. Now, if I go up one in the chain to Global Sign, then I see that the CA flag is tagged as yes. Okay. There's certificates don't last forever. I think I mentioned this in passing. Usually they have a shelf life about 1 year or 2 years now. It used to be longer. And There's also what happens if you lose your key. Let's say you wake up and you realize that someone broke into your server and they stole your key, and now they could be out there impersonating you. Can you do something about that? And so the answer is yes, you can try and revoke that certificate or advertise the fact that that's no longer a valid key for you. And we'll think about a bit about how you do that and whether it works very well or not. It turns out it doesn't work out very well. Okay, so let me do some stories that connect to these issues. Okay, so this is an older story. It goes back to 2014. This is an implementation issue. Again, it was a pretty famous one when it happened. It was a problem with Apple's library for SSL. So Apple's library is called Secure Transport. That's the version number there is the one that was vulnerable, plus earlier versions, I'm sure. And the whole thing is called go-to-fail. Okay, so this is like really, really loose code, pseudocode, high level, but it will give you the sort of the concept of what's happening. Okay, so we have some code, and what this code is doing is it's checking those conditions on a certificate. So I mentioned there's all these things that you have to check. There's lots more, by the way. This is just some highlights of things that you need to check. And that's what this code is doing. So it's basically saying, okay, I'm going to check condition 1. And if it fails, then I don't need to check condition 2, 3, or 4. I can just quit early because once it fails, it's going to fail. So I'll go down and I'll fail. Otherwise, I'll keep going. I'll check condition 2. I'll check condition 3 and 4. Okay. Now the code was written in a slightly weird way. So what happened is they had a variable called check, and it held an integer or a Boolean. So either 0 or 1. 0 means everything's going well, and 1 means that it's an error. So it's like a flag for an error. Okay, so what they would do is they would check condition 1, and they would write whether it passed or failed into this variable. And if the check was flagged for an error, then what they would do is they would go to fail, which means you skip all these lines of code and you go down to the bottom, and then the bottom would just return this variable check. So whatever code was calling this would get back a 1, and a 1 means there was an error. Okay. Now, if the condition passed, it would write a 0 in. Because check is not equal to 1, it's equal to 0, meaning it's passing. We skip this line, go to fail, and then we go to the next line of code, which is going to check condition 2. Same thing. So it writes whether it passed or failed into check. We check whether it failed. If it failed, we go to fail, and if it didn't fail, we skip the go to fail, and we go to the next, checking the next condition, onward and all the way through the code. Okay, so this is roughly the structure of how the code worked. Okay, now the code that's on the slide is fine. There's no problem with the code that's on the slide, and the code on the slide is not the code that was in Apple. Okay, this code that was in Secure Transport was very, very similar, but it just had one line difference, which is that in one of these conditions it had an extra go to fail. Okay. So that's it. So it looked like someone maybe made a copy and paste error. They were copy and pasting a bunch of stuff, and they accidentally put in an extra go-to fail. Or it looks like someone was being very, very clever, and they knew that this is the kind of thing that wouldn't, raise alarms, but is actually a very devastating thing to do. Okay. So let's think about what this extra go-to fail does. So let's assume that condition 1 passes. So check is not equal to fail or error. So we're going to skip go to fail. We're going to check condition 2. Okay. Now let's say that condition 2 also passes. So we write pass into check. Check is not equal to 1. So what we do is we skip something. Okay. The idea is that we're going to skip and go down to the checking condition 3. Okay. But what does this extra go to fail happen? What happens? What's the extra, what's different about this code now that we have a second one? Okay, so when check is not equal to 1, okay, so it's not equal to an error, we're going to skip the if condition. Okay, So we're going to skip the if condition. The question is the if condition go to fail the first one, or is it both of them? So are both of these under the if, or is it just the first one? And the answer may have to do with the programming language. So some programming languages might say, well, it looks like both of these are a condition because they're both indented. And other programming languages will say, if there were curly brackets here, right, and the curly brackets included both of these lines of code, then we would consider them together. But if there's no bracket here, then we just assume, strictly speaking, the next line is what is under the if, okay? And anything that comes after that is where we skip. So we just skip the next line, and then we go on to the line after that. All right, and so the programming language that this was written in, Objective-C, I think, I'm just guessing because that's what Apple uses, was such that that the thing under the if condition was just the go-to-fail, the first one. Okay, so the fact that there was a second one here means that this is the next line of code that you execute. Okay, so let's take this from top to bottom with that in mind. Condition 1 passes. Check is not equal to 1. It's not equal to an error. So I skip go to fail. I go to check 2. Check 2 passes. Check contains 0 because it passed. Check is not equal to 1. It's equal to 0 because it passed. It's not equal to an error. So I skip the next line of code. The next line of code says go to fail. So I go to fail. And when I go to fail here, I return. Notice I don't return, oh, it failed. You know, even though like I should only hit go to fail, but what I return is the value in check. What's the value in check? Well, it passed condition 1 and it passed condition 2, so there's still a 0 in this variable check, and so it's going to return a 0, meaning that the whole thing passed. Okay. Now the key point is that because of the second go to fail, I can never reach these lines of code. Okay, it doesn't matter. I fail here. If I fail in condition 1, you know, then I go straight to fail. If I fail condition 2, I'm going down to fail from this first go to fail. And if I pass conditions 1 and I pass conditions 2, then I go to fail because of the second go to fail. I'll never check condition 3 and I'll never check condition 4. Okay? But what if condition 3 and 4 are really important? What if they include things like, hey, you just gave me a certificate. I see the certificate is pulpspy.com, and I'm going to facebook.com, right? Is this a valid certificate for that website? That's the kind of thing that could be in condition 3 and was indeed in condition 3 or 4, one of the conditions that was unreachable in this particular library. Okay, so what was happening because of this extra go to fail is it was skipping some critical checks. And one of those checks was just, does the certificate that's being presented even match the domain that I'm trying to visit? And because that was skipped, if everything else about the certificate was valid, what you could do is you could use any old certificate that you had that was still not expired and was actually issued by CA, et cetera, and you could use it to impersonate any website on the web, assuming that the user was connecting using Apple's secure transport. Okay, so this was bad news. Some people said, okay, how can we prevent this in the future? So you can always write better code, obviously. And then what was interesting to me is lots and lots of people came out of the woodwork and they said, oh, you know, we have these tools, these automated static analysis tools, and you put your source code in. And Apple's source code isn't always open source. Not their whole operating system isn't open source, but some of the components of their operating system are open source, and this was one. So you could actually get the source code for this. And so people are like, we took their source code, we ran it through our static analysis tool, and our static analysis tool flagged it. It said there was a problem here. You know, what's going on at Apple? What's wrong with Apple? Why aren't they, you know, using tools like this? Otherwise, they wouldn't have made this embarrassing mistake. Okay, and that tells half of the story. So I don't doubt that their tools were flagging it. The problem with these static analysis tools is that they also flag lots and lots of stuff that are not errors. So you get a whole bunch of flags on a whole bunch of stuff, and then it's like you need an engineer anyways to go through and try and figure out which one's a real one and which one's some sort of false positive. especially this in terms of the state of the art in 2013 or whenever this happened. Okay, so that's probably Apple probably was using static analysis. It was just it returned so many false positives that they missed the fact that this was not actually a true or a false positive. A better approach is to do unit testing. So unit testing would be you have a bunch of certificates and you know they're bad, and you just run them against your library and you see whether it rejects them or not. And so somewhere in your pile of bad certificates that should never be accepted would be a certificate that was for a domain that's different than the domain that you're trying to visit. If you run that certificate through the library and it fails, then you know there's an error. You don't necessarily know what line of code is causing that error, but you know that there's something wrong with that library, and then you're going to go digging and try and find out what it is. Okay, so that's a much better approach. And what researchers did around that time is they said, oh, that's such a good approach. Why don't we actually do that? Why don't we go grab a bunch of SSL libraries and we'll come up with all sorts of weird bad certificates, and we'll just try them and see if we can find other cases of bad certificates that are accepted by these libraries. And what we can do is we can make the certificates really, really weird. Like we can put code in instead of data for fields, or we can do random things, or we can have certificates that just sort of end early, or we can take a bunch of certificates and kind of blend them together, like take a piece of this certificate and blend it with a piece of this certificate. Like computers can generate this stuff so fast, we can try all sorts of weird combinations. We can try a million combinations a second. We can maybe find some interesting things. So that general approach is called fuzzing. Where you take something that's valid, but then you fuzz it. So you make a bunch of invalid variants of it. And then you just unit test the code. And if you find something that works, that passes when it shouldn't, then you can dig into the details and figure out why. And then usually you can write like a clearer rule. It's not just like, here's some weird certificate that passes and we don't know why. You reverse engineer out why, and then you also can fix it as a result. Okay, so there were a bunch of papers on kind of like fuzzing, or the idea of combining different certificates was called Frankencerts, and running them against libraries. And these researchers found lots of vulnerabilities, and we're all the beneficiaries of that research because the libraries got fixed. And so now they're pretty robust even against weird certificates. Okay. Another thing I mentioned, I think twice now, is what if you have a site certificate, a valid certificate, and you just pretend that you're a CA even though you're not, and you just start issuing certificates. So I have a certificate for pulpspy.com, and I just start creating Google certificates, and I sign it with the key that's in my pulpspy.com certificate. And then my pulpspy.com certificate chains back to Let's Encrypt, and Let's Encrypt's a root or it has access to a root that's in your computer, right? Why wouldn't you accept that as a valid Google certificate? It traces all the way back. And the answer is that one of the links in the chain, which is my certificate, is not a CA. So I wasn't allowed to issue certificates. I was allowed to be the last certificate in a chain, but I wasn't allowed to be a middle certificate in the chain. Okay, so we need to check that that's true, that all the middle certificates in a chain have the CA equals true field set. And would you believe it? Some libraries didn't actually do that check, even though it was really basic. Okay, so one was Microsoft Internet Explorer in 2002. It was discovered that they didn't do that basic check. Okay, now everyone said, "Oh, that was dumb, bad implementation error." Now we know that. Well, no one's ever going to do that again. Okay, then Apple came out with a brand new invention called an iPhone, and for whatever reason, Apple decided that, hey, instead of using this, operating system that's been running on MacBooks forever and maybe scaling it down for our phones, we're going to rewrite a complete operating system again. Okay, we're going to write an operating system from scratch called iOS. And that means we're going to redo all the SSL. We're going to redo the browser, everything. Okay. And so they have this brand new library. Guess what they forgot to check, right? They forgot to check whether certificates, all the certificates in the middle of a chain were actually CAs or not. And then everyone said, okay, that's dumb. Fool me once, fool me twice. Then we have all these IoT devices that start coming out like around 2000, COVID times. And again, they're rewriting operating systems, right? They can't run full scale anything, maybe a scaled down version of Linux or something. But, they're for a lot of times they're either doing a custom operating system or they have some scaled down version of Linux that doesn't have an SSL library. And so they're writing the SSL library for that scaled down version. And they're doing it from scratch. And again, they're not checking this field. Okay. But the good news is, of course, it's not going to happen again, right? Okay. Another thing you could do is you could just do it anyways. So what happens? Okay. Let's say that this vulnerability doesn't exist and you just start issuing certificates that you shouldn't issue. Let's say you're not even a CA. I'm not a CA, but I'm just going to create certificates. When I see people trying to connect to Facebook, I'm going to drop my certificate in, and that's it. It won't chain back to the trusted root store, right? So what's the browser going to do? Are they going to close the connection? Are they going to reject it? Like, what exactly happens? And so the answer for a long time, by the way, this happened. There's a real life example. But the answer is that actually what the browser would do is it would say, you know what, we're not like confident enough to reject it. We actually want you, the user, to decide what you want to do. Maybe there's some reason why you want to go to a website that doesn't have a valid certificate. Okay. And at the time, there were people who didn't believe in paying money to CAs to have their certificates signed. So they would run websites and they would just have self-signed certificates that didn't chain back to anything. Okay, so browser said, well, we'll just let the user decide. And so they would show them a warning that looks something like this. Okay, so there's a problem with this website certificate. Do you want to click on the green thing and go to the website you're trying to go? Like, imagine someone that doesn't know anything about security. They barely know how to use a computer. They just want to check Facebook, right? And they see this. They have no idea what it means. And they know if I click the green thing, I can go to Facebook. And if I click the red thing, I can't. What do you think they're going to do? Right? Well, you don't have to guess. There were some studies, usability studies, and they found that lots of people are not going to click the red thing. Most people are just going to click the green thing. Okay, they're just going to go to the website anyways. All right. And so then researchers, particularly at Chrome, they sort of led the charge on this. Is they said, okay, well, what's going wrong here? So they said there's probably two things that are going wrong. The first thing is no one can understand what this means, right? It's actually not that confusing, but I've seen worse ones where like it's just a bunch of technical jargon and you can't really understand, like I don't know what a certificate is or a certificate authority or anything like that. Okay, so if we're going to do this, we need the user to really understand what they're doing. So when they're clicking here, they understand what they're clicking on. And secondly, we shouldn't make it quite so easy to click, right? It's very easy to just click the green thing. In fact, the fact that it's green as opposed to red, it almost, makes you want to click on it without even reading it. All right. So what Chrome did is they proposed, okay, let's fix the language. So first off, the language is a lot better. Your connection is not private, period. Okay, X, no bar. Okay. Attackers might be stealing your information. For example, passwords, messages, and credit cards. Okay. So this doesn't say anything. The word certificate isn't in this anywhere. The word certificate authority isn't in this anywhere. There's no talks about keys or anything like that. Doesn't mention SSL or TLS or HTTPS, none of that stuff, right? So it's very straightforward. It's easy to understand. And you have a big bar that says back to safety, and there's no option to just continue onto the website otherwise, unless if you clicked on advanced. If you click on advanced, then this second thing appears. Okay. And now it gives a little more technical detail because this is advanced. Okay. So it notes that maybe it's a misconfiguration. So we are acknowledging that maybe you want to go to the website anyways. But it could also be an attacker intercepting your connection. And if you really want to go to the website, now you can click on this. It will take you to the website, but it's very clear that it's marked unsafe. Okay, so this warning, the change from this to this, didn't take anything away from the user in terms of their freedom or their right to go to websites that have invalid certificates. but what it did is it really tried to clear it up. Okay. Then they did a bunch of user studies and they proved that users do the right thing more often when they see a message like this. So warning screens have improved since 2011. 2011 being this one, not this one. Again, I mentioned this website again, badssl.com. So you can try it yourself. So if you want to go to something that, for example, is self-signed, or let's put untrusted root. This is what Safari says today. So it says this website may be impersonating this website to steal your personal or financial information. You should close this page. This connection is not private. So you can see the language is almost the same as what Chrome tested, just slight variations. And I can close page or I can show details. So I have no option of continuing to the website from this. If I want to continue, I have to first click show details. Then it gives me a bit more technical information. Then it asks if I want to look at the certificate. And then it says, if you understand the risk involved, you can visit this website anyways. And then if I click on it, there's yet another warning. And it just says, are you sure you want to visit this website on a connection that is not private? Okay, so very clear this isn't a private connection anymore. Then if I click through, eventually I can get here. And now I'm on this. Now, interestingly, it's not saying not secure up here. Okay, so because I approved it basically and said that, I'm fine with this certificate, it's now saying, okay, you do have a secure tunnel to this website. It's just based on the fact that you click through a bunch of warnings in order to get there. Okay, and then the website has other variations on other things that can go wrong. You can look at it at your leisure. Okay, here's another kind of thing that could go wrong. So this is sort of a weird attack, but I thought it was okay. It's called a parsing error. Let me just go through the details itself. Okay, so what happens is you go to a CA and you say, I want a certificate for a certain domain. I want it for pulpspy.com, and the CA is going to say, okay, we're going to send an email to admin@pulpspy.com. Okay. Now, what if you go to the CA and say, I want a domain name, and here's the domain name. The domain name is, I want a certificate for a domain, google.com null character.concordia.ca. Okay. Now, the CA, when it looks at this domain, again, this is automated. So this isn't, a human's not looking at it saying that's weird, right? This is computer code. It's just parsing this string. And parsing is kind of difficult. Okay, there's lots of different rules, and we know that different code might parse strings differently in special cases. Lots of strings that you see are pretty well structured, but this one's a little bit weird. So how am I going to parse this string? What am I going to do? Okay, so there's basically, the way I see it, there's maybe more, but there's three basic things that my code would do. Okay, the first thing it would do is it would say, I see a character in there that I don't recognize. It's not a proper Unicode character. And so I'm just going to reject it. Let's just stop this process at this point. Come back to me later if you have a proper string. Okay. So that would be great. That's what code should do. Okay. However, some CA's code did not do that. Okay. So some CA code tried to process it anyways. The second thing is it might look at this and say, I don't recognize that character. It's an invalid character, so I'm just going to drop it from the string. Okay, so if I drop it, then what I think you're asking about is google.com.concordia.ca. Okay, is that a valid URL? It's kind of a weird URL, but there's nothing invalid about it, right? It's owned by concordia.ca. Com is a subdomain of Concordia, and Google is a subdomain of com. So it's google.com.concordia.ca. It's not that much different than users.encs.concordia.ca, which is where a bunch of websites are for professors. So it's just a subdomain of a subdomain of a domain. Okay. And the person that controls that is concordia.ca. All right. Now there's a third option, If you've looked at programming languages that are very lightweight, things like C. So a lot of programming languages, say Java, if there's a string and they write it to memory, they're going to say that it's a string, and they might have the length of the string and things like that. So they don't just write the raw bits of the string. They also like encapsulate it in the concept that it is a string. And they put that into memory. And so when you pull it back from memory, you're very clear about what you're getting and how long it is and things like that. Okay, C doesn't work that way. What C does is it just says, you want to write a string to memory? Great. Give me the first location in memory where you want me to start writing the string, and I'll write it there. Okay. Then later, when you go back to read the string, same thing. You just get the memory location, you jump to memory, and you just start reading the string. Now, the problem is, how do you know when to stop? Because memory's full of a bunch of things, right? There's not just your string there. And so what C says is, well, we don't know how to stop. And so this is what we're going to do. We could have the length, but then we'd have to encode it, and then strings are going to take up more memory because we have the length of the string. So we're just going to have this convention that if you want to end a string, you write a null character as the next character, and then that's considered the end of the string. Okay, so we call it a null terminated string. So it's something that some programming languages use. Okay, if you were to look at this and your code was using that convention of null terminated strings, it would think you're asking about google.com, because it would hit the null character and then it would just stop reading the string. Okay, all right. So here's the three options. We could just reject it. We could drop the null character, in which case we think it's google.com.concordia.ca, which is a subdomain of concordia.ca. Or we could read until we hit the null character. Then we could terminate the string. Then we think the person's asking for a certificate for google.com. Okay. Now, the problem here isn't which of the three that you choose to do. Okay, so it doesn't really matter. You can do one, you can do two, you can do three. They're all sort of valid approaches. One is probably the safest, right? But these two are fine in and of themselves. There's no attack if everyone does two and if everyone does three. Okay, but notice I said if everyone does. The problems arise when some people do one or two or three, and some other people do a different one. Okay. So in particular, let's consider one scenario. Let's consider the scenario that the CA is doing number two. They're dropping the null character. And the browser, when the browser receives the certificate when they're trying to connect to the website, they see the same string in the certificate. And when the browser sees it, it's programmed, say, in C, and so it thinks it's a null character, so it terminates here. Okay, so what that means is I go to the CA and I say, I want a certificate for this. And it says, okay, you can have it if you're concordia.ca. Let's say I am concordia.ca. So now I have this certificate, this weird certificate on this weird string, right? But I was able to get it because I was able to prove I was concordia.ca because the CA was dropping that null character. But then I see someone going to google.com and I want to intercept their traffic. I drop in this certificate with this weird string, and it gets sent to the user's browser. And the user's browser is different. It's going to parse it as three. It's going to consider it null terminated. And it's going to say, okay, I see a certificate. This is a certificate for google.com. Okay. And so then it's going to accept that as google.com. Okay. And so concordia.ca, you can replace, the adversary can replace it with their own domain. And the thing that they put out in front can be all the common domains that they might want to intercept traffic to. Okay, so this effectively is, you can use it like a Google certificate, even though it's a Concordia certificate, depending on how people parse it, kind of thing. Okay. Okay, the next topic I want to talk about is revocation. So let's say that you are Concordia or a server. You lose the key, the long-term key that's in your certificate. Now anybody that has that key can impersonate you. Okay, so they can basically essentially read the connection, all the information that's in the middle. So what do you do in that case? So you might say, okay, well, I'll just make a new one, right? I'll stop using this old certificate. It's compromised. I get a new one. Okay. Does that solve the problem? Well, from your perspective, it does. But in terms of the adversary's perspective, what they can do is, let's say Alice connects to you, you send your new certificate. What they can do is they can just drop in the old certificate, right? And then you'll end up using the old certificate yourself because you don't know the difference. You don't know that there's a new certificate, okay? So as long as that old certificate is still valid, then you can still use it as an adversary in the middle in order to in order to do a man-in-the-middle attack. Okay, so it's not enough to just get a new certificate. You also have to cancel the old one somehow. Okay, so that's what we call revocation. So revocation is the term for canceling the old certificate. Okay, so how are we going to do this? How are we going to revoke a certificate that's already out there in circulation? Okay, and notice the only way we can really revoke it is Alice has to know that it's revoked. Okay, so somehow Alice has to learn that information. If she doesn't learn that information, right, then she'll never know that it's been revoked. So there's essentially two options, and neither of them are that great. I should say actually there's probably more than two options, but there's two options that are used in practice. Okay, so the first one is called a status check. Okay, and this is the idea. So the idea is that when Alice connects and gets the certificate, she's holding the certificate now in her hand. Before she fully trusts it, she does all the checks on it. It's valid, it's signed, it traces back to the root authority or whatever. So there's nothing wrong with the certificate itself. But before she says, okay, I'm finally done checking this, she does one final check. The final check is she'll ask someone, is this certificate still valid? I see that it was valid for sure, right? But as of right now, as of this second, is the certificate still valid? Okay, so she'll send that message, and then she'll receive a response that will be yes or no. Okay, so the protocol for doing this is called OCSP, Online Certificate Status Protocol, and the server that you ask for, or that you go and ask whether it's revoked or not, is specified in the certificate itself. So the certificate, in one of those fields, remember there's a whole bunch of fields in a certificate, one of those fields will have the OCSP responder, which is the server that you can access. Okay, so what you'll do is you'll basically just send, say, a fingerprint, like a hash of the certificate, to this URL. And then this URL, this would be for a Concordia certificate, then this URL will respond yes or no. This is hosted by GlobalSign. GlobalSign is the CA that issued the certificate. And so that's what is standard, is that the CA that issues the certificate are the ones that are going to put this up. Okay, so CA's job doesn't start and finish when they issue the certificate. They also are expected to stay online and run a server so that they can field all of these requests about whether the certificate's been revoked or not. And then if there is a revocation and the CA, first off, the revocation doesn't take hold until the CA that issued the certificate realizes it. And once they realize it, then they can change the responses and start saying, yeah, this actually has been revoked. So let's say that, you look at this whole CA business and you're like, wow, there's a lot of money to be made, issuing certificates, and I don't have to do that much work. I just have to send some emails to admin@domain.ca, and then I have this server there that's running, that's responding. Okay, and so you're like, I'll do it for almost free. I'll and you undercut the market. Now, technically today you can get free certificates, so you can't undercut the market anymore. But just for the sake of a story, now Google, Facebook, Twitter, well, X now, they all come to you and say, great, we want you to be our CA. Okay, and so you're really, really happy. Okay, but what happens? Okay, what happens is every single time someone goes to google.com, they do it securely. They get a certificate for google.com. Now they're coming to you and they're saying, has this certificate been revoked or not? So for every visitor to Google, which could be, I don't know, tens of millions a second. I don't know exactly how many they get. They get a lot, right? All of that traffic is now also coming to you, or at least one packet of it is coming to you, asking you about these certificates, okay? Plus all the traffic to Facebook, all the traffic to Twitter, all right? So you're going to have a pretty robust service in order to answer all of these requests. And it would be very easy if you weren't prepared to get overwhelmed by all of this traffic, okay? And so these OCSP responders getting overwhelmed by traffic became just the standard story of the internet. So what would happen is you would connect over HTTPS, you get the certificate, you would try the response, but most of the time, every now and then you would actually get a response, but most of the time you just wouldn't hear back. Okay? So what do? Let's say you're a browser. What do? So you have two options. You could say, well, we're going to throw an error or a warning or something like that if we don't get a response back. Okay? But the problem is that this is happening 90%, 99% of the time users go to any website. And remember that just because you go to one website, it's usually weaving content in from lots of different websites. And so you're doing these certificate checks for all of the resources that are loading on the page, not necessarily just the root page. Okay? And so basically you'd be seeing an error every time, right? Basically every page that you go to, you'd be getting one of these errors. And so browsers said, we can't have that. Okay? And so what we're going to do is we're going to fail open, right? So I remember I mentioned this a few times. We have this distinction between failing open and failing closed. This is another example of a fail open or an opportunistic protocol where you do the revocation check anyways. You just try and do it. But if you don't hear back, then you assume everything is good as opposed to assuming everything is bad. Okay, so you do your best effort. You don't hear back. Then that's it. Okay, so what can the attacker do? Let's say that they have a certificate. It is revoked, right? And the user is checking whether it's valid or not, okay? And the responder is online, and it is responding, and it's saying, no, that's not a valid certificate. What you can do is simply drop that packet. Just never let it reach the adversary. Reach Alice. Alice will sit there. She'll wait for it, for a millisecond or whatever. And then her browser will say, well, I guess I'm not hearing back, so let's just assume it's okay. All right, so this revocation, because it fails open, it basically doesn't solve anything. It doesn't protect against someone that's in the middle because the person in the middle can also drop the response that you get back. Okay, and so this was the status of OCSP for a long time. Okay, recently, as of 2026 is when I'm making the slides, but sorry, these guidelines were older than 2026. They were introduced earlier. But as of today, when I'm recording this, there are guidelines for EV certificates. So remember, EV certificates are the certificates where you check everything about the company and you check that they're that they're a registered business and you get their registration and you put that into the certificate and things like that. Okay. So they're like the sort of high integrity certificates that are offered. And so, there's a sort of agreement. So these guidelines they're guidelines. They're not like laws or regulations. They're not from governments. They're just from a consortium of all the CAs and the browsers, or a lot of them, called the CAB form. So they're not binding, but anyways, there's basically this agreement that if you're going to issue one of these EV certificates and you want to stay on the browser's good side, then what you need to do is you need to make sure that now you do have OCSP responders that are going to be live. Okay. And so the browsers don't really check this for OV or DV certificates. I'm also not sure to what extent they check it, but there seems to be some level of oversight over this for it. Okay. So today, what happens if we have the story that's on the slide? Okay. and Alice sends a request, and now it's one of these ones that that has to respond. It's an EV certificate. Okay, so because it has to respond, it may be the case. I'm not sure if browsers have turned it on, where now they're going to fail closed if they don't receive a response. Okay, so this seems to solve the problem. If we just enforce OCSPs to be live and we fail closed, then there's nothing the adversary can't do, right? But it turns out there's still a little bit that the adversary can do. So there's two things. The first thing is that what the adversary can do is they can get an OCSP response on the certificate that they're about to attack. So they attack a certificate, they steal a key. Alice doesn't realize it yet. Okay, if she never realizes that it was stolen, then they can just keep using it. Okay, but what they do is every now and then they go over and they get an OCSP response for this certificate for Alice, as if they were going and visiting this website. Sorry, I think I misspoke. I talked about Alice losing it, but it's in this case the web server, like Concordia. So Concordia is the one that loses the key. As long as Concordia doesn't realize that their key has been stolen, they won't ask for it to be revoked, and the adversary can continue using it. At the moment they realize that it's been stolen, they report it as revoked, and the CA decides to update the status. Okay. Now, when you ask about that certificate, you'll get, no, it's not a valid certificate. All right. But what the adversary can do is they can say, is it valid? Is it valid? Is it valid before it's revoked? Okay. And they'll get yes, 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 yes back. And they can record those yeses. Okay. Then what happens is it's revoked. Now the server's saying no. Okay. But they still have some of those old yeses that they got from the server. All right. So when Alice submits, is this still valid? And the responder says no, what they do is they substitute in one of the old yeses and they send it off to Alice. Okay. Now these responses have a time window. Okay. So they're not going to be like if you ask about a certificate and you get something that says yes, it's valid. That's only going to be valid for, I'm not actually sure what the time shelf life of that is, but it might be an hour or two. But the point is that you can extend the time that you have in order to conduct these attacks by just replaying these old ones. Okay. Now, these responses are digitally signed. Okay, so they're digitally signed by GlobalSign. So you can't flip the no to a yes. Otherwise, you'll break the signature. But it turns out one thing you can do is you can flip it from a no to a try again. Okay. Now, try again is kind of weird because if you're able to send a try again message, you should be able to send a yes or no message, right? You're getting a packet and it's coming back. But in the protocol, they do allow for try again fields. And it turns out that this is in like sort of the header of the packet that's not signed. So some of the content of the packet is signed, some of it's not, the headers are not, and this is in the header. And so what the adversary can do is, even though the no is signed, they can turn the no into a try again, and then they don't have to sign it because this field isn't signed. Okay, so it's just like a kind of quirk in the protocol. But anyways, that's something else that the adversary can do. Okay, now another thing you might notice about this URL, if you look at it closely, sort of curiosity, is that this is served over HTTP. Okay, so why is it not served over HTTPS, right? If it were served over HTTPS, then we wouldn't have to worry about someone in the middle changing the response or anything like that. Okay, and so the answer to that question is let's imagine for a second that it was served over HTTPS. What would happen? Okay, so picture this. So you go to Concordia and you say, give me your certificate. Concordia says, here's my certificate. And you say, okay, before I believe the certificate, I need to check whether it's revoked or not. So you look up where you're supposed to go to figure out whether it's revoked or not. And let's say this says HTTPS globalsign.com. So then you go over to globalsign.com and you say, hi, I want to speak HTTPS with you. And you do this before you ever ask it, like, is the certificate revoked or not? The first thing you have to do is you have to establish that connection, right? So you say, I want to speak HTTPS. It says, great, I speak HTTPS. Here's my certificate. Okay. And you say, okay, your certificate looks valid, but I need to check whether or not it's revoked. So then you go into that certificate, you find its responder, right? And you go to that responder and say, hi, I want to talk HTTPS with you. And they say, fine, we speak HTTPS. Here's my certificate. And you say, well, wait a minute, I can't validate that certificate until I check if it's revoked or not. So then you go and you look in that certificate, you find another HTTPS address, right? And it just keeps going. It becomes a circular dependency. You can never get out of that loop because you can never create an HTTPS connection. You can never finalize it without checking whether it's revoked. And every time you do the revocation check, you're sent to another HTTPS connection that you can't finish until you check whether it's revoked. All right. So I don't know if you followed all that, but there's this circular dependency. And so that's why it's served over HTTP rather than HTTPS. And that's why the adversary can modify anything that's unsigned. Okay. So the way that you sort of get around it is you do a signature. So it's almost like sending over HTTPS. Doesn't have privacy or confidentiality, but it has integrity. But the integrity is coming from the fact that it was signed, not from the protocol itself. But if there's any like fields or headers or things like that that are not signed, you can change them because it's being served over HTTP. Now, there's an alternative to OCSP, which is certificate revocation lists, or CRLs. Here, the idea is that all CAs will just make a list of every certificate that they've revoked. Okay? And what you will do as a browser, or what your browser will do, is it will periodically go over to these CAs, and it will say, okay, give me your updated CRL, and then you keep it. And then every time you get a certificate, you check against the copy of the CRL that you were given by the CA. And if the certificate's not on the list, then that's fine. Okay. Now, the problem with CRLs are, first off, there's hundreds of CAs. And remember, we don't even know of all the CAs because there's these intermediary certificates that you don't really see. So you don't see the CAs that are associated with those. Okay. So you can't really go around to all the CAs unless if you know who all the CAs are. CRLs are pretty big. So they're a couple of megabytes. They can be. So it depends. It depends on how big the CA is and how many things they've revoked. Okay. But getting things that are a couple megabytes, that's something you feel. It's not something that just, happens in the background and you don't even notice it. Okay. Especially on, like, say, a mobile phone or something like that. And you have to ask yourself, how often am I refreshing this, right? Or, maybe this was revoked yesterday. Do I want to know that or not? So then I'm refreshing it every day or every hour, so how often am I refreshing it? And so, yeah. Okay, so what some browsers do, like Chrome, is they just do this automatically for you. Okay, so let me phrase it slightly different. What Google, the company, does is it goes around to all these CAs. All right, it checks whether there's a new CRL, and then what it does is it packages it up in a much compressed format. And it sends it out to all the Chrome browsers in the world. And it does this at some level of frequency. I'm not sure what frequency it does this at. I think it's probably on the order of days, but I should check that detail. So the thing that you get is called CRL set. And it's basically a slightly, or not slightly, it's quite a bit more efficient than downloading the raw lists themselves. Okay. And this just happens. You don't have to auto update your Chrome or anything like that. It's just like some data that's sent between Google and Chrome. The problem with this is that it's very incomplete, or at least historically it was. So it was really there for emergency cases. Like there's really high profile breaches. We want to make a list of those in the browser. I don't think Google ever like intended for it to fully solve the revocation problem. There was some studies, but these are pretty old now, like over 10 years old, that indicated that like something like, the majority, like say 3/4 of CAs are not in CRL set. So it covers like a quarter or less of all the CAs in the world. Now, maybe this has changed since then. I did try to look to see whether this is sort of like the coverage is better today. I didn't see anyone who had really studied it. I saw some follow-up papers, but they were also in like 2015 and 2016, and they were basically saying the same thing, that the CRL set wasn't intended ever to be like 100%, and it still isn't 100% as of that time. So as far as I know, CRL set, it's an interesting proposal, but it doesn't necessarily seek out to completely solve this revocation. The other thing is that this is a Chrome thing. So this is something Google does with Chrome. If you're using other browsers, you're not going to have this, probably. Depends if the browser does it, but I'm pretty sure that, like, for example, I use Safari, and I don't think Apple does this. Now, there's a third option that's actually a brilliant solution. Okay, it's the perfect solution to this problem. The thing is, like, go back to the example of you're the CA for Google. Every time someone goes to Google, the very first time anyways, they're going to hit your server and ask about the certificate. Okay, so 10,000 people go to Google in the next second. You get 10,000 requests at your server. What could happen instead is Google could come to you and say, I mean, I know the answer to this already, but can you just confirm for me that this certificate is not revoked, and will you sign that for me? And so what your CA server can do is it can sign it once, give that message to Google. Then when those 10,000 people come and connect to Google, what Google will do is they'll send them two pieces of information. They'll send them the certificate, and they'll also send the fact that your CA server recently signed off on the fact that this is still like an unrevoked certificate, still a valid certificate. And what you'll do is you'll trust that for the next 3 hours. And then in another 3 hours, they have to go back to your server and get another one. So they're constantly, the signed responses are kind of like certificates. Okay, so you have a certificate, but a certificate has a shelf life of 2 years. And then you have this like certificate kind of thing, but it has a shelf life of a couple hours. And so what they're doing is they're refreshing this every couple hours, but still giving it to Google once every 3 hours is a lot better than giving that same response to 10,000 people a second or 1 million people a second or whatever kind of traffic that you get. Okay, so this is great. The only problem with it is that because you're sort of changing the TLS protocol, so you're now sending an extra information. You have this extra thing, this OCSP signed response, and you're sending that down with the certificate. And what some backbone internet routers would do is sometimes they try and look inside the packets and they try and parse things out to try and figure out things about the packet ostensibly to route it better, but I'm not sure all the reasons they do it. But what they would do is they would hit this field. It was unexpected. They weren't expecting to see anything there. And then they would break, like they would drop the packet, or it would cause problems for the machine. I'm not sure exactly what the issue was. But anyways, this happened enough that it wasn't deemed reliable to do this OCSP stapling because there was no guarantee that there wouldn't be a middle box somewhere. Also, I represented it as like sort of the backbone routers. Now that I recall the details, I think it might have actually been the exact opposite. It might have been more like your home routers, your sort of commodity home routers and things like that were breaking. I forget where it was where these breakages occurred. But anyways, the companies that experimented with this included Google, and they just concluded that it wasn't reliable enough. Too many packets got dropped, and so they stopped experimenting with that. Okay. Now, maybe in future years, as we update standards and things like that, maybe this can take a place in those standards, and we can get basically like universal acceptance of this standard. and then it won't be a problem anymore. And this will actually make the world better in terms of revocation. But as we stand today, we basically have option 1 and option 2. Neither of them are great. And so revocation effectively is not a solved problem. So you can't really rely on the revocation that's sitting there today in HTTPS. All right, here's another option. What if you just don't use a certificate at all? Okay, so this was the experience that I would see a lot on the internet maybe 10 years ago, 20 years ago kind of thing, definitely 20 years ago. Things have changed, and I want to talk to you a bit about why they changed. But this is what would happen. Websites would say, HTTPS is expensive, so we don't want to do it all the time. But we also understand that when you put a username and password in, that password is sensitive information, and so we should be using HTTPS at least to connect or sort of collect that password. Okay? So normally what would happen is you would go to a website, and the website would not be over HTTPS. It would just be over HTTP. And then there would be like a sign-in button. And sometimes the sign-in button would have, like, say, a username and a password right on that page itself. Okay? So you could type your password into a page, but the page that you downloaded did not come down over HTTP. It came down over HTTPS. Okay? Then what would happen is you would click the sign-in button, and the page would be coded so that any information put into that field and then submitted would actually go over HTTPS. So the website did the right thing. So effectively, you be on HTTP, you put your password in, you would press submit or log in, and it would transfer you over to HTTPS. The password would go across the wire in HTTPS. It would log you in, authenticate you, and do all the checks. And then what it would do is it would redirect you back to HTTP. So now that you're logged in, you now go back to HTTP. So HTTPS was just for that one window of time for collecting the password. Okay. Now there's a couple problems with this. The big problem with this is, how do you know that it's about to go over HTTPS, right? How do I know if I click that button, it actually is going to go over HTTPS? And the answer is you don't. Okay. There's no indicator in the browser about whether it will or not. The best that you can do is like go look at the HTML for the document itself and try and figure out whether that submit button, is it actually going over HTTPS or is it not going over HTTPS when you submit that button? Okay. Some people thought about writing like little browser extensions and things that would try and give you an indicator, but it never took off. So you really didn't know. Now the opposite, let's say it didn't go over HTTPS, you would get a warning from the browser. We actually just saw it like a couple of minutes ago, maybe a couple hours ago, but we saw that what it looks like. It gives that warning of like, you're about to submit data not over a secure channel. Are you sure you want to proceed? Okay, but generally you don't know what's going to happen. Okay, so this leads to a very simple attack. The attack is that the user basically goes over HTTP, not over HTTPS. Okay, you get the website back. The website has the button programmed up correctly, so it will go over to HTTPS. And what the adversary does in the middle is they try and re-engineer that button so it won't go over HTTPS. So they try and downgrade that button so that it just goes over HTTP. All right. Now you might think, okay, that's a pretty sophisticated adversary. They have to know how this website is laid out. They have to know what these buttons look like. They have to know where to find it. They have to, go there and actually change that button, right? And so that's a lot of work, and that's probably not like a really great strategy. But it turns out it's a lot simpler. So this attack is called SSL strip. And what you can do is you can basically, when you take any HTML file, okay, the reference to the button, the URL that button's hooked up to, has to start with HTTPS. So what you can do is you can just go through the file and you can remove every reference to HTTPS, and you can replace it with a reference to HTTP. Okay, so you're not you don't know what you're doing. This adversary is dumb. They don't know anything about buttons. They don't know anything about the page. All they do is they just go through the website, and every time they see a link to an HTTPS resource, they replace it with an HTTP resource. Okay. Then you're going to start asking for stuff over HTTP. Maybe that stuff doesn't exist. Maybe it's only available over HTTPS, but it doesn't matter because the adversary is in the middle. So if the server starts sending back error messages, the adversary will intercept them and they're not going to pass them on to Alice. Then it will just ask for it over HTTPS. It will convert it to HTTP and then send it off to Alice. So that's what it's doing in the middle. Okay, so the net effect is that once you're on HTTP, okay, you go to this website, and the first time you load it, it loads over HTTP. What an SSL strip adversary can do is they can stop you from ever crossing over to HTTPS. Basically, you'll always stay on HTTP. Okay, so how do you fix it? Now, one thing I'll notice, though, is that if you do collect usernames and passwords doing this attack, the browser will warn you. So you also have to rely on the user clicking through that warning about, are you sure you want to submit information that's not secure? Okay, but that is something that you can click through, and if the user clicks through it, then you're able to intercept all of the traffic. Okay, so the answer or the solution to this is to move the entire website to HTTPS, so that the first thing the user does is they go over HTTPS to get the website. If it's over HTTPS, the adversary can't modify the pages because HTTPS itself is protecting the message integrity of the site, and so it's not going to let the adversary do this attack. Okay, this attack is kind of weird, but I just included it because I thought it was fun. It's also something that's like sort of dated at this point, but I thought I would throw it in. So what are we looking at here? So what we're looking at is we have a browser window, and inside of it, there's what we classically called a pop-up window. And so a pop-up window would actually pop up a new entire window. Okay, this is something you don't really see on the web anymore. In part because of this exact attack. Okay, now if you want to open it up in a new quote unquote window, what it will do is it will open up in a new tab. So you'll have a bunch of tabs open. And that's actually, it solves this problem. You can think about why later. Okay, but anyways, okay, so what I have is I have some website. It launched this pop-up. Pop-up is to paypal.com. You can see the URL. You can't maybe because it's really pixelated, but I'll assure you that URL is correct. It is www.paypal.com. And it has all the indicators that this is an HTTPS connection. Okay, so this picture's a little old. So back when this picture was taken, the indicator that you were on HTTPS was a lock symbol. The fact that it's green means it's a extended validated certificate or an EV certificate. And you can even see that it has PayPal Inc. US here, indicating that this is a secure tunnel, not just to the domain paypal.com, but to the actual company PayPal that's registered as a business in the United States. Okay, so this looks great. Okay, and so imagine here there's a username and password and a login button, right? What happens if you put your username and your password in there and you click login? It should be secure. It's going to go over HTTPS. Nobody can read that password, right? Okay, so there's one problem with this. Okay, the problem with this picture is that this pop-up window is not actually a window at all. What this pop-up window is it's an image inside of the website that you're on. Okay, so you're on this website. It's adversarially controlled. And what the adversary does is they make a picture that looks like a window. It looks like a browser window, but it's just a picture that's on this website. So it's not its own window. It's just a picture. Okay. And when I say picture, you think of a static picture. It's more of, let's call it a rendering. So they rendered this thing to look like a pop-up window. And you can render it in such a way that when you type your username and password here, it will actually type, right? Like these are text boxes and you can type whatever you want in it. You can even like have it like, so if the user clicked on the window bar here, they could kind of drag it around, okay, and it would sort of drag around. But if you ever tried to drag it past the user interface of the browser here, outside of the contents of the website, you wouldn't be able to do it because this is part of the content of this outer page. Okay, so by the way, we call that the Chrome of the browser. So and that's where Chrome gets its name for Google Chrome. But the Chrome of the browser is all the user interface stuff. So like the bar at the top and the scroll bars and the footer bar here, we call that the Chrome. So you have the Chrome and then you have the page content, and this pop-up window is completely contained within the page content. So you can't actually really be sure that it is an actual window. It's not just something on the website itself that looks like a window. Okay? If it's something that looks like it, then it's something that this person wrote the HTML of, the adversary of the outer page. And so they can program this login button to send your password anywhere. So yeah. Okay. So what we do instead is we tend to open things up in new tabs instead of allowing pop-ups. And you still see like abuse along these lines. So what you do is you see like alerts and things that pop up. This isn't uncommon. And it turns out that actually if you code up a website, you're allowed to pop up alerts and you can control the text itself. Okay. Now what you can't control is you can't control the buttons here. Okay. So you can put some custom text here, but you can just have an alert that can be dismissed with okay, or you can have an alert that says stay on page or leave page. Okay. And so when people use this for fraudulent purposes, what they do is they put the fraud into the message itself. So here it's sort of like, like basically what I'm trying to say is whether you click this or you click any of these buttons, you're never going to get in trouble, right? It's just like the adversary pops up a message, they control the text, but once you dismiss it, the message is gone. It doesn't do any damage to your computer. It doesn't matter if you leave page or stay on page. There's no harm in allowing people to customize these messages. So that's why browsers allow it. So what they do is they put it into the message itself. So you'll see like, oh, you have to call this number or you have to go to this URL. It's not like click here and we'll take you directly to the URL. You would have to like read the message and copy and paste it out. So this as a vehicle for fraud, it doesn't work so well, but it is still, examples of pop-ups being abused. Okay, so we finally have reached the end of our attack tree. And so most recently, we were considering this sort of thing, this node of the tree, the subtree, where we're going to try and get the tunnel pointed at us, okay? And there was a bunch of ways to get a valid certificate. I've collapsed that part of the tree, okay? And more recently, we talked about, could you just use a certificate even though it's not valid? So it's going to throw an error, but maybe users will click through the error. Maybe you can make it look valid because there's some sort of implementation flaw. So even though it isn't passing all the validation methods, then it's not throwing an error because there's a mistake in the implementation. There's a cryptographic attack based on hash collisions that we didn't talk about, so don't worry about that, but it's in the tree just for completeness. You could use a revoked certificate, and then you could try to disrupt the revocation check. Or you could just not use a certificate at all. Okay, so you could do the SSL stripping attack. You could do that picture-in-picture attack. Another thing I didn't mention, but you can always put locks anywhere you want on your page. So you can have lots of locks, and you can have a password field and put a lock beside it. And sometimes when users see that, they think, oh, this is secure because there's locks everywhere. Okay, but those locks don't mean anything, right? It doesn't mean that the page is secure. you have to rely on what the browser's telling you, not anything that's in the content of the page or in the favicon. So the favicon is it's sort of hard to explain. Let me just show it to you. Let me try one other website. I'll try my personal website. You can see on my website I have this like orange slice, and so that's the favicon. Okay, and so what I could do is I could make that a lock. In the old UIL for HTTPS, the lock is how you knew that you were on HTTPS. Now it's based on whether or not secure appears or not, so it's not so useful. But anyways, that's what a favicon is. You could put a lock there, and maybe people think because there's a lock here and they're seeing it that it's a secure website, even though it's not. Okay, so this is what the attack tree looks like in its entirety. You can see it's a little big to read on the screen if we put it all together, but you can grab a copy if you're a Concordia student at Moodle. If you're watching this online, it's on my website, and you can spend some time going through it. But yeah, okay. So why did we do this exercise? We spent a long time, just to build one attack tree. But I wanted to give you a thorough example. First off, I think the issues are really interesting. Secondly, you can see that an attack tree, even though it's a high-level methodology, you can use an attack tree on anything. You can use it on hardware. You can use it on a policy. You can, anything that you could attack, you could do an attack tree for. But you can still go into a lot of detail. Okay. Now the details maybe not in the tree exactly because there's just a few words in each node. The details in the story behind each node, which normally if you were presenting this to a client or you're writing a research paper or something like that, you would have some text for every node that explains what every node means. Okay. But anyways, the other thing is notice that if you didn't know anything about HTTPS, you wouldn't come up with this tree. So even though it's a high-level methodology, it's a way to get started, it doesn't let you find attacks in things unless if you know a lot about the underlying protocol. So we had to learn a lot about HTTPS to even understand all of these attacks. Okay. But the attacks themselves, you have a very wide breadth of attacks. So these aren't all technical attacks. Some of them are. Some of them have to do with cryptography. But other ones are like, hey, go over, use your government and go over to a CA and legally compel something, or do social engineering and try and trick someone to thinking that you still work at Microsoft, even though you don't work at Microsoft anymore. There's stuff that you saw fail open and fail close. So anyways, there's a whole breadth of attacks. And what I like about an attack tree is they can all sort of hang out in one deliverable. You don't have different methodologies because the nature of the attacks are very different. What you're doing is you're sort of letting them all sort of, they're all valid ways, and the adversary is going to choose the easiest attack. And if that involves going through a human instead of going through a server, then they'll go through a human instead. Okay. The structure can help you out a bit. So it's organized. An example of this, actually, if we just go back here, you can see like I have obtain a valid certificate, an invalid certificate, use a revoked certificate, use no certificate. So that structure sort of helps you. You sort of say, what are the other kinds of certificates? Like say I didn't have no certificate here. I'd be like, okay, I could use a valid, an invalid, a revoked, so one that was valid but is now invalid. Is there any other kind? Well, what about no certificate? And so maybe I wouldn't think of putting this node in until I see these three nodes, and then it makes me think, okay, yeah, that's another way of doing this kind of thing. So that structure, I think, also can help you like try and think about other paths that are possible. Okay, and then I mentioned this before, but attack tree sort of tells you a story. So if you were to start at the root node and kind of go along one of these paths, it would tell you the full story of the attack, and you would be able to understand it kind of from start to finish. Okay, so attack trees are great. Okay, so that was all I wanted to say. And so it was a lot to say, but we're now finally through. And so I'll see you in the next lecture.